Even if you know nothing about organic chemistry, you are practically at state zero, or maybe you know organic but you need a very strong revision. In all possible scenarios, this GOC one shot is definitely going to help you to get 2, or if you're lucky, maybe 3 questions from this GOC area which you can correctly attempt in just your January JEE mains. But for that, you have to finish this video till the end. This GOC will also be helping you to make a foundation for all of the organic chemistry, which will be helping you in your boards also, and definitely after that for your advance also. Because of the huge importance of GOC, I have separated this chapter also in 2 halves. In GOC-1, we'll be discussing regarding the nomenclature, IUPAC, isomerism, and all the possible questions that you may encounter in your JEE examination. And in GOC-2, we'll be separately discussing the electron displacement effects, aromaticity, the application in assigning the stability of reaction intermediates, acidity, basicity, all those topics we will be separately covering in GOC-2, because I do not want to overburden you with just this big one shot, because this GOC has definitely got a big importance in whole of your organic chemistry. Do not worry to write all these lecture notes, and also you will be requiring too many questions to practice, which we have specifically selected for you to attempt, because those are the most probable logics which NTA is definitely going to ask. Just go to the description section and you can download everything for free from our beautiful PW app, which is also helping thousands of students every year to excel in their competitive journey. So let us explore this side of organic chemistry. Yeah, so to begin with, all the basics involving general organic chemistry, the related nomenclature, IUPAC, which will definitely land you 1 question in JEE mains, along with isomerism. This all topic we'll be dealing in GOC-1, and after that the electron displacement effects, the inductive, resonance, hyperconjugation, mesomerism, and their applications. There's the stability of reaction intermediates, aromaticity, acidic and basic nature, that we'll be discussing in GOC-2. So to begin with, we have 118 elements in our periodic table. So the study of 117 elements and their compounds, it's done in a chemistry called inorganic chemistry. And the study of this one element, this carbon, is given so much of preference that 33% of our chemistry is just devoted on carbon and its compounds. Sir, carbon forms so many compounds that 117 elements on one side and carbon on other side. Yes. Then carbon must be having some versatile nature that it is forming so many compounds. Yes. And the versatile nature of carbon, you know from your basic classes, that carbon is always tetravalent. It has ability to form 4 bonds. It is showing catenation, isomerism. The self-linking property is called catenation. Isomerism we'll already be discussing. So there are so many compounds of carbon in nature. We as humans, all the living beings, are all made up of carbon. So initially, to the history of organic compounds, it was a vital force theory was postulated by Berzelius, and he believed that organic compounds are only naturally occurring. A vital force, a mysterious force, that is a force of God only, a force of nature only, can build those organic compounds. But this belief was superseded by Wohler, who created the first organic compound in lab, the urea. Urea was formed by the rearrangement of ammonium cyanate, which is itself formed by action of potassium cyanate and ammonium sulfate. So this urea became the first organic compound which have given us this definition which we have till date, that is, study of carbon and its compound is called organic chemistry. Now, what carbon compounds which we generally encounter is represented by these. Sometimes question gives you just the molecular formula, carbon, hydrogen. It has other elements also like oxygen, nitrogen. So this becomes the molecular formula of your organic compound. It can also be represented by showing its structure, where all bonds are shown like this. You may get your question like this also. Then condensed formula, in which you have to think that carbon is tetravalent, and then you, from the condensed formula, you draw its structural formula and then write its name. And many a times in JEE, the bond line projection, in which we do not show C bond H. Every carbon is just represented by a dot, by a corner. So these are all are the representation of the compounds, the carbon compounds that we'll be getting. Now, moving ahead to the hybridization of carbon. We very well know through chemical bonding that central atom, when approached by combining atoms, so carbon, because organic chemistry is about carbon, so carbon when approached by combining atom hybridizes its orbital. The first bond formed by carbon is definitely the sigma bond, and bond formed after formation of sigma bonds are called pi bonds. Formed by sideways or lateral overlap. Pi bond, remember, is always weaker than sigma bond. So whenever pi bonds are introduced into a carbon chain, it makes the carbon chain reactive. Now, talking about the hybridization, carbon forming 4 sigma bonds is sp3 hybridized. Carbon forming double bonds as an alkene carbon is an sp2 hybridized carbon. Remember how to calculate hybridization state? By summing the steric number. Steric number is nothing but summation of bond pair plus lone pair. For bond pair calculation, we only count the sigma bonds. So alkane has how many sigma bonds? Sir, we definitely know this. Alkanes have 4 sigma bonds, so steric number becomes 4, hybridization becomes sp3. This is the carbon to which we say the electronegativity of an sp3 hybridized carbon is the 2.5. The electronegativity of Pauling scale that we know is an alkane. For alkene and for alkyne, S character increases because S character is in an sp3 hybridized system is 25%. While S character in sp hybridized system is 50%. So who is an sp hybridized carbon? An alkyne. A carbon of an alkyne is an sp hybridized carbon, so it is electronegative. You have to remember this. Now, why it is sp hybridized? Because it is forming 2 sigma bonds. So bond pair becomes 2. There are no lone pairs. So steric number for an alkyne carbon is 2. So hybridization is sp. The alkene carbon has 3 sigma bonds, so steric number will be 3 and hybridization state will be sp2. Now, talking about its electronegativity, hybridization is the modified, because modified, it is theoretically proposed in VBT that central atom modifies itself, hybridized itself, and equivalent bonds are formed. So hybridization is that process of modification of atomic orbitals when it is approached by central atoms to form more and effective and strong covalent bonds. Now, electronegativity. We very well know on Pauling scale, fluorine is the most electronegative atom followed by oxygen. Now, the carbon that we know is an sp3 hybridized carbon with electronegativity of 2.5 on Pauling scale. An sp hybridized carbon, although you do not have to learn the value, it is 3.25. That means it is more electronegative than even nitrogen. So sp hybridized carbon, then nitrogen, then your alkene carbon, which is sp2 hybridized, and the least electronegative obviously is the alkane. So the carbon that we know is an alkane carbon with electronegativity 2.5. If it becomes alkene or alkyne, percentage S character increases, and S is that orbital which is penetrated towards the nucleus. What nucleus wants? To attract electrons. So as S character increases, electronegativity increases. We already have discussed this in chemical bonding, but I'm iterating it again. Now moving ahead. Sir, simply hybridization is asked. Yes, means just simply ask you hybridization. So for example, this question, in this question you are asked, you have to tell the hybridization. Although options was also there, but I've removed those options. So this carbon is forming 3 sigma bonds with hydrogen, 1 sigma bond with this carbon. So sir, it's an alkane. That means its hybridization will be sp3. This is an alkene forming 3 sigma bonds, so its hybridization will be sp2. Very simple. And let's say this is C. So how many sigma bonds? 1 with oxygen, 2 and 3. So its hybridization will also be sp2. This is a JEE Mains 2021 question. Moving ahead. Now, what is an allene? Allene is a conjugated, it's a cumulated diene. For example, C double bond, C double bond, C. Why I'm saying cumulated? Because this carbon, after formation of two sigma bonds, will, let's say this is x-axis, this is y-axis, so it must have formed the pi orbital using, let's say, py. So this is the 2py unhybridized orbital overlapping with another 2py of another carbon. Now, because this is x-axis, let's say this is y-axis. Now, this carbon, the other pi bond that it is making, it must be available in the pz orbital. So this will be having a sidewise overlapping on the along the z-axis. Now, this is a beautiful picture of an allene. You should know this. This is asked by okay, this is AIEEE, but JEE mains also, because AIEEE, JEE mains initially used to termed as AIEEE. So I just remove these pi cloud and will show you the constituent atoms. So this becomes, okay, it should be C2H4. So this is an allene, sir. Now, what are you asked in this question? The hybridization state. So let us do it. So can you tell me the hybridization? Yes, sir, easy. How many sigma bonds this carbon is forming? Sir, 3. So this hybridization is sp2. Similarly, it is also sp2. What about this? So the middle carbon is only forming 2 sigma bonds. So its hybridization state will be sp. So sp and sp2 are the hybridization states. So sp and sp2, option B is right. Moving ahead. Now, a very famous question. The reason I'm giving you, because I want you to practice hard, practice good questions, so that mains will be a piece of cake for you. Now, because question most of the time ask you count the number of sigma bonds, pi bonds, lone pairs. So let us try one Lewis structure. Now, the formula which is given to us is C3N3 azide whole thrice. Now, remember benzene structure. So obviously, because there are no hydrogens to satisfy the tetravalency of carbon, so we definitely have to use a cyclic structure. 5 and 6 membered ring structure are free from any type of strain. That's why if you try to make some structures, although you should know some structures also, so I'm thinking of a structure like a benzene with alternate positioning of carbon and nitrogen. Okay, sir. So then we should know also this now. That's why while practicing, you should definitely see to some questions. So how many sigma bonds I formed till now? Sigma bonds, sir, 1, 2, 3, 4, 5, 6. Okay, 6 sigma bonds formed. Now, to this N3 whole thrice, this is an azide group. So let me make that azide group over here. This nitrogen, a double bonded nitrogen, and again a double bonded nitrogen. Sir, nitrogen has 5 electrons in its valence shell. Okay, so let this nitrogen lose 1 electron, so it attains a positive charge. Nitrogen forming 4 bonds, octet complete. So this is feeling good. What about this nitrogen? 5. So 3 bonds are there, so octet complete. What about it? What about this one? If it has lost 1 electron, somebody has to gain that electron, because this molecule is neutral. So let us give that extra electron to this nitrogen. If nitrogen gaining 1 electron, after 5, after gaining, it will have 6. 2 bonds, octet of this nitrogen is also complete. Now, this structure will definitely be available in all the carbons, because I need to satisfy the molecular formula. Double bonded N and again a double bonded N. This will have a plus, this will have a minus. Now, let us count the sigma bonds first. Sir, 1, 2, 3, 3 sigma bonds here. So 3 ja 9, 9, 10, 11, 12, 13, 14, 15. So sigma bonds are 15 in number. Now, sir, but octet of carbon is not complete. I know, but I am mentioning it with different color so that parallelly we'll draw the Lewis structure also and we'll calculate. This is the way you should do in exam also. We'll calculate pi clouds. Sir, some pi clouds we already see. Yes, what are those? Sir, 1, 2. So 2 they are having. So 2 into 3, 2 3 ja 6. Then sir, there will be, because carbon octet has to be complete. This carbon is complete. This nitrogen octet has to be complete. Now it is complete. So these 3 pi clouds will also come, just like alternate pi cloud of benzene. So sir, 2 into 3, 6, 7, 8, 9. So how many pi bonds we have? 9. Now, The question also is asking you to calculate the number of lone pair. Okay, sir. Now, nitrogen has outermost 5, but one extra, so 6. 2 are here. So 3, 4, 5, 6. So these are two lone pair. This guy has lost one electron, so no lone pair left. But yes, this guy will have one lone pair. Now, who else? Sir, these nitrogens will also have their lone pair present. Yes. So let us count them. So this system has 2. 1, 2, 3. Okay, 3. 3 into 3 is 9. 10, 11, 12. So how many lone pair of electrons I have? 12. So these integer type question can also come. Like you have to give the summation of them. And let's say the question says the summation is AB, give the value of A plus B. So these type of questions you can very well expect in mains. Moving ahead. But what question I have given you is a question to practice. These are the question which comes in JEE mains. Now you have to just tell the number of sigma bonds. So let us count those sigma bonds. So 3. So this is 4, 5, 6, 7, 8, 9 and 10. So number of sigma bonds are 10, just like that. What are the number of pi bonds if I'm asking you? Although question of JEE mains was just asking sigma bonds. So our question is done. We are just practicing. So 1, 2 and 3. So how many pi bonds? 3 pi bonds. Moving ahead. Now how these, sir, their organic compounds are so many in number. Okay, so let us classify them. So organic compounds may be open chain, that is acyclic. They may be closed chain, that is cyclic. Point classification number 1. Now open chain are further classified as saturated. Saturated as in when carbon just has single bonds called alkanes with general formula CnH2n plus 2. If they are unsaturated, they may be alkene with a double bond with general formula CnH2n, or they may be alkyne with a triple bond having general formula CnH2n minus 2. Now, if they are cyclic as in closed chain, they may be homocyclic as in all cycle formed by carbon only, or they may be heterocyclic that apart from carbon they'll be having some other element also forming that particular cycle called the heterocyclic compounds. Now homocyclic compounds can also be aromatic or alicyclic. Now what is an aromatic compound? Aromaticity we will separately discuss. It's a proper definition, but just to give you a basic, because that basic also helps you. Sometimes that basic only makes a question in mains. Now, aromatic is a synonym of stability. So whenever an organic compound is aromatic, it attains a stability. So for time being, we just say if it is aromatic stable. How do I attain aromatic stability? Again, I'm telling you, it's a proper definition, a 3-step definition that we'll be covering when we'll be discussing aromaticity after resonance, because it has got conjugation, a current flowing effect which stabilizes the pi cloud. So for time being, we are saying if it is stable as an aromatic, then it's an aromatic homocyclic. It may be an aromatic heterocyclic compound. And what all cycles are not extra stable, that is are not aromatic, will be termed as alicyclic. For example, alicyclic is any cycle that you will get of carbon. Homocyclic, homoatomic, alicyclic is, I just draw. This is a cycle. This is what? Cycle made of carbon. So yes, it is homocyclic. Whether it has got any extra stability? No. So if it is not aromatic, it is alicyclic. So whatever cyclic structures you have, like 5-membered, 6-membered, 7-membered, from 8 members, because crowding increases to such a large extent, so generally 8-member rings are always non-planar. You should also remember this. So these are some homonuclear alicyclic organic compounds. Talking about the homonuclear aromatic, there are few famous examples. This is a ring formed by just carbon, so a homonuclear organic compound. This is a ring formed by just carbon, so a homonuclear aromatic compound. But what type of aromatic? Because it is having that extra stability. What are these examples? Azulene, a very famous example, 7-membered ring, and there are 2 rings fused together. Now, tropolone. These are few examples I wish you should always remember. So these becomes your homocyclic, as in cycle formed by carbon, but non-benzenoid aromatic compound. What about benzenoids? Carbon can also form an aromatic compound. So this benzene and all the substituted benzene becomes benzenoids. And to the classification, this homocyclic may be alicyclic, like cyclopentane, hexane, heptane, and aromatic. Aromatic may be benzene containing stable compounds, which are called benzenoids, and I can also be aromatic but not containing benzene, so I will be non-benzenoid aromatic compound but having homocyclic nuclear chain of only carbon. So these are few examples. Now talking about the heterocyclic compounds, a cycle which is formed not by carbon but along with carbon there is some other element also. So heterocyclic compounds may also be aromatic, and if not aromatic I will be termed as alicyclic. What about examples of heterocyclic aromatic compounds? Very famous examples I have already written. This is pyridine, nitrogen coming to the ring. So it is a 6-membered ring but containing 5 carbons in the ring and 1 nitrogen. The very famous pyridine, it's a base. Now the thiophene with sulfur forming this 5-member ring, and these all are aromatic. Then furan is a 5-membered ring with oxygen. Now if we remove this aromaticity, they also becomes a heterocyclic alicyclic compound. Like I've removed these pi clouds from furan, it becomes THF, the very famous solvent tetrahydrofuran. Pyran, although there are 2H, 4H, pyran also has got nomenclatures, but for heterocyclic compounds naming is not there in our syllabus, so we should not just know these because they will. For THF, furan and pyran are some structures used in biomolecules, so I've given you these structures. So these are some basic examples of heterocyclic alicyclic compounds. Moving ahead. Now sir, why you were telling those discussion classification? Again a IEEE question, as in JEE mains question. Okay, this is 2020, so this is JEE mains only, because in our times this the JEE main used to be termed as IEEE, so this is JEE mains only. Now let us okay, now although it's a very basic thing, Spiro and bicyclo. So what's a bicyclo compound? Bicyclone, with the name is also suggesting you there should be 2 cycle and they should be fused together using 2 or more carbons. Sir, can we see 2 cycles? Yes, I can see 2 cycles. 2 cycles are fused by 2 carbons, so this becomes a bicyclo compound. So B is 4. Sir, what about Spiro compounds? When 2 carbon rings are fused together using a single carbon. Sir, we have 2 rings, yes, fused together using a single carbon. They are termed as Spiro compounds. So these are Spiro compounds. So C is 1, B is 4. C is 1, C is 1, C is 1, C is 1. Okay, C is 1 and B is 4. Okay, using them, because this is not your answer, so I've got my answer, by the way. So this is a JEE mains question, so this is how you do option elimination and quickly finds your answer. But just for the sake, I got the answer, but just for the sake of doing the question. Now this is a heterocyclic compound. Yes sir, recently seen. It is not aromatic. This is also heterocyclic compound but an aromatic one. So aromatic compound, yes, this is aromatic, and heterocyclic compound, yes, it is heterocyclic. Why non-planar is written? Because oxygen has what structure? Bent structure. So this is also bent, this is also bent, this is also bent. So I'm not restricted to be in a single plane. I am a non-planar molecule, because every carbon also over here is an sp3 hybridized tetrahedral carbon. So moving ahead. Now after these basic questions, okay, now let us move to how we specify the degree of carbon and degree of hydrogen. Very simple. As I've already told you, carbon has a tendency to form how many bonds? 4 bonds. So catenation, so tetravalency. Now let us look at this picture. Sir, this is a bond line projection. Yes, because here only lines are shown. So at least we can predict the carbon present. So this is one carbon. Now this carbon is attached with how many carbons? 2 carbons. So it becomes a 2 degree. So because I'm mentioning a 2 degree carbon, the green color, I'll remember this. Hai na? So this is a 2 degree carbon. So how you specify the degree of a carbon? If I am a carbon and I am directly attached with 2 carbons, so I'll be called a 2 degree carbon. The hydrogen associated and connected with me will be termed as 2 degree hydrogens. Moving ahead. What about any 2 degree? No. What about this one? So this is a carbon. In order to make it tetravalent, there will be 3 hydrogens because CC bonds are shown by the by these lines. So how we will think about hydrogens? Do the tetravalency of carbon, because it is having only 1 bond. So the other 3 valencies will be satisfied by hydrogen. So this becomes my 1 degree carbon. Why? Because I am connected only with 1 carbon. So 3 hydrogens. So these hydrogens will become 1 degree hydrogen and carbon will become 1 degree carbon. Now, some other 1 degree carbon, I guess you can easily see these will again be 1 degree carbon. Now, what about this one? Sir, this carbon is connected with 1, 2 and 3. That means it will be having just 1 hydrogen. So because I am connected to 3 different carbons, so I will be termed as a 3 degree carbon and my hydrogen will be termed as a 3 degree hydrogen. Now, sir, do we have a 4 degree carbon over here? Yes, this carbon, because it is directly with 1, 2, 3, 4. So it becomes a 4 degree carbon. And do 4 degree hydrogen exist? No. Carbon is always tetravalent, so it can form 4 bonds. If all of my 4 bonds are made with carbon, then I will not have any 4 degree. I will not have any need of hydrogen. So there cannot exist a 4 degree hydrogen. Now, how you quantify the degree of alcohol, alkyl halides and amines. Now discussing first of alcohols and alkyl halides. What are alcohol? Sir, from class 10th only I know alcohol is a functional group constituted by O and H. Now, because how many the OH has to be present, then only I will be termed as alcohol. So how many valency this O has to be bonded to carbon chain? Only 1. So degree of alcohol also and degree of alkyl halides also. What are alkyl halides? When carbon chain is connected with any halogen. So this halogen, this X can be fluorine, chlorine, bromine, iodine. Astatine we do not take because nature astatine property is more or less down the group, metallic nature increases, so it is not even treated as a halogen because in nature no properties of astatine is seen to the mother nature as halogen. So for halogens we only take from fluorine till iodine. Now because alcohol and halogen both has only 1 bond, therefore their degree is not decided by them. Their degree is decided by the carbon to which they are directly attached. So if I am alcohol, that is OH, if I am alkyl halide as in any halogen, the carbon to which we are connected will define our degree. So this carbon can further have 3 bonds. This also can have 3 bonds. So if these 3 bonds are connected with some carbon chain, to the carbon chain we generally represent as R. So this may be R1, R2, R3. If all these are carbon chains, then this will become a 3 degree alcohol. If this R3 is hydrogen, then it's a 2 degree alcohol. Similarly, if this R1 and this R2, they are also hydrogen. So this is CH3OH, methanol. So methanol, because this carbon is not connected, so it is even not 1 degree. It's a methyl alcohol. So what is the degree of a methyl alcohol? You cannot define its degree because that carbon is not connected with any carbon. So we simply say it's a methyl alcohol. Similarly, let's say this is R, this is also R, and this is H, then this alkyl halide becomes a 2 degree alkyl halide. So for alcohols and for alkyl halides, the degree is not decided by them. because they just have one free valency. Their degree is decided by the carbon. If this carbon is connected with different carbons, then they decides the degree of alcohol and alkylides. You will get too many questions. I'm just summarizing everything. Now, what about amines? Sir, amine is functional group of nitrogen. Now, this nitrogen is not a monovalent species because nitrogen has how many electrons in its valence shell? 5. How many bonds it can make? It itself can have 3 different bonds. And if this lone pair is given, it can even be quaternary, as in 4 degree. But generally, what we see is neutral amines. So that's why I'm not mentioning that 4 degree, although in amines chapter, we'll be discussing that also. But here we are just simply defining the degree. So degree of amines is decided by, has nothing to do with what carbon I'm attached with, because I myself has different valency. I myself is a covalent molecule. I myself having polyvalent atom, polyvalent species. So let's say if this is R and these are both H, so this will be a 1 degree amine or simply primary amine. If I am connected with 2 different, I mean this carbon can be any number of carbon, any type of carbon. You are a carbon connected to me, you are a carbon connected to this R and R dash, may be same, may be different. So this becomes a secondary or 2 degree amine, and obviously this R, N, R dash, R double dash will form a 3 degree or a tertiary amine. Now, because degree of alcohol is decided by the carbon, therefore when go to aromatic, now what are phenols and what is aniline? Phenol, when OH is directly connected with benzene ring. Now remember, aromaticity we will be defining, but this we know that aromatic character provides extra stability to a compound. So because benzene is a stabilized carbon structure, so if this carbon is attached, if this benzene carbon is attached with OH, then this is definitely a functional group, but this is not a simple alcohol. This is a aromatic alcohol, and hence aromatic compounds are generally named by their general names and known as phenol. So what's an aniline, sir? When this aromatic benzene ring gets connected to nitrogen. Now, in order to satisfy its valency, how many hydrogens I need? 2. So this becomes the structure of aniline. Now, after knowing how to quantify the degree of alcohol and amines, can you tell me what is the degree of this phenol? Now, because it's an aromatic system, it's not a simple carbon system. So degree of phenol is not at all defined. If someone, although this is, it means will not trick you because this is good logic, but I'm giving you this logic that the degree of phenol is not defined. But when someone asks you what is degree of aniline, then nitrogen degree is not decided by the type of carbon. If my one bond is connected with any carbon, I'm 1 degree. So this is definitely a 1 degree or primary amine, but to this I cannot say it's a 2 degree alcohol. For alcohol, for phenols, degree is not defined. Moving ahead. Now, coming to the degree of unsaturation, as we already know through chemical bonding, but still in organic chemistry, I'm giving you every basic. Alkanes as in sp3 hybridized carbon is generally not reactive. If you want to make any reactions of alkane, you have to be very vigorous. Very extreme conditions will make everybody react. So generally alkanes does not react, but due to presence of pi cloud, because pi bond is a weaker bond, so due to presence of pi cloud, reactivity of carbon compounds increases, obviously. So because reactivity increases, therefore this term comes into great application for us. Now what is this? Degree of unsaturation. Because unsaturation increases reactivity, so what is our reference point to which carbon we assume as reference? Sir, alkanes. So let's say formula of an alkane is CnH2n plus 2. Now, if this alkane contains 2 hydrogen less, so if this if I remove as in minus 2 hydrogen, where I will reach to, sir, 2 hydrogen removed. So the formula which I'll be getting is CnH2n. Sir, this is a general formula of alkene? Yes. This is general formula of alkene also, but this is general formula of cycloalkane also. That is, if I remove 2 hydrogen, the general formula reached is having 2 hydrogen less than the saturated alkane. So to this deficiency of 2 hydrogen, we theoretically also say that its du as in degree of unsaturation is 1. Some people to this degree of unsaturation term, they also term as index of hydrogen deficiency. Some term as double bond equivalent, the DBE. Some terms it unsaturation index. Somebody there are many references which ask you to calculate the du when molecular formula is given. What I suggest is, we anyway have to remember so many things, so even if you do not learn this formula, you can predict du. How, sir? Du is unsaturation with respect to whom? With respect to alkane. So if there is a deficiency of 2 hydrogen, there is du of 1. So if somebody has 1 du, that means it can be an alkene or it can be a cycloalkane. Let's say if I remove 4 hydrogens, then obviously, sir, du will be 2. So my formula becomes CnH2n minus 2. So I can be what species? I can even be an alkyne, because 2 hydrogens deficiency can be compensated by a pi bond. So if I'm having 4 hydrogen less, that is my du is 2. So 1 pi bond is satisfied by du1. So 2 pi bonds will satisfy du of 2. So I can be an alkyne. I can even be diene as in 2 alkene. I can even be, because when I become cycle, then also 2 hydrogens are reduced from my molecular formula. So I can even be a cycloalkene. We'll be seeing too many questions employing this information in isomerism side of our GOC. So this you should keep in mind. We'll be definitely seeing many examples. Moving ahead. Now, coming to one definition, homologue series. Now, what are homologues? Homologues are those members of a family which basically have all the same chemical properties. So a group of series of organic compounds, each containing a specific characteristic. Our reactivities will be same, because we are all same family members. So how we are different? A family is different by differentiated by the age. Bigger brother, younger brother, then siblings, whatever. So in organic compounds also, if they have same functional group, but they have different mass and formula, then they are called homologues. And what is the difference between two successive member? A difference of CH2. For example, let's say alcohol. So the first member of alcohol family will be a 1 carbon alcohol. Add CH2. So CH3, CH2, OH. This becomes 2 carbon alcohol. Again add 1 CH2. So this becomes a 3-membered alcohol. So sir, they are all having same chemical properties? Definitely yes. So how they are different? They are just different. They just have got a difference of their mass, their difference by CH2 units of each successive members. So definitely sir, because mass is more, so their physical property will be different, but their chemical properties are same, and they are called homologues. Moving ahead. Now, directly jumping to the, after doing some basics, directly jumping to the most important, which will definitely land you one question in your JEE mains, that is, even advanced sometimes ask just what is the correct IUPAC ABCD. Now, directly jumping to nomenclature. Now, who are we naming? Organic compounds. Organic compounds are compounds of carbon. Because there are so many organic compounds existing in nature, we have to characterize them. So our name was given by our parents. So the parents of organic compound is a community called International Union of Pure and Applied Chemistry, the famous IUPAC. And they decide to name their children. they're the organic compounds. Like in northern side of India, how we name ourselves? Divided in three parts: name, middle name, and surname. For example, my name is Gaurav, my middle name is Singh, and my surname is Arora. So naam, middle naam, and sarnaam is the general scheme for naming a particular person. This general scheme is different for different region, but in whole of the world, the organic compounds are governed by whom? By the International Union of Pure and Applied Chemistry. So they have designed and designated the general scheme for naming of their children, which are the organic compounds. So the organic compounds name is divided into 5 parts. Like our name is divided into 3 parts: name, middle name, and surname. In the southern side of India, my roommate, my first year roommate, Prashant Ramesh, from when I've recently gone to NIT Kurukshetra at my year back in 2007, there was only 9 seats of Madhya Pradesh. I belong to MP. 2 seats in each department. There were 4 departments. Industrial was the very new department at that back in 2007. So industrial engineering and management just had 1 degree, 1 seat for MP, Madhya Pradesh board, the Madhya Pradesh state, the domicile state. So in the first year, roommates are given, by the college. Then you can switch after a month. So my roommate was from Tamil Nadu. His name was Prashant. His name is Prashant Ramesh. I was very curious. What Ramesh? So Ramesh was actually name of his father. Because in southern side of India, the rule for general scheme for naming is name followed by, there's no surname. Surname they generally take off their father. I mean, not everywhere. My friend was from Tamil Nadu and his name was Prashant Ramesh. So general scheme is different at different parts of the world. So in order to normalize, IUPAC said that our children will be named, the general scheme will be divided in 5 parts. Out of those 5 parts, the third column becomes the word root, which signifies the number of carbon present in that particular organic compound. To the number of carbon atom, we represent as R, and how many carbon you have in your main chain is represented by the word root. So let's say if an organic compounds contain 1 carbon, so the word root becomes meth. If I have 2 carbon, word root becomes eth. Similarly, prop, bute, pent, hex, hept, oct, non, dec. Although 11 carbon it is undec, 12 carbon it is dodec. But for even JEE advance, till DEC, till 10 carbon chain is more than sufficient. So I have stopped at 10 carbon. Now, this represents the word root. The third column represents the number of carbon present in the main chain of an organic compound. Now, after word root in English also we know word root is supported by suffix, and it is, if some abbreviation is coming before word root, that is referred as prefix. So there are 2 different suffix and 2 different prefixes. The very first becomes the primary, so primary prefix becomes column number 2. Similarly, primary suffix becomes column number 4. Now, what does primary suffix tells us? Whether our carbon chain is saturated or unsaturated. The length is given by column 3, word root. If I am saturated, that is, if all the carbons in the main chain are single bonded, primary suffix used will be ane, ane, ane. If anywhere in the chain double bonded carbon is present, then this primary suffix is used, then ene is used as primary suffix, signifying presence of double bonded carbon in the main chain. And if the main chain, the carbon chain is containing a triple bond, then it is represented by the word ine. So this becomes the primary suffix. Now, if my main chain is cyclic, remember that classification, cyclic, then how will we specify? column 2, that is primary prefix, will tell us that whether the chain is, if it is cyclic, we'll use a prefix cyclo. Sir, if it is not cyclic, then this is not applicable. Like in my friends also, I mean, I have a very close friend. His name is Gaurav Agrawal. He do not have any middle name, so he do not leave any space. Gaurav Agrawal. So if there is, if I'm not cyclic, will I leave a space? No, I will just do not write anything as primary prefix. Now, we all know that apart from carbon, carbon contains many other elements also. Those elements drastically change my properties, and in order to respect those extra added elements, we refer them as functional groups. So whatever element attached to a carbon, if increasing the and changing the property of a carbon like anything, then to those elements we refer as functional groups. And what all functional groups are connected to our carbon chain is signified by the fifth column, that is the secondary suffix. So functional groups, we will separately dealing what are those functional groups. But there are some functional groups which are definitely not carbon, but they change the property of carbon to not that large extent. Therefore, they are functional groups, but they are not given a preference, a privilege of getting into the fifth column of secondary suffix. Instead, they are treated as a branch. And to a branch, IUPAC suggests you name all the branches in column 1, as in you mention their secondary prefixes. Sir, so give us some functional groups which changes the property of carbon, but not to that large extent. Therefore, IUPAC has given them preference of being just a branch. They are not given a special preference of a real functional group. Although they are, or no, for just to name them, you will say they are functional group. But those functional groups are treated as a branch. Those functional groups are treated as a branch. And to these branches, we do not write their suffix. We write their prefixes. So the famous example are all the halogens, fluorine, chlorine, bromine, iodine. What are their prefixes? If F is there, we write fluoro. Cl we write chloro. Br we write bromo. Iodine we write iodo. And sometimes even a carbon, like we have a rule for selecting the main chain. If a main chain is selected by applying the rule, we'll be seeing that rule. If a main chain is selected. Now, if in that main chain, some carbon only is remaining, not counted in the main chain, then that carbon will also be treated as a branch. So it may be of 1 carbon, 2 carbon, 3 carbon. So how we represent the number of carbons? By the word R. That's why I've written R. What is this? So this is the free valency with which I'm connected to the main chain. So these all are free valencies by which these branches are connected to the main chain. So this R is connected to the main chain. But sir, how we will name this R? Remember, number of carbon represented by R, to which we generally refer as alk. I mean, if that chain is of 1 carbon, so that alk will be meth. If that branch is of 2 carbon, then that alk will be eth. If it is of 3 carbon, that alk will be prop. So generally, to this R, I'm representing as alk. So meth, eth, prop, but, whatever number of carbon present in that particular branch. But because it is a branch, I will further add YL to this. So 1 carbon branch becomes methyl, 2 carbon branch becomes ethyl, 3 carbon branch becomes propyl, so on and so forth. Now, sometimes this carbon do not directly gets attached to the main chain. Instead, it uses an oxygen for the direct connection with the main chain. then this becomes the main chain. That is, main chain is also carbon chain we represent as R. So this R, O, R is generally, this functional group is termed as ether. This functional group is generally termed as ether. But this ether also changes the property of carbon, but not to that large extent. So it is also treated as a branch, and for a branch we name its prefix. So the secondary prefix of OR becomes R is represented by alk, but this alk is not directly connected with the main chain. If it would have been directly connected, we would be naming it as alkyl. But this alk is not directly connected, is connected with an O. So here we will use the suffix oxy. So let's say if to the main chain the branch is O, CH3, one carbon. So for one carbon, alk is meth, so it will become meth oxy. If two carbon is connected with an O as a branch, so O C2H5, so 2 carbon is eth, so it becomes eth oxy. Similarly, prop oxy, bute oxy, so on. Now, one more branch you should know, because we have already discussed and mentioned that pi bond of benzene, double bond of benzene, we do not even write those double bonds, we make it a circle because they are stable, they do not react. Aromatic is a synonym of stability. Sir, if they are not reactive, then they will also not be given preference. Yes, and therefore benzene itself is treated as a branch because it is not reactive as a simple alkene, it is a stable molecule. Therefore to the whole of benzene ring, what is benzene ring? C6H6. But because I have to connect that with the main chain, I have to take one hydrogen, so it becomes the free valency C6H5. Sometimes it is written as phenyl pH because its prefix is phenyl. Yeah, so one more functional group, the NO2 group, but treated as a branch, is prefixed as nitro group. So moving forward, and now discussing about how this main chain is selected. So in order to select a main chain, obviously we have to go to a carbon. We have to start from a carbon. So we'll start from what carbon? The priority says you should always select that carbon which is containing the functional group. After that, priority goes to the multiple bonds, that is double bond and triple bond. After that, the priority goes to maximum number of carbon atoms. After that, the priority goes to maximum number of branches. After that, the priority goes to the branch's location has to be lowest, that is the lowest location or lowest locant rule. And if there is a tie, then the tie is broken by rule of alphabetization. And after selecting the main chain, you have to number the chain. So how will you number the chain? The priority is again the same. Firstly, we will be numbering so that functional group will be getting the lowest number. After that, we will be getting our priority to the multiple bonds. They should be getting the lowest number. Post that, every branch should have lowest possible number or lowest locant rule again. And if there is a tie, then it is broken by the rule of alphabetization. So for main chain selection, 6 fingers, functional group, multiple bond, maximum number of carbon atom, maximum number of branches, the lowest locant rule, and rule of alphabetization. But for numbering, only 4 fingers, functional group, multiple bond, lowest location, and the last is rule of alphabetization. Sir, but how to apply? So let's learn how to apply these rules. For example, this is our first question. First, we have to select the main chain. Because when you will select the main chain, then only you will know the word root, the column 3 of the naming scheme. So in this example, we do not have any functional group. So first option, first priority gone. This does not have any multiple bond also, so second gone. Now maximum number of carbon atom. So whenever you are going for maximum number of carbon atom, just see the junction first. Like this carbon is the junction. How to reach this carbon? By selecting the maximum carbon. So I can reach till this junction from here. How many carbons I'll cover? 2. If I'll go from downside also, there are 2 carbons. So I can go from this side also, this side also, because linearly, visually things are quite easy. So let us start from here. So we have reached till this junction. Then think of like riding a bike. Ride to the maximum distance. Now, after that, downside just have 2 carbons. So I'll definitely go forward. Now, coming to this next carbon stop, I just have to go forward only. After here, downside, I have 1 carbon, straight, I have 2 carbons, so I'll be going straight. Now, once you reach from one end to another end without any discontinuity, after that, the main chain is selected. So then retrace your path. So if you retrace your path, you will get a box, and that box will be your main chain. Then after that, circle the branches. Now numbering the main chain. So I can number from left to right or from right to left. How to number? Minimum number should go to functional group. There is no functional group. Then multiple bond. There is no multiple bond. Then the lowest locant rule. What is lowest locant rule? The location should be minimum. For example, if I number from here, from left to right, so it will be 1, 2, 3, 4, 5, 6 and 7. Okay. But I can even number from right to left. So it will be 1, 2, 3, 4, 5, 6 and 7. Now, which numbering is correct? The yellow one or the orange one? Let us go to the location, lowest location. So from orange color, the location of branch that we have is at 3 and at 5. What about yellow color? From yellow color, the location of branches are located at 3 and 5. So location is again 3 and 5. That means lowest locant rule has also tied in this particular case. So what is the tiebreaker? Rule of alphabetization. So for 3, if I'm going from right to left, 3 is acquired by CH3. Remember, CH3 is a carbon. Carbon alk is 1 carbon alk is meth, because it's a branch, so its name will be methyl starting from M. What about the yellow one? Sir, the third position is acquired by ethyl group. Ethyl starts with an E. So what does alphabetization tells you? Sir, E comes first, so this numbering is right and this numbering is wrong. So what is the name of this organic compound? Sir, name is divided into 5 columns. First we name the branch. So how many branches we have? We have 2 branches, ethyl and methyl. Which branch name is written first? Sir, again alphabetically you should write. So name will be ethyl is at 3rd position, so it will be 3-ethyl. Remember, always remember this. You have to, between a number and an alphabet, you will always put a hyphen, and for the name, the first alphabet will be capital, rest everything will be small. So 3-ethyl and 5-methyl, column 1 finished, because branches are named. Column 2 does not exist because the main chain is not cyclic. Column 3, the word root, which is hept because it is containing 7 carbon. And what about column 4? Because it is saturated, so it will be ane. So this will be the name of the first organic compound. No, column 5 does not exist because there is no functional group. Now, let us do this question. Selection of main chain. Sir, no functional group, no multiple bond, maximum carbon in cyclic chain is 6, maximum carbon in the straight chain is this 1, 1 and 2. So which is having maximum carbon? The cyclic chain. The cyclic chain becomes the main chain. Moving ahead, after selection of main chain, I have to number the main chain. Now I have to number what is the rule? Functional group does not exist, multiple bond does not exist, then maximum lowest location rule. Now if I put a 1 over here, then I can have 2 branches acquiring this position number 1. So obviously this will be 1, 2, 3, 4, 5, 6. Some people do, so this is ethyl, this is methyl. Remember, the priority for numbering is functional group, multiple bond, then lowest location rule. If lowest location rule ties, then you go for alphabetization. Here, if I've given 1 over here, then location will be 1 comma 1 comma 3. If this will be given 1, location will be 1 comma 3 comma 3. So which is lowest? 1 comma 1 comma 3. So this, because we have not reached till rule of alphabetization, so why should apply? So its name will be because how many branches we have? Sir, we have 3 branches. So which branch? Now, while writing the name, which branch will be written first? Sir, alphabetically we will be proceeding. So because this is a 2 carbon branch, so it's ethyl. So at position 3, I have the branch ethyl. Then at position 1, so what I'll do is 1 comma 1, because both are methyl, so writing them together, and in order to write them together I am using the word di. If they are 3 in number, it should be tri. So this becomes dimethyl. Column 1 khatam, column 1 finished. Column 2, sir, now the main chain is cyclic, so column 2 will be existing. So then cyclo comes. What is the size of the main chain? So word root becomes hex, because it is saturated, so column 4 becomes ane. Again, column 5 does not exist because functional, I do not find any functional group. Moving ahead. Now, some more questions. Again, selection of main chain, functional group. No, sir, no functional group. Multiple bond. Yes, sir. So main chain is this cyclic chain. What about numbering? Minimum number goes to functional group, does not exist. Multiple bond. Yes. So either this will be 1, 2 and the 3, or it can be 1, 2 and 3. Now, I've just gone till 3 because, sir, 1, 2, I can have minimum number of multiple bonds in both the yellow one while moving anti-clockwise also, and while moving clockwise also. So first, tie break. Functional group, not present. Multiple bonds, tied. Now go to lowest location rule. Now, because 1, 2, 3, after 3, I'll be having 4. I'll be having a branch at 4. But if I'll go with that orange numbering, 1, 2, 3, 4th will have no branch. So obviously, which number is right? The orange one is wrong. So let me remove that orange one. So 1, 2, 3, 4, 5 and 6, because if I'll be going that from that ways, 4th position will not be having any branch. So again, I have not reached till rule of alphabetization because lowest location has given me my answer. So numbering done. So writing the name first, what is written? The branches. How many branches I have? Let us circle the branches. This is 2 carbons with an O. If 2 carbon directly attached, it's an eth but yl. But if these 2 carbons are connected via oxygen, so it's a ether prefix. What is the prefix of an ether? Sir, eth oxy, starting with an E. This is nitro starting with N, and this is bromo starting with the B. So what will be written first? Bromo. So this will be 6 bromo. After that, E or N? Definitely E. 3 eth oxy. One more branch? Yes. Column at 4th position, I have the branch nitro. So this is column 1 finished. Column 2, yes sir, main chain is cyclic. So it is cyclo. Just always do this column 1, 2, 3. So column 2 done. Column 3, the word root, which is 6 carbons. So hex. Column 4, because it is unsaturated, so there is an ene. Double bond is present between first and second carbon. We generally speak out and write the lowest number. So among 1, 2, which is lowest? 1. So hex 1 ene. No functional group, so it is done. Sometimes when name is given to you, this 1 can also be omitted. So it can either be written as hexene. So if it is hexene, then what is the predicted position for the double bond? 1, 2. Because 1 you can write also, you can remove also. If you are writing the particular answer, you should always have a habit of writing it, because if it is not 1, then some students used to miss it. So never miss it. If there is no mention of the number of the unsaturation unit, then it is definitely 1, or else whatever it is, you should write. Now, this is finished. Coming to the condensed formula. Sir, it is a condensed formula? Yes. So how we will write its name? By expanding the formula first. So what does Me represents? Me represents methyl. Many a times methyl and ethyl are written as Me and Et, hence written that also. So while writing the expanded formula from a condensed formula, we always have to remember the tetravalency of carbon. So there are 3 Me. What is Me? Me is CH3. So tetravalency, sir, each carbon will be having 1 bond because carbon needs to form 4 bonds. Okay, so these 3 jobs are done. Now they are connected with a carbon, so that is C is written. So this will be this C, done. This C is further connected to a CH. Its tetravalency is done. Yes sir, 4 bonds. What about this? Sir, it also need to have 4 bonds. 1, 2. What about other one? Sir, it is a double bonded carbon, so it is also 4 bonds done. Now what comes next is a C. Sir, but this carbon should also have 2 bonds. Okay, making that 2 bonds. 1 bond is Me. Me is CH3. 1 bond is Et. Et is 2 carbon, as in CH2 bond CH3. So in whole it becomes C2H5. Sir, this is the exact structure of that condensed formula. Now our job is to first decide the main chain selection rule. Functional group does not exist. Multiple bond, yes, so this should be in our main chain. After that, maximum carbon. So because multiple bond is in between, so I'll go that side also, this side also, to reach the ends of carbon chain. Now while moving that side, upside only 1 carbon, there I have 2 carbon, so yes, I've reached one side. Now getting to the other side, moving to this carbon, then up, down, up, straight or down, I just have 1 carbon, so I'll be going anywhere, name will be same. So once I have reached from one end to another end, what I have to do is retrace my path, and a box will give me the main chain. What next? Circle the branches. Main chain selected. Let us number it. Now if I'll be numbering, there's no functional group and multiple bond, 1, 2, 3. From that side, multiple bond is getting at 3rd position. From this side, 1, 2, 3. So multiple bond is also tied. So tie would be broken by lowest location rule. So 1, 2, no branch. 1, 2, yes sir, 2 branches. So definitely this wins. So 1, 2, 3, 4, 5 and 6. How to name it? First, name the branches. How many branches? 3. All are same. So what are their position? 2, 2, 4. 3 as in try. What are these branches? Methyl, column 1 finished. Column 2 does not exist because main chain is not cyclic. Column 3, 6 carbon is represented by an hex, and column 4, unsaturation is between 3, 4. So writing the lower number, which is 3, ene. This is how you beautifully name any organic compound. This is the rules. Now, few questions. This is an IEEE question. Again, sir, this is the structure. Okay, so obviously we can see the main chain. Let us number that main chain. So if I'll be numbering from this side, then 1, 2, 3. Let us try from this side. 1, 2, 3. No, sir. 3 will not have any branch. So that numbering is right. 3, 4, 5, 6 and 7. So how many carbons you have in your main chain? 7 carbon. What about branches? At position number 4, I have 2 methyl. At position number 3, I have 1 ethyl. So it will be 3 ethyl, 3 ethyl, 3 ethyl, 4, 4 dimethyl, because I have 7 carbons, so hept, and because it is saturated, so ane. So without moving, just while observing, you can give your answer. And these sort of questions are got huge frequency of coming to JEE mains. Moving ahead. Again a JEE question, write IUPAC. Okay, these two questions I have to give the IUPAC. Let us give the IUPAC. Sir, no functional group, no multiple bond. So again, maximum carbon, so cyclic becomes the main chain. Let us number it. Functional group absent, multiple group absent, so lowest location will give you numbering. So 1, 2, 3, 4, 5, 6. Why, sir? Because if 1, 2, then 3, 4, 5 would be coming. So definitely starting from here, because then this will be getting 4th. Now what about the name? This is ethyl with an E. So this will be 2 ethyl. After that, 1, 4 dimethyl. Sir, column 1 finished. Column 2 is cyclo. column 3 is hex, column 4 is ane. Moving to this question, again it will be just done by lowest location because main chain is definitely the cyclic chain. Let us number it. For numbering, rule is functional group does not exist, multiple bond does not exist, so lowest location rule. Now again, this is 1 comma 1 and that will be 3, so this is just the same question. 1 2 3 4 5 6, so this will be 3 ethyl 1 comma 1 dimethyl cyclohexane. Moving ahead, the same question which we have done. Now IUPAC, again this is 2019 question, a very latest question. This is having both the multiple bonds. So again, functional group does not exist, multiple bonds, yes sir. Where is it? Over here also and over there also. Now because this is one end, that is another end, so next is maximum number of carbon. So to have maximum number of carbon, we'll go like this. So main chain selected. After reaching one end, we will retrace our path so that main chain is selected. This the enclosure that you will get will be your main chain selected. Now numbering, functional group does not exist, multiple bonds, yes sir. So this, if I'll start from here, 1 will get a multiple bond. If I start from there, 1 will again get a multiple bond. So again, multiple bonds are tie. Then lowest location rule. So 1 2 3 4 5 6 and 7, the white one. What about the other one? 1 2 3 4 5 6 and 7. Now sir, multiple bonds are tie. Let us go to the branches. What about the branches? This is a branch at 4th carbon. What carbon branch it is, sir? 1 2 3. So it's a propyl starting with a P. It's a methyl starting with an M. It's also a methyl starting with an M. So what about the numbering? From left to right, I have branch at 3. I have branch at 4. And I have a branch at 5. From that side also I have a branch at 3, 4 and 5. So lowest location rule is tie, that side also, this side also. Now what will be the tiebreaker? It will be rule of alphabetization. But alphabetization, first I'll be applying for the multiple bonds because this multiple bond is 1 2. So multiple bond is ene. That multiple bond is ine. So some people say this, that double bond is given more preference than triple bond. It's just rule of alphabetization, because if now lowest location has tied, then I have gone to rule of alphabetization. So while applying that alphabetization also, first I'll apply that alphabetization for the multiple bonds. So because ene and multiple bond are preferred than branches, so ene is starting with an E, ine is starting with an Y, therefore E will be preferred first. Now because E is preferred first, so this white numbering is right and that orange is anyway wrong. So let us now name it. First, column 1 is for branches. So looking at the white branches, P, M and M. So what will be written first? M. So M is at 3rd position and 5th position. So 3, 5 dimethyl, 3, 5 dimethyl, yes. Then sir, 4 propyl, then 4 propyl. Then how many carbon in the main chain? 7 carbon. So hept. Both options are same. These two are definitely wrong. Then what about ene, sir? Double bond is there between 1 and 2. So 1 ene and 6 ine. So 1 ene and 6 ine. The option D is right, B is wrong. Now ene is ene, ine is yne, sir, but here E is not written because when you will pronounce it by phonetically speaking, you just tell me it's enine. So how will you pronounce it? Enine. So after, if Y is here or any vowel would be here, then vowel before Y and other vowels are emitted. So this E is not written because while speaking it phonetically, the vowels are omitted if vowel or Y is coming after that. So because it's a Y, so I have not written this E. Moving ahead. Now for cyclic compounds, now generally JEE asks it. For cyclic compound, the case is anyway you get cyclic compounds. I mean, the straight chain compounds we receive in nature also are generally more in number. So for cyclic compounds, what we do is whatever the rule apply that, but apply that only till maximum number of carbon atom. For main chain selection, what is the rule we have? First we go to functional group, then we go to multiple bonds, and then we go to maximum number of carbon atom. If till maximum number of carbon atom the rule has tied, then we give more preference to the multiple bond. Why? Because remember, in English grammar, whenever you get confused about using a preposition, your English teachers must have told you whatever is when you hear the name, when you hear the sentence, whatever where you hear, if that feels good, then that is right. Similarly, when cyclic structures are present, generally we prefer to take that cyclic structure as main chain, because the name that we get after selecting that cyclic chain as main chain is generally good to hear. So, sir, we do not feel like having goodness in speaking any organic compounds name, because you have not seen such many organic compounds. So I'm giving a rule. The rule says when you have a cyclic chain, the main chain selection rule is applied till maximum number of carbon atom. Till maximum number of carbon atom, if you are feeling that straight chain is your main chain, then select that chain. If not, and if both are getting tied, then you have to preferably select the cyclic chain as your main chain. As in, giving you an example. For example, this example. Now, selection of main chain, functional group does not exist, multiple bond does not exist. So maximum number of carbon in cycle is 3. Maximum number of carbon on straight chain is also 3. So maximum number of carbon has tied. Now we will not go to any other, that is maximum number branches, lowest locus. Do not apply that. Just select this cyclic chain as your main chain, because when you do that, the name sounds good. So what sounds good is right. So this becomes our main chain, and that becomes our branch. So if this is my main chain, so how to number it? This 1 2 3. Now this is our main chain and that is a branch. But sir, the main chain is connected with this carbon, so this carbon is the branch, the carbon of the branch, which is making this branch exist in nature. So for numbering of a branch, always give position number 1 to the carbon which is directly attached with the main chain. So this becomes your first carbon, let's say, because I am numbering the branch, so this is 1 dash. And obviously, if I'll move upside also or downside also, I have to move at least on one side. So let's say this is not there, so I'll be moving upside, so it will be 2 dash. So if this would have been just these 2 carbons, so it will be simply ethyl. But sir, now this branch has also a branch. So when a branch contains a branch, it is called a complex branch. And how to name a complex branch? I have already done it for you. First, I have numbered this complex branch. Numbering of complex branch always starts with that carbon which is directly attached with the main chain. So this becomes first carbon of the branch, followed by whatever number of carbon it has, because it has 2 continuous carbons, so 2 dash. So how to name this complex branch? The name of a complex branch is written in a parenthesis, a bracket. Now first, if it would have been just simply this, it will be ethyl. But this ethyl branch has one more branch, which is methyl connected with what carbon? With the first carbon. So what we write is 1 dash methyl, naming the branch of a branch first, and then what is this branch? This branch is ethyl. So name of this complex branch will be 1 dash methyl ethyl. Now, because I have written this complex branch in a parenthesis, so sometimes even question can do this with you, that because I have introduced that complex branch in a parenthesis, so its numbering some people can also write as 1 2. Sir, but how will we determine this is 1 2 of the branch and not of the main chain? Because that 1 2 is written in parenthesis, and sometimes that numbering of the branch, of the complex branch, is done as 1 dash 2 dash. in order to specify that this numbering is not numbering of main chain. This numbering is numbering of complex branch. So you can do 1, 2 also. You can do 1 dash, 2 dash also. So preferably I have done 1 dash. So this is 1 dash methyl ethyl branch done. So its name is done. So this is a branch for this main chain. So column 1 finished. Column 2, yes sir, main chain is cyclic. So it will be cyclo. Column 3, main chain is 6 carbon chain, so it is prop. Column 4, because it is saturated, so it is ane. So name will be methyl ethyl cyclopropane. Sir, why you have not spoken 1 dash? Because 1 can also be written. If nothing is written, we will preferably assume it to be 1. So it can be either written as 1 dash methyl ethyl cyclopropane or simply methyl ethyl cyclopropane, or if it is a parenthesis, some people can also write it as 1 methyl ethyl cyclopropane, because this one is inside the parenthesis. So this numbering is definitely for the branch. Now, giving you some more example of the complex branches, because some students feel not comfortable, so I'm making you comfortable with few examples. Now let us say this free valency is making this complex branch attached to a main chain. Now how to name this complex branch? Sir, if this would not have been there, then this is 1, 2. I'm not doing 1 dash, 2 dash now. So this is 2 carbon chain, 2 carbon branch, so it is ethyl. So this becomes 1 methyl ethyl, already done. What about this one? Sir, branch is having 2 carbon, but position 1 is having 2 branches. So it will become 1, 1 dimethyl, and the branch itself is a 2 carbon branch. So ethyl. Now what about this one? Sir, if this is connected with the main chain, then this is the carbon to which the branch is getting started, so it will be first carbon for you. Now this cannot be 2, because that way the branch will be of having larger number of carbons, so it will be a 3 carbon branch, but this 3 carbon branch is having one more branch, that is methyl at first carbon. So its name will be 1 methyl propyl, because the branch is a 3 carbon branch. Again this one, sir, this is the main chain. Now we know, sir, this is 1, 2, 3, 4, 3, 4. So wherever you can go, it is this the same. So this is a 4 carbon branch with another branch of ethyl on the second carbon of the branch. So name becomes 2 ethyl, first the branch of the branch, and then the name of the branch, which is butyl. So this is how you name a complex branch. The last one, sir, first carbon, because directly attached to main chain. So 2 and 3. So what about the branches? So methyl at second position. So 2, 2 dimethyl, and the branch itself is a 3 carbon branch. So it becomes propyl. I hope we are making sense over here, and we are in sync with each other. Now moving forward, after these IUPAC names, now many a times your whole organic chemistry, the question is framed using the general name of the compounds, because our name also, we have a name given by our parents that is written in the school, but at home we have a pet name. At maybe some friends of ours call us by some different name. So we have some systematic name also, and we have some general name also. And general name has got no rules. Even a 6 feet tall guy can be called at his home Chotu. Even a Chotu sa guy can be called as Raja. So general name has got no rules. So general names you should also know, because industrial importance of organic compounds give the right to that industry people that I will call that thing this only, and the name becomes famous. So general name of organic compounds are also famous, and you should know some general naming of alkyl groups. Now the first one being the normal group. Now because we already know the degree of carbon, so normal group is generally when the free valency is obtained by a 1 degree or a primary carbon, known as the normal group. For example, if question is saying that you have to make a reaction of N-propyl chloride, So this is a general name. You have to draw its structure. So what is N? N is a 1 degree. Prop as in you have to use 3 carbon. So let's say this is 3 carbon. This can be also 1 degree carbon. This can be also 1 degree carbon. You can use any one. Let's say this one. And to this 1 degree carbon, I am attaching the functional group called chlorine because it's written chloride. So this becomes N-propyl chloride. One more example. Let's say someone is asking you N-pentyl alcohol. Now, because we are class 10th passed, so I presume that you know alcohol is OH group. I've told you that also. So pentyl as in 5 carbon, 5 straight carbons. Because normal group is generally used for straight chain. So this can also have that branch, that can also have that branch. So because let's say this one, so to this 1 degree carbon, I am attaching OH. So this becomes your 1, 2, 3, 4, 5. This becomes your N-pentyl alcohol. It's we can definitely write its IUPAC name, but this is how the general name is written. Moving ahead. What about the secondary group? For example, by the name also, secondary is a 2 degree carbon. So for example, somebody is asking you that you have to draw sec-butyl bromide. So how to draw it? So first look at the alk word, bute as in 4 carbons. So does straight chain of a 4 carbon has 2 degree? Yes, sir. This one also and this one also. If I have a free valency over here also, over there also, name will be same, IUPAC name will be same, because if I'm having that free valency over here, it will be 1, 2. If I'll have that free valency over here, it will be 1, 2. So even if I'm using a general name, there should only be possibility of drawing one structure. If more than one structure are possible, then that general name is not applicable. So and secondary is a 2 degree carbon. So because it's a 2 degree carbon, then definitely we are going in the right direction. And what about the functional group? Bromine. So actually 2-bromobutane can also be generally named as sec-butyl bromide. Coming to the tertiary group, that is 3 degree group. So for example, tert, butyl, amine. Now, I have to create a tertiary carbon using how many carbons? Bute, 4 carbons. So, sir, if this carbon has to become a 3 degree carbon, then definitely minimum it needs 3 branches. I mean 3 carbons minimum. And after getting a free valency, this carbon can be termed as a tertiary carbon. So, how many carbons in total I am requiring? 4. Now, whenever a general name is using an alk, that alk is the total number of carbons, not the main chain carbons. So this becomes your tertiary butyl group. If I hold a pen over here, it will be generally named as tertiary butyl pen. If your master is hanging from this free valency, then this will be termed as tertiary butyl master. If a functional group nitrogen, so because to satisfy the valency, I'm writing an H2. So this will be termed as tertiary butylamine. If it is OH, tertiary butyl alcohol. So this is how you write a tertiary group general name and the structure. Moving ahead. Now, very, very, very famous iso group. Iso is also a general name. For example, you have to draw isopropyl alcohol. Now, what is an iso group? Iso group is a name of a picture, of a photo. What photo? Remember, iterate this with me. First carbon, second carbon must have a methyl branch and its free valency. This picture, this photo is termed as iso's picture. This photo is iso photo. Now, again, what is the photo of an iso group? Whenever iso term comes, first carbon, second carbon, a methyl branch and its free valency. So this picture becomes iso picture. Now, this picture is constituted by how many carbons? 3 carbons. So it will be isopropyl. Now, to this functional group, if I am attaching an OH, so this will be termed as isopropyl alcohol. Although its general name will be, this will be main chain. Its IUPAC name will be, this will be main chain. And 1, 2, 3. IUPAC we can definitely write, but you should know how to make the structure using the general name. Now, one more example. Okay, I'm attaching hydrogens also over here. So this is CH3 for tetravalency and this is H. That is, I guess, more than clear. Now, one more example. Now, somebody is asking you to draw, let's say, isopentyl amine. So how to draw this isopentyl? Sir, isophoto you already told us. What is the isophoto? Let us draw with another pen. So first carbon, second carbon and a methyl branch. This photo has to be there. So this is iso. But how many carbons you have used to make this photo? 3. But how many carbons you need in total? Because general name, whatever root word you have is the total carbon given. So this is pent. So but this photo I need because this is iso. But because I have to use 5 carbons, so I'll attach those remaining carbons like this. So adding 2 carbon, okay, I'm using different color because iso photo requires this much. First carbon, second carbon and a branch. But because I need 5 carbons, so 2 carbons I'm adding here, and after that I'll be adding whatever required functional group, which is amine in this case. So this becomes the general name and the picture of isopentylamine. Moving ahead. What is a neo group? Tertiary carbon, we know. For example, neopentyl bromide. Now this is a general name. Let us know how to draw its picture. What is a neo group? Carbon next to a tertiary carbon. So tertiary carbon is what? Sir, this carbon attached with 3 different carbons. So this becomes a tertiary carbon. So the group, the carbon just next to a tertiary carbon, if this has got a free valency, then this picture is the picture of a neo group. Again, the carbon next to the tertiary carbon is generally termed as neo group. So in order to form this neo group, how many carbons we have used? Sir, 5 carbons. So it is neopentyl group. If I am hanging with this free valency, I will be termed as neopentyl master. If there is a bromine, so it will be termed as neopentyl bromide. Moving ahead. What is a vinylic group? Carbon next to a 3-degree carbon is a neo group. Similarly, a double bonded carbon, if double bonded carbon has a free valency, if double bonded carbon has a free valency and whatever functional groups are attached to it, for example, I'm asking you to draw vinylic alcohol. So what is a vinylic group? The free valency of a double bonded carbon is generally termed as vinylic group. So if that vinylic group is attached to OH, this is a vinylic alcohol. If I will be hanging with that free valency, I will be termed as vinylic master. If I'm attaching this fan, it will be vinylic fan. So this is the general picture of a vinylic group. Now, coming to the allylic group. So the carbon next to a double bonded carbon. So double bonded carbon having a free valency is a vinylic group. But the carbon next to a double bonded carbon having a free valency, this group is generally termed as allylic group. So if I'm required to draw an allylic, let's say chloride. So what will be an allylic chloride? So carbon next to a double bonded carbon is called the allylic group. So if chlorine is attached, so this picture is the structure of an allylic chloride. Similarly, allylic alcohol, allylic amine, allylic whatever. Now, phenylic and benzylic group, they are examples of these vinylic and phenylic group. Now, first, phenylic group. So by the name only we can see phenyl as in benzene ring. So if this benzene ring is having a free valency, this group is generally called a phenylic group. So if I have to draw a phenylic amine, So phenylic amine is phenylic amine attached with an NH2. But this phenylic group is also an example of vinylic group. Why? Because this is a free valency of a double bonded carbon. So vinylic group is also a type of, so phenylic group is also a type of vinylic group. And one person can have more than 2 general names, more than 3 general names. My school friends are calling me by other name. My cricket playing friends are calling me by some other name. My siblings are calling me by some other name. So I can have many general names, obviously, but I'll be having a systematic name. So IUPAC name everybody has, but general name you cannot restrict that this guy can have only one general name. So this is also a vinylic group, and this is vinylic group is also this is also a phenylic group. Phenylic group is also an example of a vinylic group. Coming to the benzylic group now. For example, a question is asking you to draw benzylic alcohol. So how will you draw this? Carbon next to a double bonded carbon, remember? Carbon next to a double bonded carbon. Now this is a double bonded carbon. The carbon next to this double bonded carbon, let's say this one, its free valency is called benzylic group. But sir, this is also an example of allylic group. So yes, benzylic group is an example of allylic group. And what is benzylic group? The carbon next to a double bonded carbon is an allylic group. And what is benzylic group? When that double bonded carbon is of benzene ring. So carbon next to benzene ring, its free valency is called benzylic group. And if to that group, if I'm attaching this OH, so this becomes the picture of a benzylic alcohol, because this is the carbon has to have tetravalency. So this will be 1 degree benzylic alcohol. If this H is some R, it will be 2 degree benzylic alcohol. If these both the H are some different alkyl groups, it will be 3 degree benzylic alcohol. So for benzylic also, benzylic alcohols also, you will further be having degrees. Now, I hope these classifications are clear to you. Now, why telling you these? Because these are all, I've summed up everything for you. These all are basic JEE mains question to you. Now, moving forward, some NCERT basics more regarding naming. Some general naming of alcohols, because whenever benzene ring contains some functional group, those compounds are called, we already know their general name, they are called benzenoids. And for benzenoids, they are so extensively used in industry that their general name are so very famous that even IUPAC has to admit their general name to be the IUPAC name. For example, benzene having an OH, the very famous benzene having an OH is generally known as phenol. But the name phenol is so famous that for IUPAC, that general name is accepted by International Union of Pure and Applied Chemistry. So for organic compounds having benzene ring, their general names are very, very important, loved by JEE. Moving ahead, some general names. Benzene with an OH, we definitely know its phenol is a general name, but this is so famous that this phenol is even regarded as its IUPAC name. So for column number 2, 3, 4, that is cyclo, then hex, then ene at 1, 3, 5 position. We do not do this. And column number 5 for OH alcohol. Instead of all these columns, what we write is phenol. So phenol is an IUPAC. Phenol becomes and regarded as an IUPAC name. Even when question comes in JEE and they are asking you its IUPAC name, you can even tick phenol because they will not be giving you any other option. So this is phenol. Now some more general name. If this phenol is substituted with methyl group, then this is called cresol. And again, when we talk of benzene ring, 1, 2 position is the ortho position, the general name. So it becomes orthocresol. Its IUPAC name will be 2-methyl phenol, but also termed as generally ortho position. And benzene having OH and CH3 is generally termed as cresol. So ortho, meta and para. What is meta position? 1, 3. What is para position? 1, 4. General name, super important. Now, If a benzene is containing two OH at ortho positions, ortho, meta, para, but one more general name is industrially famous for them. Ortho, this is benzene 1,2 diol, but this ortho position of OH is also famously termed as catechol. Again, the meta version is known as resorcinol and the para version is known as quinol, and this is not very famous. Quinol is very famous, but it is also known as hydroquinone. But obviously quinol is famous for the para name. But this is all NCERT fact, so I've given you these facts also. Now, NCERT in alkyl halides also, a very famous general name for dihalides also exist. What are dihalides? Sir, by the name we can also say a compound having two halogens. Now these dihalides are also generally categorized as geminal dihalide or gem dihalide simply, and vicinal dihalide or vis dihalide simply. Vicinal, by the name also it is clear, vicinal, vicinity, as in both the free valencies are at adjacent carbon, adjacent as in carbon next to each other. So if the dihalogens are present next to each other at adjacent position, this becomes a vicinal dihalide. And if both the dihalides are present at the same carbon, it is termed as a geminal or gem dihalide. Now, again, their naming, general name is also very famous. Now, a very famous example from NCERT. Now, these two carbons, although if you write its IUPAC name, what it will be? Sir, 1,2 dichloroethane. What about this? Sir, 1,1 dichloroethane, but they are also generally named as ethylene dichloride or simply ethylene chloride, because that is a general name for dihalides. And this is for vicinal one. And for geminal one, you get an extra ID. That is ethylene. This is also ethylene, but not only ethylene, ethylene is in between, and ID is also coming. So how you will pronounce it? It is ethylidene. It is ethylidene dichloride or ethylidene chloride. Now, many of my students miss it. This ID is, so this is ethylene, this is ethylidene. So what is the difference? This ID is ETH. I mean, I'm giving you a mnemonic to remember this. ID is ETH. ETH is used when you get a gem dihalide. So make a story. If you're roaming around in a place, you're moving on a road, and you on the roadside you find a gem, a diamond lying. You find that gem, you find that diamond. That diamond makes you rich. So ETH ho gayi. So I mean, it's just a story, because many of my students used to forget this. So what mnemonic one of my student gave me, sir, Eid ho gayi, sir. When I find a gem, I'm happy, I'm grateful, Eid ho gayi. So ID comes when you find gem, or else simply it is ethylidene chloride. Moving ahead. Now, why discussing these names? Benzene 1,2 diol. Recently we have done. So it is catechol. Now, directly moving to the functional groups. So functional groups are those structural units which, when added to an organic compound, decides its property and reactivity. So IUPAC has served us with a priority list, in which the functional group which is coming first is the most senior. And for functional groups, what we will be using their secondary suffix, that is column 5. But if a question, sir, is supplied to us, because JEE asks such questions to you, that it is having more than one functional groups, then sir, which functional group will be regarded as a functional group? The senior one, because it is more reactive. So the senior functional groups will be regarded as a functional group, and for that functional group we will be writing its secondary suffix in the column 5. While for junior functional group, we will be just treating as a branch, and the name of the branch is written in first column. So we have to learn the prefixes also for these functional groups. Now, the very senior functional group for us, for JEE Mains and JEE Advanced, I mean to our level, the most senior functional group which we should know is the carboxylic acid with the formula COOH. Now, because we have already seen in the selection of main chain criteria that the carbon which is connected with the functional group has to be taken in the main chain. So this RC becomes your main chain, and this carbon you will be naming in the word root as in column 3. So secondary suffix, that is fifth column, you just have to use for this to mention this OOH. So the suffix of OOH is oic acid. The second seniority wise functional group is the sulfonic acid group with the formula SO3H. So this R becomes your main chain, and the suffix for SO3H is nothing, the name only, sulfonic acid. The third functional group being the acid anhydride. Suppose I have one carboxylic acid, and if two carboxylic acid are anyhow dehydrated, then they have to release water molecule. Then this, let's say this RCOOH, let's say it has lost its OH, and the other molecule of carboxylic acid must lose its H. So water will be getting dehydrated. So let's say this is another molecule RCOO. This green one, H is gone. This pink one, OH is gone. So water removed. If you add them, you will find such a structural unit, and it is called acid anhydride. Third functional group is ester. If you just look at carboxylic acid, you, instead of this H, if you write another alkyl group, so it becomes RCOOR-. So here also this will be taken in the main chain. So we have to use a name in order to specify whom this double bond O and this O attached with another carbon chain. So this suffix is O8. Moving forward, the fifth senior functional group, I have written that side, is the acid halide. The most famous acid halide you find in your examination is chlorine. So instead of this halogen, fluorine, chlorine, bromine, iodine, anything can come. But if it is chlorine, the suffix is oil chloride. Remember, this oil chloride is used just to mention this double bonded O and X, because carbon, I'm again repeating, the rule that we have is we have to select that carbon in the main chain which is directly attached to first priority is functional group, and these are functional groups. So this carbon of all these functional groups will be named under the word root, that is column 3. So what suffixes generally used is that carbon is named in the word root, and you just have to know the suffix of the other elements. So for double bonded O and an X, the suffix is oil halide. If it is chlorine, it is oil chloride or oil bromide or oil iodide. Now the fifth functional group is the other acid derivative. Instead of OH, what we are having, a nitrogen. Remember, nitrogen has 5 electrons in its valence shell. So in order to complete octet, it forms 3 bonds. Sir, 1 bond is already there with carbon. So this becomes your main chain. And obviously, it can also have some alkyl substitutes, which will be named as a branch. And the name of those branches will be coming in column 1. So what will be the suffix used for acid amide? Just the word amide. But amide is naming whom? This double bonded O and the nitrogen. Now, next functional group is acid are cyanides. What are cyanides? When this carbon chain is attached with C triple bond N. But again, this C you will be naming in your word root. So you need suffix for triple bonded N. Triple bonded N has a suffix of nitrile. Now, the other one, isocyanide, sir. Here this carbon cannot even come to the main chain, because if R is the main chain, then it is connected directly with nitrogen. So NC becomes your functional group, which is called isocyanide, the 8th senior most functional group. And here the suffix used is isonitrile. So isonitrile is used for NC. Now next is carbonyl groups. What is a carbonyl group? C double bond O group. So if I'm C double bond O group, generally I'm termed as a carbonyl group. Now, if this carbonyl group, obviously if I'm C double bond O, I'll be having 2 valencies. If both of my valencies are connected with some carbon chain, then I'm a ketone, and the suffix used for this double bond O will be ONE, one. But if any one side or maybe both, if any one side or maybe both is connected with an hydrogen, then this particular carbonyl group is termed as an aldehyde. And in this case, the suffix used for this double bond O will be al, because aldehyde has a aldehyde has a suffix al, and ketone has a suffix of one, on. Moving ahead, the next 11, 12th and 13th, what are these functional groups? If the carbon chain is connected with an OH, this OH we definitely know its suffix is all. If it is SH, the suffix is thiol, because it's a thiol alcohol, and thiol both relatively have same properties because oxygen and sulfur are all group 16 elements. So chemical properties will be same, although the extent of reactivity will be different. Now, next and the last one is amine. What is amine? Sir, nitrogen. Nitrogen definitely can have 3 bonds. So it can be, for example, this will be 1 degree amine if these 2 bonds are hydrogen. If it can be 2 degree, it can even be 3 degree, but those carbon chain will be treated as a branch and written in column 1. So what will be the suffix of this nitrogen? For this nitrogen, the suffix is simply amine. So these are all functional groups that you will be knowing. Sir, why you are again and again telling this, that this carbon is going to word root, this carbon is going to word root? Because there are few cases, for example, like when a functional group is directly connected to a cyclic chain. Now remember, cyclic carbons have different reactivity and straight chain carbons have different reactivity. That's why we have chosen that cyclic chain is the main chain or straight chain is the main chain. Generally, cyclic chain, because of the strain that they get, they are generally more reactive. 6-membered ring is free from any type of angle strain. So generally 6-membered, that's why organic compound generally tries to form a 6-membered ring or maybe 7-membered ring. So 6-membered ring are stable, but if the ring size is lesser, then it will have some strain because these bond angles will be closer. So whenever cyclic structures get these functional groups, for example, the cyclopentane, let's say, is having this COOH functional group. Now, what is our rule? Functional group that is attached to the carbon atom has to be selected in the main chain. So this is the functional group and this is connected to this carbon of the ring. And if this carbon, if a ring is selected as a main chain, then I cannot select this carbon in my main chain. So I need one more name of a functional group where I can name even this carbon, considering it as a unit of the functional group, because generally the carbon that is attached with the functional group goes with the main chain. But if this main chain is itself cyclic, then I cannot count this carbon in my main chain. So for such cases, we need one more secondary suffix that should include a name including this carbon. That's why this list I'm giving you, that other secondary suffix of functional groups that contain these types of carbon. For example, carboxylic acid. Now this R will be just treated as the main chain and I will be needing a suffix for complete COOH, which is carboxylic acid. Similarly, for acid anhydride, the name will be carboxylic anhydride. For ester, it will not be O8, it will be carboxylate. For acid chloride, it will not be oil chloride, it will be carbonyl chloride. For acid amide, it won't just be amide, it will be carboxamide. For cyanides, it will be carbonitrile, because now that triple bonded C is not taken in the main chain, so it will be carbonitrile. And for aldehyde, it will be carbaldehyde, because all CHO will be taken. Here, this whole CHO will be taken as a functional group and its suffix will be carbaldehyde. So again, summing it up for you, for example, for this compound, the name will be, this is our main chain, so cyclopentane, functional group is connected to this carbon and I'm marking this carbon as 1, so it will be 1, and this, it will not be oic acid, it will be carboxylic acid. Similarly, this is the one first case when other suffixes used. So when you use the other suffix of the functional groups with the suffix with the carbon, when they are directly attached with the ring, point number one. There is one more case when the other suffix as in the suffix with carbon is used. Like for example, let's say this is the structure. Now, what rule we have? We have to take that carbon which contains functional group. So if you take this carbon, let's say 1, 2, 3, then you can either go upside or you'll say, sir, that is not the main chain, so I'll go downside. But in that case, you out of these 3 functional groups, you have selected 2 and 1 you have left. So when you have equal functional groups and when you are forced to leave one functional group, then in such cases also IUPAC asks you that what if you consider the whole CHO as the functional group? So this functional group 1, functional group 2, functional group 3. What does the niyam tells you? That functional group is connected to that carbon and that carbon has to be taken in the main chain. So taken in the main chain. And you have used all the functional groups considering them to be same priority. So this becomes a 3 carbon chain and all functional groups are CHO. So you will not use, because it's an aldehyde, but you cannot use ul, because ul is a suffix used for just double bondo. With the C, what suffix you use? Carbaldehyde. So its name will be prop ane 1, 2, 3 tri carb aldehyde. Now you will find so many questions in application form of these other suffixes, although they are in comparison to the suffix which we have read before, that is these suffixes, they are more famous because the carbon contained by the functional group is always taken in the main chain with the main chain. When it cannot be taken in the main chain, when it is directly connected to a cyclic chain, or when more than 2 of these functional groups are present. So if you have to leave one, then leave all, take all of them as same prior and take the other suffix so that the rule is not violated. So in these 2 cases, we'll use the other suffixes, which are these. Moving ahead. Now, sir, you said that when 2 functional groups are present, then we will write suffix for the senior functional group. Seniority table now we know. But what about the junior functional groups? We have to write their prefixes. So learning about the prefixes of these functional groups as well. Although for carboxylic acid, because it's the senior functional group, and so if it is the senior most functional group, why you will be needing its prefix? But before 2004, like for example, if it was CWH, because this convention, what grammar is right, what feels good when you hear it. So these names, these amendments by IUPAC was done around 2004. Before 2004, sir, then if the suffix of, if let's say this is CWH, you should know the prefix of CWH, because 2 CWH you are taking in the main chain, 1 CWH you are leaving, so that becomes your branch. So for such cases, initially the prefix of carboxylic acid, and for other functional groups definitely you will be needing their prefixes. So learning the prefixes of functional groups. So what will be the prefix of CWH? Now remember, when we are taking the functional groups as branches, you have to consider their carbon also. So here the prefixes that I am giving you will be containing the carbon also. So carboxy is the prefix of CWH. For SO3H, prefixes sulfo. Thanks to the mother nature, when acid anhydride is supplied to you by mother nature, so there is no such example where prefix, I mean when anhydride is taken, is losing a battle from another functional group. So there is still no use of a prefix of anhydride, because whenever anhydride is there, it is always the senior most functional group, so its prefix is generally not required. So IUPAC do not even mention its prefix. Now what about ester? So if I'm saying I need a prefix for this whole thing. So this COOH, COO prefix will be alkoxy-carbonyl. Remember, this OR dash is alkoxy, the ether group. Alkoxy, alk will be decided by this R dash. Let's say this is CH3, so it will be methoxy. If it is C2H5, so it will be ethoxy. So alkoxy and CO, I've told you, CO is a carbonyl group. So its prefix is alkoxy-carbonyl. Now, what about acid chloride? COO, Cl. So I need prefix of this. So prefix of this will be chlorocarbonyl. Now, chlorocarbonyl or bromocarbonyl or iodocarbonyl. So halocarbonyl is the prefix of acid halides. Now, what about acidamide? So acidamide has an RCOONH2. Now, this R is the main chain, must be containing some senior functional group. That's why I have to give a prefix of this COONH2. So prefix of COONH2 is carbamoyl. It is carbamoyl. It is carbamoyl. Say an iterate is 3-4 times. Do it for 2-3 days. The priority also and the name also will come in sync with you. But you have to revise these things if you are learning it for the first time. Now, what about cyano? So this suffix is for CN. So if CN is a junior functional group, the prefix for CN will be cyano. The prefix for NC will be isocyano. The prefix for aldehyde will be aldo or formyl. But remember, this prefix is for the complete CHO group, including the carbon. So it is aldo or formyl if it is a junior functional group. And for ketone, we just need to know, because this carbon chain will still be part of the main chain. So we need a prefix for just this double bond O. So the prefix for this double bond O will be either keto or oxo, a very famous and important slide for whole of your JEE exam. Now, what about OH? If OH is a junior functional group, then prefix for single bonded OH is hydroxy. Prefix for SH is mercapto. And prefix for the nitrogen, if it is a junior functional group, prefix for nitrogen is amino. If this amine is having a senior functional group, then prefix for this nitrogen is amino. Moving ahead. Now, just applying all these logics in the direct questions that is coming in JEE mains. So this first question, you have to tell me the correct IUPAC name of, okay, the structure is given and you have to tick, sir. Okay, how many functional groups we have? 2. One is cyanide, another one is NH2. Which is the senior functional group? So cyanide. So selection of main chain, functional group, this is the functional group. So this becomes your main chain, and maximum carbon we are considering, so that carbon has gone to the main chain. Numbering the main chain, minimum number goes to functional group. So this is 1, 2, 3, 4. So cyanide, because whenever a carbon containing functional group is there and it's carbon you are taking in the main chain, so obviously the chain will be starting from that carbon only. So such functional groups are also called terminal functional groups. So the C containing that triple bonded N. Now this becomes a branch. How do you write the name? So column 1 for the branches, I have one branch. This branch is nitrogen. So hydrogen we do not name. Nitrogen, why these hydrogens are used to satisfy valency. So what do you have to name? Just this nitrogen. Prefix for this nitrogen is amino. Connected with what carbon? Third carbon. So 3 amino. So 3 amino. So these options are wrong. 3 amino, 3 amino. Now what is the size of the main chain? So 4 carbon. So bute. So bute, it's a saturated chain. So ane. So no, that is triple bonded carbon, but it is forming a triple bonded carbon not with carbon. So for carbon chain, it is a saturated system. So bute, then a ane, and the triple bonded N suffix is nitrile. So option C is right. Moving ahead. Now these are some basic questions which JEE asks number of times. Moving ahead. Correct IUPAC name of this, let us identify. Sir, NO2 although functional group but treated as a branch, so go away. So this COO, sir, they are carbonyl group, so it will be aldehyde or ketone, which is senior aldehyde. So C double bond O connected with an H is an aldehyde. So here functional group is there and we will take it in the main chain. So this will become our carbon number 1 only. So this is also a terminal functional group, aldehydes. So this becomes 1, 2, 3, 4, 5, 6. and obviously this will be the 7th carbon because I have to move from one end till the another end. So how many carbons I have in my main chain? 7. What about the branches? This is one branch. Although this is a functional group, but now this ketone is treated as a branch because its daddy, its senior functional group, aldehyde, is present. Now, what about this? This will be a methyl branch. So, naming the compound, column 1 for branches. This is nitro with an N. This is methyl with an M. Let's say I'm writing oxo, so it will be O. If option is using keto, so it will be K. So, which is written first? Obviously, MNO. So M comes first. So 4 will be having methyl. So 4 methyl, yes. So this option gets eliminated. Now, after that, 6 nitro. 6 nitro, perfect. So I guess we got our answer. Now, oxo it has 3rd carbon. So 3 oxo, 7 carbon. So hept. Double bond is between 4, 5. So 4 ene and functional group is at position 1. So it will be 4 ene 1 ul. But remember, vowel coming after a vowel is omitted phonetically because you will term it as enul, not enial. So that e, that vowel gets eliminated, and 1 you either write or do not write. Option has not written. So option C becomes your right answer. Now this 2019 question, sir, again there are polyfunctional groups. Which is the senior functional group? Carboxylic acid. So our chain will be starting from this. So 1, 2, 3, 4. This can also be 5. That can also be 5. Just to, for the case of simplicity, we'll go horizontally. Circle the branches. 1, 2. Done. This is hydroxy starting with an H. This is methyl starting with an M. What will come first? M or H? M, N, O, P, A, B, C, D, F, G, H, I. Okay, H comes first. So hydroxy. So you are gone, you are gone, you are gone. By just doing ABCD, you know hydroxy is written first. So this is 3 hydroxy, perfect. 4 methyl, perfect. Pentane 1 oic acid. So this becomes my right answer. Moving ahead. So this is just ABCD now for us. Now this is a logic. I mean some question, some practical question which you should know. Some NCERT logics also loved by JEE. So mesitile oxide, although it is a general name, so first you should know what that compound is. So mesitile oxide is nothing but it's a ketone containing 5-member carbon. Now the first carbon after first, because it's a ketone, so I cannot put a carbonyl group at first carbon because then it becomes an aldehyde. This is a knowledge which I'm remembering, and you should also remember that mesitile oxide is a ketone. So in order to make it a ketone, first I have remembered it like this, that first carbon cannot have double bond because it will be an aldehyde, so it will be a ketone. Now it's an alpha beta unsaturated ketone. What is alpha beta? It's a general positioning name. Now the carbon next to functional group is generally represented as alpha carbon. So alpha beta, here there is no beta carbon. So let's say this is alpha carbon and this is beta carbon. So this becomes alpha beta unsaturated ketone. But this also has a methyl group in this particular carbon. So let us name this, sir. 1, 2, 3, 4, 5. So this will be a methyl group. So its name will be 4-methyl. Its name will be 4-methyl. Then 5 carbon chain is pent. Then 3, 4, so 3 ene and 2 one. So this is your answer. But obviously, in order to land up to such answers, you should remember some facts. So what is a mesitile oxide as per NCERT, as per carbonyl group logic? You should remember it's an alpha beta unsaturated ketone, and the ketone, the alkene, also has a methyl group attached to it. So the structure you should know by its general name, and then you can definitely write its IUPAC name. Now, as I've told you, we have seen in JEE question also that general names for compounds are hugely important. So for aromatic compounds, I have given you few general names. Just read them using this table and we will move forward. Now, moving to the isomerism involving organic compounds. So what are these isomers? Isomers are 2 or more compounds having same molecular formula. But what do they differ in? If they differ in their structure, then they are called structural isomers. Obviously, if they differ in their structure, then the names that we have discussed, their IUPAC names, those will also be different. And the other type of isomers are having same molecular formula and both same structural formula, but they have different what? They have different stereochemical formula. What is stereochemical formula? Like, I have a duplicate brother, a judwa bhai. So if I am having a mass of, let's say, 100 kg, that one also has a mass of 100 kg, both of us exactly looks the same, but in three-dimensional space I'm oriented like this always and he is oriented like this always. So orientation in three-dimensional space, if they are different and they are actually two different compounds, then those isomers are called stereoisomers or space isomers, which we will be discussing separately in depth, but after discussing structural isomers. So what are the types of structural isomers? Very easy. We'll be done. We'll be finishing them first. So there are 6 types of structural isomers: chain, position, ring chain, functional, metamers, and tautomers. Now, discussing about the first 4. What are chain isomers? As I've already told you, they have same molecular formula, but the structure will be different. How the structure will be different? They have different size of either main chain or side chain. Remember one thing: functional group, if the compound is containing any functional group, then the nature of functional group should also be same. So if the definition of chain isomer has to be true, then it definitely does not have to be a functional isomer. For example, now let's say these are the 2 compounds. Let us name them, because IUPAC name we have already recently done. So let us name them. Sir, this is simple. They are 5 carbon alkane. It is a 5 carbon alkane, so its name will be pentane. Sir, it's a 4 carbon straight chain alkane but with a methyl branch, so its name will be, numbering we'll be doing from this side because this is giving minimum number to the branch. So this becomes 2 methyl butane and this becomes pentane. So they both are what type of isomers? They both are chain isomers, as in same molecular formula. Obviously their degree of unsaturation, if molecular formula is same, so their du will also be same. All isomers will definitely have same du because they have same molecular formula. So because they have same molecular formula but different structural formula, and why the structure is different? Because the size of main chain is different, so they are termed as chain isomers. Now coming to the positional isomer. Now if I am not chain isomer, then only I can be called a positional isomer. So positional isomers have same molecular formula, but the size of main chain and side chain should also be same, else I will be termed as a chain isomer. And what is different? They should have a difference in the position. By the name also you can say position of what? Functional group, multiple bond or branches. Again, they should also not have to be a functional isomer, as in nature of functional group must also be same. So when I can be termed as a chain or a positional isomer, when I am not a functional isomer, that means that definition is superseding us. And if I have to be a positional isomer, my main chain and side chain should be same. So chain is a dominating definition than position. So if I'm not functional, if I'm not chain, then only I will be termed as a chain isomer, as a position isomer. And what is a positional isomer? When I have different position of either functional group, multiple bonds or branches. For example, let's say this is a 4 carbon chain. Let us name it. This is 1, 2, 3, 4. So its name will be butane 1 all and its name will be butane 2 all, because main chain is same but position of functional group is different. So they both are positional isomers. Now, what about these two? Sir, it is similar. Functional group. Nana, do the IUPAC name first. Remember, the selection of main chain, it starts with that carbon from which functional group is attached. So this becomes 1, 2, 3, 4, 5. So this is actually pentane 1 oic acid. What about this? 1, 2, 3, 4. Sir, this is 2-methyl butane 1-oic acid. So here, even size of main chain is not same, so they are not positional. If main chain, side chain, everything is same, then look at the position of functional groups, multiple bond or branches. If it satisfies the definition of a chain isomer, then call it a chain isomer, not a positional isomer. Many students make this mistake. So I hope you got that. Now let us do some more examples. Like for example, these two, although these two. So whenever you need to identify what type of structural isomer it is, preferably just write its name, or even do not write its name, at least do the marking. So this will be 1, 2, 3, 4. So this is 2-methyl butanoic acid. This is also 1, 2, 3, 4. So this is also 2-methyl, though they are not even isomers, they are identical. Many a times JEE do this, they give the same molecule in showing in different forms. So these two are identical. What about these two? Sir, this is methyl methyl, so 2 methyl groups connected with a carbon, and the similar side, this is actually the condensed formula of the same species. 2 methyl group connected with CH, the same. So they both are identical. They are not even isomers. So they are identical. You should always remember these things. Now, okay, what about these two? How you will name this? Sir, this is cyclohexane, 6 carbon chain. This is 1-methyl cyclopentane. So size of main chain is not even same. So these two are option 3 are chain isomers. Now, what about this fourth option? Sir, this is 1, 2, 3. So this is 1, 1 dimethyl cyclopropane. What about this? This is 1, 2 dimethyl cyclopropane. So size of main chain, side chain, everything same. What is different? Position of branches. So these two becomes. Now identifying chain and position, I guess it's very easy, done and dusted. Moving ahead. Now, sir, what about ring chain isomers? They are also same. See, remember we have done DU, degree of unsaturation. Who has same DU? Let's say DU1. When 2 hydrogens are removed, who satisfies the removal of 2 hydrogen? A pi or a cycle. So alkene and cycloalkane, the name will be different, but one is straight chain and one is ring. So whenever I have same molecular formula, but one of my structure is a straight chain, one of my structure is a ring, then what type of structural isomer I am? I am preferably termed as a ring chain isomer. For example, now this is an alkene, molecular formula C4H8. That molecular formula is also C4H8. So alkene and cycloalkane they are what type of structural isomer? Ring chain isomer. Similarly, one more example. I mean, a class showing ring chain isomer will be a straight chain alkyne and cycloalkene. So these two, alkyne with DU2, cyclo DU1, alkene DU1, so total DU2. So alkyne and cycloalkene are also what type of isomers? They are also ring chain isomers. Now, moving ahead, functional isomers. Now, by the name only you can see they have same molecular formula, and why the structure is different? Because they have different nature of functional group. Some very famous and beautiful examples: alcohol and ether. Alcohol is ROH, ether is O, and both side carbon chain, so it is generally ROR. Alcohol and ether are always functional isomers because nature of functional group changes. Acid and esters, they are also functional isomers always. Cyanides and isocyanides, always functional isomers, obviously if they have same molecular formula. And similarly, 1 degree, 2 degree, 3 degree amines, aldehydes and ketones, they are also functional isomers because presence of alkyl group not only decides but dictates the nature of a functional group. We will be throwing more light and discussing it to a larger extent when we will be discussing electron displacement effect in GOC-2. So sir, these are all examples of functional isomers that we may get or we may see. No, you can definitely apply your common sense. Like, for example, this question. This is a carbon, this is a carbon, this is a carbon. So because this is a terminal carbon, so there'll be an H. So this functional group is aldehyde. Sir, this O is connected with carbon-carbon. Okay, that means this is an ether. But what type of ether? Cyclic ether. So although it's a untraditional example, but because you have common sense of IUPAC, then you can definitely say it's an aldehyde and it's a cyclic ether. And they both have different functional groups. So they are also examples of functional isomers. So the examples which I have given you initially in the previous slide, they are all traditional examples, but you may find another functional isomers examples as well. Now, moving forward, let us move to the next structural isomers, which is the metamers. So what are metamers? Two or more compounds having same molecular formula and same nature of functional group. If nature of functional group changes, I'm a functional isomer. So functional isomer is again a senior definition. So if both molecular formula and nature of functional group is same, and along with that you have a polyvalent functional group, which has more than two free valencies which are directly connected with a carbon chain, then whatever nature of alkyl group changes along those polyvalent functional group which are attached with carbon chain, if they changes, then all the possible structures are named as metamers. Let me give you an example of some polyvalent functional groups, like a carbonyl group, but definitely not aldehyde, but yes, ketone can change the number, the positioning, the arrangement of alkyl groups and can form metamers. Similarly, other functional groups that can form metamers are esters, ether, thioether, 2-degree amine, not 1-degree amine, because 1-degree amine is just containing this one alkyl group. So if arrangement of carbon in this alkyl group changes, there is no position of other free valency. So 1-degree amine can never form metamers, but 2-degree can form, 3-degree can form. Similarly, 1-degree amide cannot form, but if that amide is having an alkyl group, then this R arrangement can change with this main chain carbon arrangement. So the 2-degree amide can also form metamers. Obviously 3-degree can also form metamers. Anhydrides can also form metamers. Now this is not very traditional, but if amide undergoes dehydration with a carboxylic acid, so this O is replaced by NH and it is termed as imide. So they can also form metamers. The diazo group in both sides of nitrogen, the nature of alkyl group may change and can form to some metamers. Now, practicing a basic NCERT question, but JEE loves asking this type of question. What? JEE simply asks you with options that this is a molecular formula. What are the possible number of structural isomers? So how you will count them? I'm giving you a method so that you may not miss any structure. So you should apply this method of writing down all the structures using a tradition, a stepwise method, so that you may not skip any structure. Like for example, we are given a molecular formula of C4H11N and we are supposed to draw all the structural isomers and tell what are the possible structural isomers. Now, for doing such type of question, first calculate the DU, that is degree of unsaturation. So if I have 4 carbon, what is the number of hydrogen I need? So 2n plus 2, that is 10. Now, let's say because this compound is containing some functional group also, that is nitrogen. So obviously with nitrogen, what functional groups you will have? Amines. So if that amine will be connected with this carbon chain only, so remove one hydrogen, it will give you a free valency. So C4H9 and a free valency, it will be connected to nitrogen, and in order to satisfy the octet of nitrogen, I need 2 hydrogens. Sir, molecular formula satisfied. So tell me, what is its degree of unsaturation? 0, because there is no unsaturation in this particular molecular formula. So you do need not have to learn all the formulas of DU. It's just a common sense. Now we know it's a saturated compound. So how to draw its possible number of structures? Very easy. Whatever carbon you are supplied with, first you draw its direct straight chain. Now to this straight chain, what extra I have to add? NH2. Where this NH2 can go? Sir, it can go here also. Then its name will be butane 1 amine. So this is structure number 1. Let us say I have this structure only, but if instead of 1 I'm having an NH2 over here, so it will be butane 2 amine. So these are two different compounds. Sir, if I place this NH2 over here, then we'll do numbering from this side. Over here, then we'll do numbering over this side. So structures are already formed. So this is end of a straight chain carbon containing NH2. Moving forward, what about the next structure? Sir, this chain can also change. I mean, first you draw whatever the number of carbon you have, you draw in a normal sense. Now, subtract 1 carbon from that chain. How many carbons we had in the main chain? 4. Remove 1 carbon. Now this is that 1 carbon. Now where you can place it? Sir, here? No, because it will be 4 chain already done. Here? Already done, because then this will become a 4 chain carbon. So the only possible case is this. Now we have to play with this structure. So let us decorate this structure with NH2, because NH2 we have to add again. Now here, if you add NH2 any side, the name will be 2-methyl propane 1 amine. And one more possibility is attaching that NH2 over here. So it will give you the 4th structure. What will be its name, sir? 2-methyl propane 2 amine. Sir, after do you have any other possibility of forming this 1 degree amine? No, sir. Why? Because if you remove 1 more carbon, you will be ending up with 3, but then you will have 2 carbons in your pocket. So if you will place one carbon only, you will form a 3 carbon chain. So this is the only possibility of playing with these 4 carbons forming a 1 degree amine. But we can also form 2 degree amine. So these are all examples of 1 degree amine formed by molecular formula C4H11N. So after these 1 degree amine, let us work on 2 degree amine. So what is the possible, how can a structure form a 2 degree amine? So I need this NH. Minimum I need 2 carbons. Now we can, if these positions has to be fixed if I have to form a 2 degree amine. Now what else I have? Sir, 2 carbons are utilized. You are given 4 carbons, so you are having 2 carbons in your pocket. Okay, so this is the first carbon. Out of those 2, you just pick first carbon. Okay, this is the first carbon. I cannot attach it over here because I am planning to draw all the 2 degree amines possible. So I can even draw that carbon this side or that side. So either here or there, it will be the same. So I'm drawing that carbon to that side. Now, this is the structure to which now I have to do the permutation and combination. So let us select the structure. And let's say what possibilities which we may have. Now, how many carbons we are left with? Sir, 1 carbon. So let us think of the possibility of drawing that carbon. First position, definitely I can write over here. So this will give me structure number 5. What about this? So this position we have already drawn. So for next option is this. What is the other permutation? Sir, you can draw over here. Anything else? No. Now let us check whether they are different or not by naming them. It will also help us in doing example of some IUPAC. Now, sir, this is a functional group. Selection of main chain, functional group connected with this carbon also, that carbon, both are same. Maximum number of carbon is also same. So select any as your main chain. So let us take this as our main chain. So this is 1, this is 2. Now what about this? This will become a branch connected with nitrogen. So how do you name a 2 degree amine? This alkyl group is connected with nitrogen. So how do you name it? You name it as N-ethyl column 1, column 2 does not exist because main chain is not cyclic, column 3 becomes eth, column 4 becomes ane, and to carbon number 1 you are connected with a nitrogen, so 1 amine. Simple. Vowel cancelled. So this is N-ethyl ethane 1 amine. Now what about this one? Sir, this will be main chain 1, 2, 3. So this will be N-methyl propane 2 amine. What about this? So this is also 3 carbon chain, main chain. So this is also N-methyl propane 1 amine. That's it. So these all are the possible. These all are possible 2-degree amines. How many 2-degree amines we made? 3. These all are possible 1-degree amines. How many 1-degree amines we made? 4. Now, can we make some 3-degree amine also? Yes, definitely. So let us try that also. In order to have 3-degree amine, I minimum need 3 carbons. Sir, what about the other carbon? That is only the other one possibility we are left with. So if I have one more carbon in my molecular formula, so that can go this here also, here also, here also. Wherever it will go, it will form the same structure. So it will be the main chain. So its name will be N, N dimethyl, column 1 of the branch done. Column 2 does not exist because main chain is not cyclic. Column 3's main chain is of 2 carbons, so eth. It is saturated, so ane, and to first carbon there is attachment of functional group, so 1 amine. So this is the 8th structure is the only 3-degree amine possible. Now, after knowing that the possible number of structural isomers are 8, then let us designate the relationship between them. So among these 1-degree amines, first and this second are position isomers because size of main chain is same. Third and fourth are also position isomers among each other because size of main chain is same. Out of these 1, 2 and out of these 3, 4, if you will compete, then they are chain isomers because size of main chain is only different. So these are the relationship among these 1-degree amines. But when you talk of 2-degree amine, then all these 2-degree amines are metamers of each other. You will not go by the definition of chain and position isomers, because when definition of metamers is true, you just look at all 3 of them. They all are 2-degree amines, and what are changing? Nature of alkyl group along this bivalent. This is not a trivalent, this is a bivalent functional group. But because 1-degree amine is a monovalent functional group, so metamers for this is not defined. But for 2-degree amines, so all these 3 are metamers of each other. Similarly, for this 3-degree amine, do you find any metamer? I cannot have any 3-degree amine. So what can you say about this 2-degree? Any of this 3-degree, that 3-degree, any 3 of this 2-degree and this 1-degree, they all 1-degree, pick any one of them, 2-degree, pick any one of them, and to that 3-degree, they all are functional isomers of each other. So you should definitely know this priority. That is, first you will check whether you are ring chain or not. Then you should check for tautomers, that we'll be discussing. This is left. So then you will think of the functional isomer. Then you will go to metamers. If metamers definition is valid, we will not see the, so priority is this. So if somebody is functional isomer, you will not see meta, chain and position in them. If someone is having a relationship with the definition satisfying the definition of metamers, then you will not see to their chain and position relationships. So this is the priority that you should know. Now, why I'm explaining you all these? Because I'm covering a number of questions with just this knowledge, because this is just JEE Mains 2024 question, in which this is a molecular formula. It's saturated alkane because 7 2 14 plus 2 is 16. So this is a saturated alkane. Again, draw all the possible structures, and you were supposed to give the number of structural isomers possible, which is 9. So this is a homework question for you. Moving forward, now this is a JEE advanced question, so let us try that. And the question is also the same. You have to tell the number of structural isomers. What is the question actually telling you? Number of cyclic. Okay, question is specifying that you have to draw cyclic structures. So what are cyclic structure isomers possible? Okay. So molecular formula is C4H6. So for saturation, how much I need? 4 to ja 8 plus 2, 10. So I will 4 to ja 8 plus 2, 10. I would be needing 10 hydrogens for saturation. And how many hydrogens I have given with 6? So how many hydrogens I'm getting shorter of? 4. So du for this will be du for this will be 2, because 2 hydrogens create 1 du. Now this 2 du can be satisfied by what? Sir, it has to be a cycle, because question is telling you it has to be a cycle. So 2 du can be satisfied by 2 cycles if I have a 2 cyclic structure, or if I have a cycle and a pi bond. So let us draw this cycle and pi bond first. What all structures we can have? So for 4-membered cycle, this is a 4-member cycle. Now introduce a pi bond. How can you draw pi bond? Anywhere you'll find this name. What name? This one. So this is one possible structure number 1. Now can you reduce the cycle? Yes sir, we can make a 3 carbon cycle now, but you are supposed to use 4 carbons. So let's say this is the 4th carbon. How can you draw this 4 carbon? So draw anywhere, because here it will be same. Now but you also have to draw a pi bond, because du is 2. Cycle creates 2 hydrogen, satisfies 2 hydrogen deficiency, and again we need a pi bond. So to the pi bond, what are the positions, what are the ways you can draw pi bonds? Sir, very simple. Now the possibilities are, you can draw pi bond here, so it will be structure number 2, here structure number 3, here structure number 4. So these all are 4 structures. Sir, no, you do not have any other option, because if you draw there, it will be like this only. So these are the 4 possible structures. Now what about 2 cycles? Sir, how can we have 2 cycles? Just go to this, like you have a rectangle, you can either have this. So these are 2 cycles. Check for the formula, you'll get the same formula, because 1 cycle and 2 cycles. 2 cycles will have du2. So this will become your 5th structure. Was the trickiest part. So the answer for this question is 5. So these type of questions you get in mains also and advanced also. Moving ahead. Now again some questions. So we have to relate. This is N-propanol. N is as in normal, prop as in 3 carbon with an OH. So this is propane-1-ol. Isopropanol. So iso is 1st carbon, 2nd carbon and a methyl branch, and to the free valency we'll write OH. So these are the general names given. So this is propane-1-ol, this is propane-2-ol. So main chain is same, position of functional group is changing. So these are position isomers. So position isomers as in P is 3. Okay, P is 3. Let us go to the option. P is 3. P is 3. So these 2 options are eliminated. Moving ahead. What about methoxypropane and ethoxypropane? Obviously it's an ether, so it will be metamer. Let us check, let us draw the structure. Methoxypropane. So how you will draw methoxypropane? Sir, methoxy and propane as in 3 carbon, because this becomes methoxy and this is your propane. Now ethoxyethane, ethoxy and ethane. So this is your main chain, this is your ethoxy group. So what are they? They are metamers. So Q is metamer, as in Q is 1. So Q is 1. Q is 1. No. Okay, so this is Q. Okay, Q is 1 in that option also. So we have to check R then. R is propanone and propanol. Propanone is ketone, propanol is aldehyde, so they are functional isomers. So this is R is 4, R is 4, R is 4, R is 2. So C is right. Option C is your answer. Let us check this also. Neopentane, isopropane. General name. I told you general name is important. Neopentane and isopentane. Let us draw neopentane. What is a neo group? 3 degree carbon. The next carbon and to its you will draw the free valency. So here if you will draw this OH, so this will be neo. Okay, that was not neopentane, it is just neopentane. So to this free valency, if I'll add hydrogen, so this is nothing but neopentane, because what is neo group? The carbon besides the tertiary carbon is your neo group. To that carbon, if I'm adding hydrogen, that is neopentane. Isopentane, okay. First, second, and a methyl branch and free valency. This is isophoto, but I have to draw isopentane. So this is propane, this is butane, and this is pentane. So what about them? They are, this is a 3 carbon main chain. This is a 4 carbon main chain. So what isomers are they? They are chain isomers. So they are chain isomers. S is 2. Although we directly have got the answer, but because we are practicing, so I'm telling you everything. Moving ahead. Now, which of the following is metamer of the given compound? This is the structure you have. What functional group it is? It is an amide with benzene on one, phenyl group on one side, and cyclohexyl group on the other side. Now, what about this? Sir, molecular formula is also not same, because here this is cyclohexane and here they have taken phenyl. So molecular formula will be different. So obviously not an answer. Now, here nature of functional group has also changed, and I guess, although nature of functional group, this was an amide and this is an aldehyde and this is an amine. So if nature of functional group changes, so they becomes functional isomers. The question is asking you metamer. So no, it is not a metamer. What about this? No, sir, molecular formula is also not same, because here it is cyclohexane, here also it is cyclohexane. It has to be benzene on one side. So here molecular formula, they are not even isomers. They are not even having same molecular formula. So obviously last option is right, because nitrogen, the amine side has phenyl group over there. Here the amine side has phenyl. So nature of alkyl group is flipping. So obviously option D. See, simple. Pen, you just do not have to pick up your pen, and you just visually, if you know the definition, you can find your answer. Moving ahead. Now, again, okay, metamers, these are all asked question. This is JEE Mains 2021 question. Now, let us relate. This is phenyl group and 2 carbons. This is a phenyl group and 2, okay, there are 3 carbons, so they are not even isomers. See, in JEE Mains question, always check that whether molecular formula is same or not, because they have the molecular formula is also not same, so they are not isomers definitely. Now, this is a 3 carbon with 2 branch. This is, okay, so these are chain isomers, so not an answer, not an answer. Obviously this is a ketone, this was also a ketone. Let us calculate number of carbon. 1 2 3 4 5 6 7 over here. 1 2 3 4 5 6 7. Definitely. So these are not positional isomers, by the way, because ketone is a divalent functional group, and along divalent functional group, what is changing? Nature of alkyl group. So chain position definition is not considered. They are metamers. Obviously we got the answer, but still checking. What about the last one? Sir, this is a alcohol. This is also alcohol, but position of alcohol is changing. So it is a positional isomer. So not a metamer. Moving ahead. Yeah. So moving forward, after a day's break on my part, let us continue our discussion on the last type of structural isomers. Structural isomers are also sometimes called as constitutional isomers. So the last type of structural isomer for us is tautomers. Now, the definition of tautomers actually started in the history from acetone. Acetone is the smallest ketone. So what is, sir, if I have to form a ketone, I need a carbonyl group, and to a carbonyl group, because I want to form the smallest ketone, so minimum I need 2 carbons on both sides. So because this is the smallest ketone, so even if you write this 2 or not in its IUPAC name, it has to be the same compound. So its IUPAC name will be propane 2-one or simply propanone, because over here even I can skip 2. Generally 1 is skipped, but for ketone, even if you even if you have to form a ketone, it has to go to the second carbon only. It cannot go to the first carbon, else it will become an aldehyde. So acetone is the general name of propanone. So one scientist called Franklin, this is the actual history behind the development of definition of tautomers, that a scientist named Franklin was working on a bottle of acetone. So whatever the bottle, that compound, that acetone was giving all the properties, all the positive test that you will be seeing in our later chapters of organic chemistry, that it was giving a perfect, beautiful, positive test for ketones. So Franklin said acetone is a ketone. But on the other side of world, a scientist called Duppa was also doing experiment on the same acetone compound and was getting positive test as if it is an alcohol. Like if you react alcohol with sodium metal, it forms hydrogen gas. So Duppa said no, it is an alcohol. So they started fighting with each other, as in a scientific fight was happening between them. So another scientist named Nor, although you do not have to remember the name, another scientist Nor ultimately told them that no, this compound, this ketone actually, or carbonyl compounds, if they contain an alpha carbon. What is an alpha carbon? The carbon next to a carbonyl group. Now this is our carbonyl group. So the carbon next to a carbonyl group is called an alpha carbon. So, nor this equilibrium, existence of equilibrium between keto form and enol form was actually told to the scientific community by Nor. Nor experimentally determined and told the scientific university that no, Franklin, acetone exists in this form also, and acetone exists in this alcoholic form also. If you try to write the name of this compound, then what it will be? Sir, it is prop 1-ene 2-all. So it is an enol form. So hence the name enol forms. So some students confuse themselves by the fact that tautomers are only keto-enol isomers. No. There are many examples of tautomers like nitroso-oxime tautomers, like ene, amine and imine tautomers, but they are not meant for JEE mains. So even I have not written them, I'm just iterating them. So there are many examples of tautomers in nature. But the very famous example with which the definition of tautomer started, the famous example of tautomer is a keto-enol isomer. Now, if you just look at the molecular formula of acetone and this propene 2-all, that is enol form of this acetone, then they have same molecular formula. But obviously their name is different, their functional group is different, then they should be called as functional isomers. But they are not called functional isomers because Nor said that these two structures exist in dynamic equilibrium with each other. As in, if at this point of time, if you have 100 molecules of acetone, then some molecules of acetone will be existing in this particular form, but in the same very moment, some molecules will be existing in the form of an enol form, within the form of an alcohol. So this was experimentally determined by Nor, and to these structures, because they were satisfying the definition. What definition? They had same molecular formula but different structural formula. So they were given the name tautomers, because generally functional isomers are two different compounds existing independently in nature. They are two different compounds, but they are existing simultaneously in a dynamic equilibrium with each other, and therefore they cannot be named as functional isomers, and hence given the name tautomers. Now, sir, I have written all these. There are some theoretical information also, like what is the difference between the electronic distribution? Here, double bond, the pi bond is between carbon and oxygen. Here, the pi bond is between carbon and carbon. What is the other difference? The movement of atom is there. What atom? Hydrogen. Hydrogen is moving from this alpha carbon to the carbonyl oxygen. This is the carbonyl group, and now receiving that particular hydrogen. Movement of an atom. In Latin, tropy is known as movement or transfer, and desmo refers to an atom. So desmotropy is also a name given to tautomerism. What atom is moving? Hydrogen. Therefore, sometimes to keto-enol isomers, they also refer as prototropy. So these all are some extra information which you should know about tautomers. Now, generally, we definitely because NOR has determined as they exist in simultaneous equilibrium, in a dynamic equilibrium with each other. So for equilibrium we can definitely experimentally calculate the equilibrium constant. So it was calculated. Through the value of equilibrium constant, we can definitely say the reaction is not at all moving forward, because value of K is 10 raised to power minus 6, of the order of 10 raised to power minus 6, so it is very small. So if equilibrium constant value is very small, that means what? Sir, at equilibrium, when the reaction or mixture always exists in equilibrium. So when you take a bottle of acetone, largely equilibrium is shifted in backward direction. So it was concluded that generally keto form is more stable than enol form. And what is the approximate percentage? Ketone form exists in a percentage of more than 99%, and enol form contains they exist in nature less than 1%. Now, why it is so? Sir, we can see thermodynamically also. Bond, when you, if you look at the keto form, what extra, if you want to move from a keto form to enol form, what bonds you have to break? Sir, this here it is a double bond, here it is a single bond, so we have to break this pi bond, this C bond O, and this is CH3, but this is CH2. So one bond what I have to break is C bond H. So C bond H has an energy of 440. One bond which we have to break is the C double bonded O, which is, although we'll break just the pi bond because one bond is still there. So what amount of energy is required? 720. So what is the total energy required thermodynamically? 1160. Now, if I need to come back from enol form to keto form, what bonds I need to break? Sir, this O bond H, because then this O bond H will become, with this hydrogen, will be moving to back to this carbon. So if this hydrogen is removed, then this O bond H has to be broken along with this pi bond, the C bond C pi bond. What is the energy that is required, sir? 1120. You do not have to learn this energy, but at least learn the logic that 1120 higher or 1160 is higher. 1160 is higher. So what is the difficult task to do thermodynamically? 1160. So what is the relatively easier task? 1120. Therefore, this energy is supplied and reaction proceeds in backward direction. So if theoretically someone is asking you that why keto form is more stable, reason being keto form is thermodynamically more stable than the enol form. I can give you a inorganic knowledge also. Now, this is a double bonded carbon. So if you look at the double bonded carbon, we know through chemical bonding, double bonded carbon is electronegative carbon. If an electronegative carbon is connected with oxygen, who itself is an electronegative atom, so if I also want electron, that species also want electron, so they start fighting with each other, because no one is losing, no one is giving up to the fight, as compared to when a single bonded system is connected with an electronegative atom. Single bonded is not that electronegative. So single bonded carbon can easily give the level of the amount of electron required by the electronegative atom. So this is a common sense of inorganic, which you should also know. Therefore, the theory says thermodynamically keto form is more stable than enol form. Now, sir, but how these two forms are, I will also give you the mechanism of how keto form is converting into an enol form. But just to give you an idea of the reaction mechanism side of it, let us discuss that this is a carbonyl group, how it is converting to an enol form. Now, starting the logic of reaction mechanism from this topic, because in GOC-2 that we'll be discussing in the next short, we will be spending much of the time and our attention on the reaction mechanism side of the organic chemistry. Now, so I'm starting this reaction mechanism logic starts from the topic of Tautomerism only. So I'm starting from this point only. Now, this is OH minus. Sir, what is this? This is an electron rich species. Electron rich species wants to give what? Wants to give electron. So the species who wants to give electron is known as a nucleophile also. It is known as a nucleo, as in plus, and in Latin philic nature, as in loving nature. So what is a nucleophile? Plus loving. Now, If this plus loving species is attacking a carbon, now actually to an electron rich species, when we refer an electron rich species as a nucleophile, an electron rich species is not always termed as a nucleophile. An electron rich species becomes a nucleophile when it is giving electron to carbon. And why giving electron to carbon? Because we know carbonyl is a electronegative group because of presence of this oxygen atom. Because it is highly electronegative, so this becomes highly polar, taking delta negative and inducing delta positivity, as in deficiency of electron in the carbonyl carbon. This positivity is loved by this minus and the attack takes place. Let us do the attack. So as soon as this carbon is receiving electron from the incoming oxygen, so this oxygen has given the electron to this carbon, so a bond is formed. Once this carbon has received that electron, it do not require this extra electron, so this pi cloud will be moved to this oxygen. It is electronegative also, it will try and receive that electron, so this O becomes O minus. But as we very well know, every reaction is reversible. So this can also take place, but reverse can also take place, as in these electron can even fall back, and once this central carbon receives the electron from oxygen, it will further give away, it will further kick back this OH minus, and this reaction can even go to backward direction. Sir, again we have to see the equilibrium constant value. Yes, experimentally it was seen also, and without doing that experiment through common sense, you can also say that, sir, there is nothing special about the product, so why it will be formed? If this OH minus is taking so much of pain and attacking the reactant molecule, whenever the product formed is stable, then only it will be formed, else it will not be formed. I'm not saying this minus plus will not attract, because reaction mechanism is nothing but attraction between minus plus. But that minus plus attraction may be of n number of types. Like this is the path 1 through which we have received a product, but we cannot say that that product is any way more stable. It is just same. So this will not be happening because I'm not feeling very much comfortable, very much stable by forming that product. So why will I do a thing to which I'm not liking at all? So I will remain in what state I am. Now, because there must be some other case also, because you will say, sir, but minus plus will attract each other. So why this minus is not attracting that plus? Because there is another plus which is more, which is to which this OH minus is more inclined to. Now what is it? Let us understand that. As we already know, carbonyl is a strong electron withdrawing group. So it will withdraw electron as a unit. This CO will also withdraw electron. Now because I am withdrawing electron, I will make my alpha carbon, that is the carbon next to me, as in this carbon, I will make my alpha carbon electron deficient. That alpha carbon, if containing hydrogen, which is always the weakest section of the society, it is that player in a game which is the weakest player. So who gets all the beating? The weakest player. So this small hydrogen with no electronegativity will be forced to give away its electron as demanded by the alpha carbon, and this alpha carbon will happily take up this extra electron in order to satisfy the demand of electron that is coming from the strong electron withdrawing group. So this carbon becomes acidic, and as soon as a base, now this electron rich species giving electron to hydrogen is now referred as base, not nucleophile, because when an electron rich species gives electron to hydrogen, it is termed as a base. I'm giving you all very thorough logic. Please Make note of this. If you need, revise and repeat, rewind and listen to this again. This is very, very basic importance which student do not give attention to. Now this base will give electron to this hydrogen. So the whole thing is removed as H2O. Sir, what about this electron? This electron will go to this carbon and carbon will form a carb anion. Let us draw this. So this is a carbonyl group still attached as it is because it is highly electron withdrawing. These two bonds can be anything, but carbon has recently rejected hydrogen, taken away its electron and became a carb anion. Now you will say, sir, why this reaction will take place? This will also not take place. What is so special about the product? There is a very special thing about the product, and the speciality is this product is resonance stabilized. But sir, you said resonance effect is an electron displacement effect which we will do in GOC-2. But why you are? Because in chemical bonding also we have done this much of resonance so that we can understand that resonance is nothing but delocalization of non-sigma electrons. Non-sigma electrons are not localized as sigma cloud, sigma orbitals. Non-sigma electrons are free to move, free to delocalize. This carbon has taken up these extra electrons and it is not its sole responsibility to take and bear the burden of these. For example, you are going to station. This is an extra burden. You take 10 more luggages with you. If you have the whole set of friends with you who are eagerly waiting that you will give your luggage to them and they will help you to board a train, then you will not have any problem in taking 10, 20 extra luggage with you because you have n number of people who are always ready to share your extra load. Similarly, this lone pair is not, carbon is not electronegative, but this lone pair is not the whole sole responsibility of carbon because it delocalizes. What is delocalization? Out of these two electrons, if this forms a pi bond, this is delocalization. So a pi bond is formed over here. As soon as this carbon has received this extra yellow electron, it is not requiring this green electron. So it will move back to this oxygen. So this extra electron is actually even carried by this oxygen. And oxygen being more electronegative is very happy to carry the extra luggage of carbon. So this carb anion is not stable. It is very stable. And because here the intermediate, the product form is stable, the reaction will move in forward direction. And as reaction will move in forward direction, what picture you are seeing? Sir, it will be a double bonded carbon with O minus. Hydrolyze it, it will become OH and hence you will get your enol form. So that's why keto can also change to an enol form, and keto form is thermodynamically stable. But here the reaction, the chemical kinetics is telling you because intermediate form is stable, so it can also proceed to form a stable enol form. Stable with respect to what? Stable with respect to that part. But out of keto and enol form, which is more stable? Keto form. Are keto form always more stable? We'll be discussing more about it in the coming slides. But coming to the mechanism which we have, sir, some people gets very confused. Generally, tautomerism takes place in basic medium, which we have already seen. So let us revise it again because I have given you the mechanism. So I have written a beautiful way of, so that the colors will be very visually visible to you. So when this notes will go to you, it will be very clear to you to understand again. Now, this tautomerism in basic medium we have already done, as in the presence of a base. This is a ketone. This is the alpha carbon having this hydrogen which will become acidic. So when a strong base is attacking to this hydrogen, it will be removed as water and a carbon ion is formed. Now, the carbon ion formed, which we have shown in this slide, the carbon ion is formed. I told you it will be easily resonance stabilized, and in fact oxygen will be very much eager to take up this extra electron. So what will be the resonating structure? Here it will be a pi bond and it will become O minus. I've drawn it over there. There is a double bond and this is O minus. A beauty. What beauty? I'm showing that this red electron is coming to the oxygen extra. So this must be that pi bond. Now this is called, because it's a base, so this OH minus was given by, let's say, some metal hydroxide like NaOH, magnesium hydroxide. So the after giving of OH minus, there will be some plus also. Let's say that plus is B plus, Na plus, Mg plus 2, whatever. So this Na plus and this minus will form a salt, and to this ion we refer as enolate ion. If you hydrolyze this, base will be washed out and this O minus will attain plus of water and will become OH, your enol form. But some people get confused and say tautomerism can only take place in basic medium. No, it can also take place in acidic medium. How, sir? Although the mechanism, the actual mechanism you can leave for advanced, but still I'm telling you this because in complete of your organic chemistry, this logic will be helping you that reaction mechanism is nothing but attraction of plus minus. Now, it can take place in acidic medium also. How, sir? Like you have HCl, HNO3, whatever acid you have, it will furnish H plus. When H plus is furnished, because we know carbonyl is a polar molecule, so there will be presence of lone pair on oxygen. Can't you see this lone pair can also be donated to this H plus? Sir, what will take place? Sir, this OH will be formed. Oxygen being electronegative, after giving that lone pair will attain a positive charge and will become very, very, very electronegative. Now, although carbonyl group was stable, but after this protonation of the oxygen of carbonyl group, oxygen is very, very angry, highly electronegative. So it will demand extra electron from carbon, and therefore carbon attains a positive charge. Because this carbon is also not a weak player, because it is an sp2 hybridized carbon. So it will demand, if like for example, this is OH plus is like boss of your father. If your father, I mean, do not take it personally, I mean, if there is a if this, let's say OH minus is OH is a boss, OH plus is a boss of some person, and if it takes up that electron from that person will be feeling very bad. So when he'll be coming to his home, he'll be nikalofying his bharas, his anger that he has taken from out, received at office. He will be giving that anger in, I mean, not of the same amount, but some amount of that anger will be anyway shared in the family, in the home also. So this carbon will also scold this carbon that they have told me so bad things, and this carbon will ultimately go to the weakest section, which is hydrogen. So when this complete positivity is created, electron of this hydrogen can again be removed, and it will be removed in form of H plus. But now you'll say, sir, H plus, it requires some base. If you have taken an acid, let's say HCl, H plus was given, but Cl minus will be there. So that Cl minus is, I'm represented as A minus. So A minus will act as a base and will give electron to hydrogen. So its electron will be gone to that particular carbon, and this alkene is formed. So enol form can even be processed, enol form can even be produced in acidic medium also, in basic medium also. A very beautiful mechanism I have written for you with different colors, although you do not have to learn the mechanism, but try to understand and have the feel for not tautomerism, but for later discussion of organic chemistry. Now, up till here, what we have summarized, sir, tautomers are isomers having same molecular formula, different structure formula, and what type of different functional groups also. There are many examples of tautomers, but to us the famous example is a keto-enol isomer, out of which keto form is generally more stable and enol form is less stable. How keto form becomes enol form? The alpha carbon of keto forms, hydrogen is removed and is taken to the oxygen of carbonyl carbon. Generally, to the keto-enol form, because movement of hydrogen takes place from one atom till the third atom. You can check that. From the hydrogen is moving from this first, second, and moving to the third atom. So this, sometimes this is also called a triad system of tautomers. Although this is more information, so I've just summarized whatever I've told you till now. Now, What type of questions you are supplied with? Very easy question. As per talking, I'm strictly talking for JEE mains, because advanced loves Tautomerism, so have to invest a bit of more time in Tautomerism, but I will be restricting myself till mains. Reaction mechanism of Tautomerism I've discussed because it will be helpful in carbonyl compounds also. Now, let's say this is my ketone and we are asked to draw its tautomers. So a ketone can form tautomers, yes, if it contains alpha carbon. Do it contains alpha carbon? Yes, it contains 2 alpha carbon. What is alpha carbon? Carbon next to the carbonyl group. So this is also my alpha position, that is also my alpha position. How many hydrogen this has? 3. How many hydrogen this has? 2. Hydrogen in general, you will always think of basic medium in general. So let's say this hydrogen is removed because of presence of base. I get a minus over here. I can even get a minus over here. Now, you tell me which minus is more stable? 1 degree is more stable, because if this is minus, then this is receiving electron from this side also, so it will have more luggage. When you think of minus, think of like you are carrying a luggage. This carbon is carrying extra minus. So when you will be comfortable, carbon is not electronegative. So when a carbon ion is comfortable, when someone is sharing the burden of luggage, this methyl group is in fact overburdening this carbon. So what type of carbon ion is more stable? Least substituted. So this carbon ion is relatively more stable, and hence this will lose its hydrogen and forms the carbon ion. This carbon ion will be directly going over here. It will be coming over here. So what will be your structure of the isomer? Structure of the enol form. So to this keto form, this will be your enol form. Now, this enol form is stable. I mean, I just make, because this is the first question I'm discussing, we just make that enol form also. Which one? When this carbon was losing its hydrogen, what structure you'll be getting? This structure. And you'll be getting OH over here. So double bond is formed between these two. But let's say this structure is, this compound, this is A, this is B. So what I'm saying is, this is more stable. Obviously, this is not formed because that carbon ion is relatively more stable than this one. But students confuse themselves with this thing, that out of keto and enol form, who is stable? Keto form. Existence of enol form is generally less than 1%. But in that one, out of that, those 100 molecules, 99 molecules will be existing in keto form. Only 1 molecule will be existing in enol form. That's why it is not called functional isomers, because they are same compound maintaining itself in a dynamic equilibrium between this structure also and this structure also. But both structures are existing at the same point of time. So out in that 1%, who will be forming this enol or that enol? That enol. So you have won the race among being a stable enol. You are also gone case, I am also gone case when compared with the keto form. So keto form is more stable. Enol form is anyway less stable than keto form. But between enol forms also there may be a fight. This is what I wanted to tell you with this example. Now, discussing some more examples, like for what about this one? Sir, again, we have now been a bit sharp. So this is alpha carbon, this is alpha carbon. So when minus comes over here, it is 3 degree plus I from all the sides. So minus will not be stable. Here plus I is only from one side. So relatively this is not good. This is relatively, this minus will be good. Relatively as in with respect to 3 degree I am better. So this will form, this will give hydrogen and will get the pi cloud. So what will be our keto form? This carbon, then these two bonds, and here I'll get the OH. So I'm forming the double bond over here. So this becomes our keto form and this becomes our enol form. Keto form is more stable, enol form is less stable. But what is the enol form which is getting produced? This one. Here I am not putting the double bond because this is the minus is not stable when carbon gets substituted with alkyl groups. Now, what about this? Again, sir, you are giving us same question. Now, these questions are good questions. For example, I have to draw enol form of the structure. Sir, carbonyl group, done. Sir, this is also alpha carbon, but sir, alpha carbon. Now, I'm mentioning one thing. If you want to take hydrogen from an alpha carbon, that alpha carbon has to be sp3 hybridized. You must have observed in the previous cases, in the previous slides, that alpha carbon has to be sp3 hybridized, because sp2 hybridized system is always electronegative. So why it will be reacting in this fashion? So what alpha carbon of beside a carbonyl group, the carbon present is an alpha carbon, but what alpha carbon releases H plus? sp3 hybridized. Sir, then this is only sp3 hybridized. This is the alpha position, but this carbon is not sp3, this is sp2. But if you just look at this carbon, now if this will release H plus, minus is formed over here. This minus is resonance stabilized, minus pi sigma. Pi cloud can go over here. But what if I can show you more extended resonance? Remember, this was stable because of resonance. If somebody is having more houses, think of resonance like this, that you are staying in a township and minus sigma pi, as in after a sigma bond, you after next, I mean, if you are staying in a township, you are living in a house. After next house, you again have, let's say, your relatives. I mean, in a township, there are lots of duplexes. You are staying in one duplex. Next duplex, you do not know. But next to next, it is a duplex of your family only. So you can roam around in this building also, and you can roam around in that building also. So you will be very much stable in that particular township. And if the duplexes are getting extended, then you are having more and more and more houses to live in. Similarly, so you'll be more stable. So similarly, this electron cloud, if getting extended, sir, how? Let's say if this hydrogen is removed and minus is coming over here. Now, I'll show you this minus. If this CH2 is attaining a minus, let us check the level of resonance this has. This has got an extended resonance because pi sigma minus. Whenever you have to check the delocalization of cloud, there should be alternate positioning of non-sigma. So non-sigma, then sigma, non-sigma, then sigma, non-sigma. It is called a conjugate system. We'll be doing this thoroughly in GOC2 in resonance. But I'm discussing over here because some logics you should know in the beginning only, because resonance we also know through chemical bonding. Now, so this sir, and this sir, oh, this is very extended conjugated system. So this is more stable than the simple less conjugated resonance. So here I'll get a pi bond because this extra minus will form a pi bond. This pi will be flipping to this carbon. This double bond O will become O minus. Let's say it is getting H plus from solvent, so I'm writing H also. So this also becomes your enol form, and in fact it will be more stable enol form. More stable than whom? More stable than this one, when you get a pi bond over here and OH over here. But obviously less stable than the keto form. Moving forward. Now, what about this? This is actually a super special case of, what is the extreme case of resonance? Sir, when resonance gives you the character of being an aromatic compound, then you become a not resonance stabilized. Extreme case of resonance stabilization is aromaticity. You become an aromatic compound. So for example, if this keto form is supposed to become an enol form, so what I'm telling you is, if this keto form becomes an enol form, then how can it become an enol form? Just focus on this carbon. If this hydrogen is taken up by a base, and if this electron moves to this carbon, you get a beautiful picture. What picture, sir? This is your conjugate base, the carbanion. And just like benzene, I'm just drawing one resonating structure for you. Just look at this resonating structure. A 6-carbon ring. This single double bonded O will become O minus. Let's say O minus received proton H plus from water. So I'm directly writing H plus. Now look at the pi cloud. This pi is recently shifted to this side. This minus has recently formed a pi bond over here. This pi is as it is. And this was a methyl group. Sir, this is benzene? Yes. Benzene is not only resonance stabilized, benzene is aromatic stable, because when this cyclic, when the delocalization of pi cloud forms a cycle, it shows that current is flowing. Movement of electron is current, and when this current is flowing in within the molecule, then these pi cloud becomes so stable that they do not react. Because now let's say you are those pi clouds getting delocalized. Remember that township example? Because you have got so many alternate position, house, so there'll be family members. So the members of the family will be playing among themselves only. They will be not visiting anybody outside the township for any type of friendship. They are stable. What is stable? You will not react. That's why I told you, double bond of benzene never react. We will be throwing more light on aromaticity, resonance in GOC2. But this is common sense, so I'm dealing here also. Now, one more thing I have to tell you, that whenever a cycle of resonance is completed, and this is completed by 4n plus 2 pi electrons, by 4n plus 2 pi electrons. So this rule is called Huckel's rule. Hucke. This is called Huckel's rule. So when an resonance stabilized become aromatic, when the cyclic conjugation is done by 4n plus 2 pi electrons. N can be any whole number. If n is 0, it can be 2. If n is 1, it can be 6. So for example, over here, how many pi electrons are completing this electron current, this delocalization? 6 pi electrons. So this is following Huckel's rule, and this becomes aromatic stable. And mind you, when this enol form becomes aromatic stable, so by the name only we know aromatic compounds are not stable, they are very stable. So this is not only a enol form stable with respect to other enol forms, because other enol forms you can also make. You can also remove this hydrogen, can make pi bond over here, this will move, that will move. But out of all those enol forms, this is more stable. This is even stable than the keto form. How do we know this, sir? We know this through the value of equilibrium constants, but you do not have to learn those values. You have to learn this case. What case? That generally keto form is more stable than enol form, but some special cases enol form can also become stable than keto form. What are those cases? Let us directly jump to those cases. This I'm leaving because that is an example of anti-aromatic compound that we will be discussing after GOC, although I have written that question. But coming directly to stable enolic forms, one we have already dealt. Aromatic enolic forms. If compound become aromatic, then enol forms become more stable than the keto form. For example, let's say this is basic example of an alkene. I've even mentioned this carbon with the green color. Remove one hydrogen, pi cloud will be moving here, here, and here. You will receive your phenol. Already done that in the previous slide. So what is the first case when an enol form can become more stable than keto form? In case of aromatic enolic forms. So what is the famous example of an aromatic phenol? Aromatic enol, the phenol. Now its percentage will increase and its percentage will decrease. Although I have written 99% over there, because how I have written that? By knowing the value of equilibrium constant. So just in order to make you learn this, that aromatic stability is not this stable. When generally enol form used to get 1 rupee out of 100 rupee share. Because of aromatic stability, aromatic form, the enol form is getting 99% share. So just think about when we say that aromatic is the extreme case of stability, the reason I have written that 99% is because I want you to feel that aromatic stable are not stable. They are very stable, that you were the weak, enol form were the weakest form of tautomer, but if aromaticity is present, then even the weakest player can win the race. Now it has become the winner. So just to have that feeling that aromatic is not just stability, it's extreme stability. Now, moving forward. Other case, sir, there are some other cases also. There are two more cases. First is the beta diketo. Now, we already know carbonyl group is ketone, aldehyde ketone. The next position after a carbonyl group is an alpha position. After that, beta position. Now, so let's say this is my carbonyl group. This is alpha carbon. This is beta carbon. Now, what happens is with this beta diketo, at beta position, there should be presence of both the carbonyl groups. What happen in this case is if they form a enolic form with the middle carbon, this is called active methylene group. That's why the middle carbon I've mentioned with a different color also. So what is so special about this carbon? This carbon is very acidic. Why? Because this is having electron withdrawing nature from this carbonyl group also and from this also. So this carbon is electron is being removed, extracted from this carbon from this side also and this side also. So this will be in very much tension. So this will directly take electron of this hydrogen because it will become acidic, and it is therefore called an active methylene group. Okay. So if it takes electron from hydrogen, then it can form a pi bond. So let us make a pi bond here also, here also. You can make anywhere. So let's say I made here. So this double bond O becomes OH. Now, one point is it is very acidic because both sides strong electron withdrawing groups are present. Point number two, why I'm saying this enol form is much more stable than its keto form also, because there is formation of intramolecular hydrogen bonding. Remember, when intramolecular hydrogen bonding comes into effect, when it forms a chelation effect. Chelation is a ring formation. So this forms a 6-membered ring free from any kinds of strain, and therefore because of presence of intramolecular hydrogen bonding, the steric crowding which was there has also reduced and molecule has become stable. So this enol form is more stable than its keto form. One more case, when you have alpha, beta diketo are stable, alpha diketo are not stable. But when alpha diketo are present in a cyclic chain, when alpha diketo, what is diketo? Let's say it's a ketone. What is its alpha position? Just let's say if I'm considering this is my ketone, the next to me is the alpha position. So this becomes alpha diketo. But normal alpha diketo are not stable. Cyclic alpha diketo are stable. So because cyclic are stable, and why straight chain alpha diketo are not stable? So because this is a famous example. So that's why I'm telling you that why. I mean, if I'm not a straight chain, I'm a simple alpha diketo. I'm a simple, not cyclic, I'm a simple alpha diketo. So what happens is, obviously these diketo groups will create bheed, crowding. So this crowding repulsion is called steric strain. It is called steric crowding, steric strain. So because of this crowding, there is steric strain. And because of this steric strain, what happens is at alpha position, molecule try to become enol form to reduce the strain. But over here, I will not feel the strain because this is not a cycle. So this carbon has to be a triangle. Agreed. This carbon has to be a triangle. Agreed. But this is also trigonal planar. This is also trigonal planar. This is just a single bond. So if I'm having a single bond, why will this group will be inclined this way? It will rotate because this was having a repulsion with this one. So why shouldn't we rotate? So if I am straight chain, I can simply rotate. That's what I'm showing. Just rotate it. So if it is that side, this is that side. Still this is sp2 hybridized a triangle. Still this is sp2 hybridized a triangle. So actually there is no van der Waals strain or steric strain. There is no van der Waals strain or steric strain is the strain due to crowding. So because I can easily rotate, so I am not feeling any strain. So I'm stable. So therefore, alpha diketo normally are stable, although you can even form their enol form also, but their enol form is not at all stable. This K value I have given because I've had this value through my good references, but you do not have to learn these values. I'm just giving you this value, which is because I'm telling you that look at the value of K. It is a 10 to the power minus 3. So reaction is not at all moving forward. That means alpha diketo are not stable because they can easily rotate and remove the strain. But if I'm cyclic, cycle restricts the carbon. Now it cannot rotate or else cycle will be broken. So now if you are a cyclic alpha diketo, you have to remain as it is. You cannot rotate because cycle is there. Cycle will get broken. So now you cannot rotate and you will feel that repulsion also. So what you will do is you will try to reduce the repulsion. How? Just form your enol form. How, sir? This is alpha carbon. I mean, this can also do, this can also do, any will do, but it will be the same thing. So let's say this carbon has lost one hydrogen, hydrogen gone. So it will form a pi bond, pi bond. This double bond O becomes OH. So now again it becomes intramolecular hydrogen bonding. Yes. So again, I'm having double profit. One, the strain is getting removed. Two, I'm getting extra stability also because of attraction of hydrogen bonding. So a cycle is formed. And this cycle is a 6-membered ring structure. 5 and 6-membered ring structure are very stable, provides a chelation effect. And in those cases only we get intramolecular hydrogen bonding. Now, these are some examples where enol forms become more stable than the keto forms. Now, these are the examples that is asked by JEE Mains. I mean, just basic examples. I mean, this is a JEE Mains 2024 question. You have to tell which has got the highest enol form. So we already know keto is not stable, enol is more stable. So when this is CH2, this hydrogen will take electron. This carbon will take electron of hydrogen, will form a pi bond over here. This will move. Again, this will move bond over here. Again, this carbon will give bond over here and this. Sir, this is phenol. So let us form this phenol. This double bond O becomes OH. This double bond O becomes OH. This double bond O becomes OH. What about the pi cloud? I'll use another pen so that it may look beautiful to you. This carbon will take electron from hydrogen and give to this carbon. So this is the pi bond formed between these two. This is the pi bond formed between these two. This is the pi bond formed between these two. So, sir, this is also aromatic. The same question that we have done, this is not asked one time, this is asked many times. So for Tautomerism, you get only these type of questions. Now, although this is an advanced topic that sometimes you are even asked to organize that which enol form is more strong. So although I have given this content and given the logic also that electron withdrawing group increases the percentage enol content, and this is a very famous example, but famous for JEE Advanced. So then why you have written is for all those students who feel that extra edge is important, because Advanced asks it so many number of times, mains have not asked it. But I feel in good question of mains only, this can also come. But because we are already filling much of time in Tautomerism, so I'm moving forward, but I've included this slide for all those people to see. If somebody feel more comfortable and want to ask some question regarding this one, so you can always comment in the go to the comment section, comment. I'll get back to you with the discussion on the comment only. So moving ahead. Now, moving to the next topic. Now, after finishing the structural or constitutional isomerism, this brings us to the stereoisomers, having same molecular formula and structural formula. So here IUPAC name will also be same, but definitely they will be having different stereochemical formula, as in their orientation in three-dimensional space will be different. Now these space or stereoisomers are further of two types. First being the configurational isomers. They are also actually two different compounds satisfying the definition of being a stereoisomer. So they are definitely true isomers. But the other type of space isomers are conformational isomers shown by alkanes. And they are actually why I have written they are pseudo, because they are non-true. Why? Because they are not two different compounds. For example, if you have an alkane, then because of the sigma bond of alkane, these bonds can freely rotate. So because of my free rotation, I can form different orientations, or technically called the conformers. So these different orientations satisfies the definition of being called an isomer, but because this orientation and this orientation is of the same compound, so they are not two different compounds. So this conformational isomers are non-true isomers. And coming back to the configurational isomer now, the first type of configurational isomer, if this free rotation is restricted, how you can restrict this rotation? Just tie my two fingers using a thread. Now they cannot move. Now they are fixed. So if this restricted rotation is created in Mother Nature, then that particular restricted rotation is actually termed as a geometrical stereocenter, giving rise to the first type of configurational stereoisomer, which is a geometrical isomer. So directly going to what are geometrical isomers. So first thing, they should have presence of a geometrical stereocenter. What is a geometrical stereocenter? It is, as I've already said, it is that center which can have a restricted rotation. Who can restrict the rotation? If a pi bond is present. So presence of this pi bond will not allow the movement of these groups to undergo any sort of rotation. So if let's say it's A and it is B, let's say it is C and it is D. So A and D will be just opposite to each other all the time until this molecule is surviving in nature. So what is the most famous example of a geometrical stereocenter? An alkene. So there are some other examples also. Yes, JEE loves them, like C double bonded N. It can be an imine, it can be a substituted imine, it can be an oxime. These all are the nitrogen derivatives when they react with carbonyl compounds. So class 12th NCERT, that's why they are also important. Now one another restricted rotation that can act as a geometrical stereocenter that can force the molecule not to undergo any rotation is the cyclic compound. Because if a carbon is forming a cycle, then these two particular bonds of the carbon containing the cycle will lie in the same plane. But sir, carbon is sp3 hybridized, so it will be tetrahedral. But whenever you talk of a tetrahedral structure, two bonds can lie in the same plane. One can be upside of the plane, one can be downside of the plane. So how can you in 3D, how can you think of a cycle, sir? A cycle as in every carbon is sp3 hybridized, but two bonds will be in one plane, one bond up, one bond down, although it will not be a 90-degree angle. But for the case of simplicity, in order to show the geometrical isomers of a cyclic compound, because cyclic, if I'm forming a cycle, then this cycle will never break and will restrict all the groups. If A is upside and B is downside, then here if A is upside and B is downside, then it will remain as it is, because now these bonds can also not rotate, although it is single bond. Why? Because then cycle will break. So if cycle will break, the molecule will destroy. So till this molecule is existing in nature, it can also not have any rotation. So what are the examples of a center which we will now term as geometrical stereocenter? Are alkenes, C double bonded N, and cyclic alkanes. So or maybe their combinations can also act as a geometrical stereocenter. So if I need to satisfy the definition of being called a geometrical isomer, first thing I need to have is a geometrical stereocenter, and after that the groups attached with me on both the centers should be different. Why, sir? I'll give you an example also, and this is a JEE mains question also. Just last year, number of questions you get of this form, so I'm directly using those examples. Like for example, in the first option, the question is saying that which one of the following will show geometrical isomerism. So you have to check that condition only. Now, what is the condition? Sir, do it has a geometrical stereocenter? Yes, this C double bonded and a cycle. So it is combination of two geometrical stereocenters, which is a double bond will also restrict the rotation. Ring will also restrict the rotation. So how many geometrical stereocenters we have over here? Sir, one. Now, just look at both the group attached with both the centers. Now, this center is carbon of an alkene connected with an hydrogen and a bromine. So with this side of the geometrical stereocenter, both groups are different. Okay, now coming to this side, sir, this is a carbon, but this carbon is carbon of the cycloalkane, which is also geometric. It will also restrict the presence of these two bonds. They will never be rotated, or else the ring will break. So it is a restricted rotation, but the groups attached with this carbon should also be different. So how will you check the point of difference? Sir, go to the atoms attached to it. So going, now this is the carbon. I'm just coming to this carbon over here. So this carbon on this side attached to CH2, over here also CH2. So our environment is same. Over here CH2, this side also CH2, still the environment is same. It again reached to this carbon, which is CH. It again reached to this carbon with this, which is CH. So that means this side has different groups, but this side has same groups. And because it has same groups, so you cannot have different orientation. So it will not show geometrical isomerism. But because the condition of any compound to show a geometrical isomerism is, first you should have a restricted rotation center, and second is both the ends of that restricted rotation center should have groups which are different from each other. This side has different group, but this side has same group, and hence not capable of showing geometrical isomerism. Moving ahead. Now, what about this? This center is capable because it is having different group, because here this is CH2, this is CH2 same, but this is CH2 and this side is CH with a bromine. So this is satisfying the condition of having different groups. But now this has lost the battle because this is CH2. So it has both the same centers. So this is also not an answer. Similarly, this has lost the battle, and in this case this carbon has also lost the battle because it is also having similar group. So both the carbons are not capable of showing geometrical isomerism. If anyone will fail, the molecule will fail, but because I'm discussing this one example only to tell you all the logic, therefore I'm discussing every example, or else for JEE Mains it was a very easy question. Now if you know this, why will you check all the options? Now coming to this one, this carbon is definitely having two different groups, H and Br. Now let us check this carbon, sir. Again, this CH2 is same, but we'll go to next point of difference. This other is CH2 connected to the carbon on upside, and on downside this is CH with a Br. So environment is different. So this is also having different groups, this is also having different groups, and because they are having different groups, so orientation can change and it will show geometrical isomerism. Moving ahead. Now, sir, if I show geometrical isomer, the two forms will be different. So what are they called? Because they are different, so they should have been given some name. So IUPAC have decided their name also. The most famous nomenclature used to represent geometrical isomers is cis-trans nomenclature. Now, therefore, geometrical isomers are also sometimes called as cis-trans isomers. Now, what is cis-trans isomers? For example, this is, we obviously know the IUPAC name of this compound. I have already written it. This is but2-ene-1,4-dioic acid. Now, if you just check, I do not, because I have written all those things beautifully so that when you will get these notes, you can easily revise them. So I'm using laser, but you can definitely see here the similar groups are present opposite to each other. You can also see CWH, you can even see H. Even if one has, so this is a geometrical stereocenter, and both groups to this side also, that side also, they are different. So it is definitely satisfying the definition of showing geometrical isomerism. Now, what are geometrical isomers? They are two compounds having same molecular formula, same structural formula. IUPAC name is also same, but they have different orientation in three-dimensional space. And why orientation is different? Because it has a restricted rotation. This CWH, if it is opposite to each other, it cannot convert and come on same side, because then bond will be broken. If bond broken, then molecule has died. So if molecule is existing in nature, it will always exist in this particular form, where they will be opposite to each other. And where similar groups are opposite to each other, to that particular geometrical isomer we name as trans form. And obviously, when the similar groups are on same side, I am termed as cis isomer. Now, cis form of this is also generally termed as maleic acid, a very famous name asked by JEE a lot of times. And trans form of this isomer is also termed as fumaric acid. You can make some synonym, you can make some mnemonics, like for example, back in our time in NIT Kurukshetra, after we used to get freed from ragging, the last day we used to have FT. I mean, back in 2007, we loved them, because till now, I mean, why love? Because it used to create a bond between seniors and us. As in, still now, some of my seniors are so much connected to me that that bond is generally out of the very bad word, which is now these days I definitely recommend it should not happen. But back in our time, it was good also, it was productive also. And when we used to get free from our ragging, the final day used to be called as FT. So FT days used to happen back and in our point of time. So I have remembered this fumaric as transform FT. So even you can do some mnemonics, because this is one of the most famous general name. Now, so one type of nomenclature to name a geometrical isomer is cis trans. Moving ahead, you can also use another type of nomenclature, which is EZ nomenclature. Now, what is it? You have to apply a sequence rule called the CIP. By the scientist, it is named the CIP rule. You can skip the name and just go to the logic. The logic says, in order to show geometrical isomerism, I need a geometrical pseudocenter. Yes. Both the centers should have different groups. Having here, fluorine is there, chlorine is there. Now, here, bromine is, sir, if chlorine is opposite to bromine and if chlorine is opposite to iodine, these are two different orientations, hence two different geometrical isomers, but we cannot name them cis and trans. So people got worried, sir, because they are satisfying satisfying the definition of being a geometrical isomer, but we should have a tool to name them because they are different. See, orientation is different. So scientists IUPAC have given us the sequence rule, the CIP rule, which they said that with the carbon, you on each side you decide seniority, as in these two groups are different. Now, who is senior? They just simply go to the atomic number. This carbon is attached with fluorine, this carbon is attached with chlorine. Who is having heavy atomic number, mass number? If atomic number ties, go to mass number. So who is heavy? Sir, this is heavy. So this becomes my senior group. So this becomes my senior group. Among bromine and iodine, now let us prioritize the seniority on the other side. So this carbon is connected with bromine and iodine, which is having high mass, sir, iodine. So this is senior. When senior group are on same side, but this is senior group, not similar group. When senior group are on same side, how seniority I'm deciding? By just looking at its mass number. If senior group are on same side, I will call you a Z form, a Z isomer. And obviously here senior group are opposite sides, so it will be termed as an E form. Many students forget this, that opposite is E. So even for that I have a mnemonic. The mnemonic is, for E, you should always start uttering opposite. Opposite. How I make my students remember is, E is opposite. So when similar groups are opposite to each other, it is opposite form. Moving ahead now. Sir, cyclic is also a geometrical pseudocenter. Yes. Here both the groups are same. Here both the groups are same. So, sir, not capable. But this can generate geometrical isomerism. Why? Because this is ethyl and Me different. This is some alkyne and this is some alcohol. So both are different. Sir, two compounds having same molecular formula, same IUPAC name, but different orientation in three-dimensional space. Let's say cyclic compound forms a ring, cyclic carbon chain forms a ring, and one bond of the tetrahedral carbon will be upside of the ring, one will be of the downside of the ring. So it will not be exact 90-degree, but in order to show its orientation, sometimes the structure in two-dimensional copy in your notes, in your book and pen and paper, it can be represented like this, that one bond is upside, one bond is downside. So if ET and alkyne are upside, then this is one orientation. If ET here, okay, I have not changed the orientation, so let me change this orientation because I need to show two different compounds. So this will be CH2OH and this is C triple bond CH. So this ET and alkyne on same side, here ET and alcohol on same side. So they have different orientation. So they are also geometrical isomers, but we have to know a tool to name them. So again, we'll use EZ nomenclature. How? Decide the seniority at this end. So among ET and Me, sir, obviously carbon, this is Me is CH3, this is CH2CH3. So CC got tied, but after that it is connected with another more carbon, it is connected with all hydrogen. So above one is senior. Do not just count, just go to the attached atom, and if that gets tied, go to the atoms attached with that atom. Pick that one which is having the highest mass, because remember when you used to see Ramayana when you were small, so when atoms get tied, what bond you will pick? Which is having the highest mass. Like when the Ramayana Yudh used to be happen, what tir, what arrow you used to pick from your bundle? The one which is having the highest power. Generally we pick that arrow only. So that, and then make a fight, whoever wins will become senior. Like over here, okay, this side who is senior, this is senior. Now coming to this side, this is attached with carbon only tie. Now this carbon is further attached with almost, I mean all the three bonds are with carbon. So this carbon is now having what? 3 arrows of carbon. So he'll pick one arrow of carbon. So here what is coming? Carbon is coming from this side. In order to decide seniority, I'm not giving you those theoretical rules, you just apply this common sense. So this carbon has next sent whom to fight the battle? Carbon only. This carbon, he got tied, but how many bonds it has? 3. 2 hydrogen and 1 with O, oxygen. So oxygen has higher atomic number, higher atomic mass. So this carbon will force an arrow of oxygen, and this carbon will force an arrow of carbon. Who won the battle? Oxygen, because I'm not considering all the mass, I'm just competing the bonds. Which bond? The best bond competed with the best one. If everything gets tied, then obviously they must be same. So because it is further connected with oxygen, so this becomes senior. So senior groups are on opposite sides, so this will be E form, and obviously here they are on same side, so it will be Z form. Although this is a very good example which I have given you, JEE do not ask that much of CIP. I mean advanced can, but mains, sir, so why you are telling us? Because mains have asked them. The basic CIP rule which you should know, that I have already told you, go to the mass number. Now the correct IUPAC according to EZ nomenclature. Sir, let us do IUPAC first. So how will you name it? Sir, this will be main chain 1, 2, 3. Double bond is coming at 3 position. Lowest, we have to give minimum number to multiple bond. Here it is 1, 2. So I'll start numbering from here. So this is 1, 2, 3, 4, 5, 6 and 7. Easy, sir. Now after this, sir, do we have any branch? No. So its name will be, this is hept, then 2-ene and 4-ine, because E is written first. After vowel and Y, vowel gets eliminated, so E gets eliminated. Now checking at least this in the option, hept 2-ene. Okay, sometimes this 2 is even written here. So I mean options can play with you with your common sense, because they have given ene but they have not shown the number. So what it will be? This 2. This you have to predict. So yes, this name can be right. No, this name is wrong. This name is wrong. Yeah, this name. So among A and D, how will you pick the answer? You have to know the EZ nomenclature. See, these questions, although this is a 2012 question, but an asked question and a very famous and probable question for JEE Main. So I'm not leaving anything apart. Now, what about EZ? So now this is alkene, which can show geometrical isomerism. So this over here, the what form they have formed, sir? This is hydrogen and this is hydrogen. But sir, if similar group on opposite side, it can be termed as trans. Yes, it can also be termed as trans. But if the question is asking you that you do not use cis trans nomenclature, you use EZO, so you have to use EZ nomenclature. So how? Because you know sequence rule. Go to the second carbon. This second carbon is what? Sir, this second carbon is it is connected with carbon, it is connected with hydrogen. Who has higher mass? Carbon. So this is senior. Now coming to this carbon, this is connected with hydrogen and this is connected with another carbon. So here this is senior. So senior group are on opposite side. So this is trans also and this is E also. Hello. So this is trans also, this is E also. So yeah, our answer will be this is E isomer. Now moving ahead. Now coming to the other nomenclature used for geometrical isomers, it is simply Syn-Anti nomenclature. Now, why the Syn-Anti nomenclature is used and why I am actually telling you this, because although for GOC essentially it is not very important, but for carbonyl compounds, the chapter of your NCERT class 12, aldehyde, ketone and carboxylic acid, they show a very famous reaction called addition elimination reaction. What generally happens during addition elimination is carbonyl group, we very well know it's a polar molecule containing good amount of positivity. Partial positivity in carbon is produced because of electronegative oxygen, already discussed. Nitrogen, ammonia and its derivatives, obviously they have nitrogen with lone pair, so this is electron richness, this is minus attacking this plus. This is our reaction mechanism which I was talking about. So this nitrogen will act as a nucleophile and will attack carbon. As soon as carbon will be receiving those electrons, these electrons will be getting transferred to the more electronegative oxygen, which is actually making this molecule polar. The moment nitrogen loses electron, nitrogen is also electronegative. So who ultimately pays the price of any battle? The weaker player of a game, hydrogen. So nitrogen snatches away electron of hydrogen and this hydrogen is released as H plus. The moment it is released as H plus, this O minus will trap this H and forms OH. This is a basic example of a nucleophilic addition mechanism. So as I've told you, I'm discussing the relevant reaction mechanisms also. Now, sir, here one hydrogen is removed, but this nitrogen is having G and H. Yes, G can be any group, because this is a very famous NCERT table where number of G are used in class 12 aldehyde ketones chapter. So for all the groups, I've generally mentioned them as G. Now, anyway, it easily gets dehydrated. So what gets eliminated? Water molecule. So after elimination of water molecule, what is formed? A pi bond. Thereby a restricted rotation is created. Therefore this carbonyl compound, it can be aldehyde, it can be ketone, can also show geometrical isomerism, because of presence of lone pair, if this group is in this side, it will remain in this side and it can be same side with R1 or R2 or with anything. So aldehyde and ketones, what aldehydes and ketones? Aldehydes and ketones undergoing this addition elimination and forming the different type of nitrogen derivatives, ammonia derivatives, are also capable of showing geometrical isomers. Now because they are also capable of showing geometrical isomers, so we'll need some nomenclature to name them as well. So what nomenclature we generally use? We definitely can use EZ nomenclature for them, but for them IUPAC and Mother Nature and our commercial world generally likes this Syn-Anti nomenclature. Syn, as the name suggests, sim is just like cis and anti is just like the trans, which is the opposite, but opposite and same of what? So coming to the oximes, when carbonyl group will be called oximes when the group attached with nitrogen is OH, and Aldehyde forming oximes are called aldoximes. The picture. Now, for aldoximes, the nomenclature is followed by just seeing the position of hydrogen and oxygen. So, aldehyde on one side will definitely have hydrogen. So, if hydrogen and OH are on same side, it is called syn, just like cis. If hydrogen and oxygen are on opposite side, it is called anti, just like trans. But for them, Syn-Anti nomenclature is used, and for aldoximes, you have to do not apply CIP, C, H and OH, because aldehyde will have H. So H, OH same side, H, OH opposite side. Do not apply CIP for aldoximes, apply C, H and OH. Same side cis or syn, opposite side trans or anti. And for ketoximes, for oximes formed by ketones, you definitely have to apply SIP. So let us apply that SIP. So it will be out of this carbon, this is senior. This is senior. So senior on same side. So this is Z. So opposite will be definitely E. Moving forward. Now, some other nomenclatures, some other geometrical isomerism nomenclature is famous. For some other compounds using same Syn-Anti or EZ. Now, hydrazones, these are all carbonyl compounds basic, and discussing what is hydrazones. When the attached group is NH2, then this particular compound is called hydrazone. So let us decide by CIP rule. Among this is senior, this is senior. So here senior group are on same side. So this is Z. So this will definitely be E. What about this? Now, this is phenyl hydrazone. When the group is not NH2, it is NH bonded with the phenyl. So what compound it is generally called? Phenyl hydrazones. These are all NCERT basics which we will be discussing in carbonyl compound. Most of you must be knowing them. So these phenyl hydrazones also can show geometrical isomerism because of presence of C double bond N. Now, what about the nomenclature? This is senior. That is definitely senior. So senior opposite. So it can be termed as E also. It can be termed as Anti also. We will not use trans, but Syn, Anti and EZ can be used side by side. Now, azo compounds, the azo compounds are also famous in NCERT. I mean, this phenyl. Generally, aldehyde ketones, azo compounds, which show aromatic, which show geometrical isomerism in nature, and we see lot of examples. But what our scientists see examples? Aromatic aldehydes and ketones generally show geometrical isomerism. So that's why you must be seeing in the examples and JEE, the question that JEE will be asking you, they generally offer aromatic aldehydes and ketones making these compounds because they exist in nature. Aromatic compounds generally show geometrical isomerism when they are aldehydes and ketones. Now, doing such reactions. Now, what about this, sir? Sir, again, it is same, sir. Senior group on same side. So this is also Z. So you can call it Z also or Syn also. In this case, you can even call it cis, but IUPAC generally prefers for azo compound, they prefers syn, not cis. Z. So they use syn, anti and EZ nomenclature. Obviously, this will be E or anti. So I have discussed few relevant topics, and now moving to this question also comes a lot of time now. Sir, how can we calculate number of geometrical isomers? So first case, when terminal groups are different, as in, see, if you have a geometrical stereocenter, what type of isomers you can have, sir? One can be cis, another can be trans. I mean, one can be on same side, another can be on opposite side. So one stereocenter creates how many geometrical isomers? 2. So do the permutation combination basic. So n, if a compound has small n number of geometrical stereocenters which are capable of showing geometrical isomers. So total number of isomers will be 2 raised to the power n. This is a common sense for calculating number of geometrical isomers, but when terminals are different, for example, an asked question, we'll be practicing all the theory with relevant examples. Now, you are supposed to tell me number of geometrical isomers which are having including geometrical, you have to tell me all structural isomers including geometric isomers for pentene. So what is pentene? Acha, one thing. Pentene, look, what will be the du of pentene? Sir, pentene is C5H10. So its du will be 1. one DU can be satisfied by alkene also, by cycloalkane also. And the question is also telling you that you just calculate acyclic. Do not calculate cyclic structures. So do not worry about cyclic structures. Question is asking you, you just calculate acyclic structures. That means you just have to calculate the geometrical isomers for alkenes. Straight chain alkenes having molecular formula C5H10. Okay. So remember, to calculate number of isomers leaving nobody in between, what trend, what pattern we learned? Whatever number of carbons you have, just first make a straight chain. So how many carbon we have? 5. So this is the 5 carbon chain. Now, after getting this 5 carbon chain, sir, what we do is we decorate it with what? With the branches or functional group or whatever. So what you have for decoration, sir, we just have double bond, because C5, 5 carbons use hydrogen definitely. Obviously, if you pick a double bond, 2 hydrogens will be coming less to satisfy the definition of being a alkene. So double bond can come here. Name will be, numbering will be done from this side. It will be pent 1-ene. If double bond coming to this side, name will be, so this will be pent 2-ene. Over here, so then numbering will be doing from that side. So these are 2 possible structures with 5 straight carbon chain. What we do after this, sir, break 1 carbon. Okay. So if we break 1 carbon from a 5-membered ring, we land up with 4 carbon main chain. This is the 5th carbon. Remember, we used to always approach such questions like this so that we do not miss any. 4 carbons. This is the 5th carbon. Not over here, because it will be 5 carbon chain, already done. Not here, already done. Here also will just give me the same structure, because I'll pick, if over there it will be 1, 2, so same. What else you have to decorate it with? Sir, now one more thing. We have the double bond to decorate this compound. So let us go to making that double bond. If double bond go this side, it will be same name. What name? 2-methyl but 1-ene. What about the 4th structure? So these 2 options explode. This one, name will be 2-methyl but 2-ene. What about this one? Will it be different? Let us name it and check. 2, 3. Yes, sir, it is different. This is 3-methyl but 1-ene. Now, sir, 4 carbon chain option done. Now, even if you make 3 carbons, you will have to pick 1 carbon at some place. Terminals you cannot place, so you will place all carbons in between. So there will be no position of double bond. So this is all the possible structural isomers which you can make of C5H10. Now, so what answer you will give? This is a JEE mains question. 2021. What answer you will give? 5. No, the question is asking you tell me all structural isomers including geometrical isomers. And now recently, after structural isomers, we have read how to calculate number of geometrical isomers. So let us check who all can show geometrical isomerism. So this is a time consuming, yes, but once you practice, I mean, it will hardly take 1.5 minutes. Now first draw this. Now, because here CH2, so if any of the group is having similar groups, then it cannot show geometrical isomerism, so no GI. What about this? One is CH, another is Me, so this terminal, this is good. Okay, one is H, another is C2H5, this is also good, so this will show GI. And because it will show GI, so this second one will be cis, another will be trans, and both these are different compounds. Now, what about this? No, sir, this will not show GI, because if any one end is symmetrical, leave it, because that is symmetrical. How can it show cis trans? Now, similarly, this one, sir, this carbon, this is also CH3, this is also CH3. So both are CH3. So this end has lost the battle. No GI. What about this one? This end has lost the battle, so no GI. So only one structure is showing GI. So how many structures you have? So 1. But this 2, this cis will be 2, and this trans will be the 3rd form. So this will be fourth, this will be fifth, and total you will be having 6. Or else you can only also do this, that how many structural isomers you had? 5. But one was showing geometrical isomerism. So this either the fifth, this second one will be cis. So there will be some another trans. So after this fifth, you will be having 1 6 also. So actually, if you'll ask me, these formulas essentially per se, for just practicing, you can always apply these formulas, but I recommend during paper you just use your common sense, like we have used and came up with number of geometrical isomers were 6 in number. In that case, so I just recommend, although I have given the formula, it is 2 to the power n, and when terminal groups are same, then what happens is you start counting with, if you just apply the formula, sometimes formula gives you answer, sometimes it will not. In order to understand formula also, we have to learn the basic. So although I have given you the formula, but I'm suggesting you that if you are doing such questions, then do them by basic, because in order to understand the formula also, we'll be understanding why this is not 2 raised power n and something different. So these are all statistical formulas, but I'm suggesting do not mug these formulas. Anyway, you will not be remembering them. So this answer is 6, and how we have reached to answer 6? With common sense and applying the same common sense again. Now, when terminal groups are same, what happens? Let us understand that. So in order to mug those formula, let us understand that, because to learn those formula also we have to understand. So do this in paper also. Yes, sometimes if you are very interested, then you can learn those formulas, because the answer will be coming. I mean, you will be saving much of time, but it will be risky also, because sometimes applying that formula will save time also, but it can also make your answer incorrect. Like this JEE question, I'll be discussing this question after this. Here that formula will work. Now, what is the case? Now, why the formula is getting changed? First, let us understand that. Now, let us name this compound. 1, 2, 3, 4, 5, 6, 7, and 8. So this is a 8 carbon ring with multiple 8 carbon straight chain hydrocarbon with multiple bond in 2nd, 3rd position and 6th, 7th position. Okay, sir. Now, so there are 2 geometrical stereocenters. Yes. So actually, if the terminals were different, so what we have, I mean, that was a common sense. This will give cis trans, this will give cis trans. So how many isomers you will be having? 2 raised to the power 2, because here are 2 successful geometrical stereocenters. So 2 raised to the power 2 is 4. But answer is not 4, because terminals are same. Now, sir, tell me what same means. If you try to number this, if I have numbered it this way, then 2 has got bromine. If I number it from this side, 1, 2, 2 has still got bromine. Again, double bond is between 2, 3. So this 2, 3, 6, 7, both are same. 4, 5, 6, 7, C, and then 8. So when I am saying that the groups are same, I mean is, now you look at this geometrical stereocenter. Do not go by the whatever groups they have. Zoom out of the question and apply a common sense that this is a geometrical stereocenter and this is geometrical stereocenter. It can be cis, it can be trans. Similarly, this can also be cis and this can also be trans. So let's say if this is cis and this is cis, then this is the first compound. Out of those 4, this is the first, this is one of them. If this is trans, then out of those 4, this is one of them. So generally what we say is 2 raised to the power 2, that is 4. But what I'm saying is, you are calculating one compound 2 times. How? Because if this is cis, then this can be cis, this can be trans also. So let's say if this one is cis, I'm using another pen to show this. If this one is cis, this can be trans also. So what other option you're having? If this is trans, this can be cis also. So when you consider this is cis, this can be cis trans. When this is trans, this can also be cis trans. So actually you are calculating all the possible combinations. But 2 3 can also, somebody is numbering from this side and saying it is 2 3, somebody is numbering from that side and saying it is 6 7, but this is the same position. So these two structures are same only. So why you are counting them 2 times? If how many students are present in this room, sir? Student 1, student 2. You are counting this student 2 times does not make the number of students in this class 4, because this is cis, this is trans. Somebody will say 2 3 is cis, somebody will say 6 7 is trans. If you number opposite side, this is the same option. So because of this, whenever groups are same, one is deleted. I mean, somebody gets, not always one, but somebody gets cancelled. So this is how you should approach such questions. So answer for this question will be, how many geometrical isomers you have? 3. A very beautiful and subtle logic. You can again revise and come back. Now this is why I have used this question, because this question came in 2024. Although this question was a modified question, it is having an optical stereo center also. So we'll be discussing this question, but after optical isomerism. But we will have to calculate geometrical isomers for them, not considering this optical stereo center. So this one I have discussed. How many geometrical isomers we had? 3. Moving ahead. Now this is a real question, JEE 2024, and you are supposed to calculate number of geometrical isomers given by the structure. Now again, that zoom out thing will help you here. If you will apply the formula in that question, if you apply the formula, with God's grace you will get answer also. But here if you apply the formula, you will get wrong answer. You will only get right answer with common sense. That's why I said apply common sense at first place, don't learn the formulas. Now actually, this is also a geometrical stereo center. Yes, sir. This is also a geometrical stereo center. Yes, sir. Because ends are also different. Ends are also different. This is also a geometrical stereo center. Ends are. So how many geometrical stereo centers we have? 3. But this is a symmetrical. You can number this compound from this side also, that side also, both is same. Such compounds are symmetrical. Let's see. 1 2 is having an alkene with H and D on one side. If you number from that side, okay, first let me finish numbering. 3 4 5 6 and 7. If you number from right side, how will you number? 1 2 3 4 5 6 and 7. See, 1 is having HD, 1 is having HD. 2 1 2 having double bond, 1 2 having double bond. Second carbon is having methyl, second carbon is having methyl. Third carbon is CH2, third carbon is CH2. Fourth carbon is obviously the common. So when a structure becomes symmetrical, when you can number from this side also and this side also, both are symmetrical. So in such cases, you keep calculating one thing 2 times. So somebody gets cancelled. So what you should do? Zoom out. Okay, sir, zoomed out. Don't see the group. Just see them as a unit. So let's say this is one stereo center. Take it as a unit. This is one stereo center. This fourth one. Having 2 groups. What are these? Methyl and hydrogen. This is methyl, and because it has nothing, so it will be CH, because carbon is tetravalent. So methyl and hydrogen. Now if you just look at the 2 groups which are attached to this carbon, just pay attention and watch closely to the groups attached. Now if you just see, it is connected with this, on this side it is connected with 1 carbon, 2 carbon and a double bonded carbon. Yes, that double bonded carbon is itself having this HD and can show geometrical isomerism. But what I'm trying to show you is this is 1 2 3 carbon with double bond on these carbon and also a methyl branch over here. Similarly, if you go to this side, this is one carbon, second carbon, and third carbon. The same structure, one carbon, second carbon, and the third carbon. The same structure with such HDs over here and methyl over here. So what I'm trying to tell you is these two groups are structurally same. These two groups are structurally same. Look at them. 1, 2, 3, 1, 2, 3. So what I'm trying to tell you is you have considered this as a geometrical stereocenter. Okay, you have not done incorrectly because this is different, this is different. But this carbon of this middle stereocenter, this carbon of the middle stereocenter, if both these groups have got same type of geometrical isomerism, like for example, I'm again drawing this but not showing that those bulky groups, but showing them as a collective unit, that this is Me and this is H. So if these collective groups, if this is cis and this is cis, remember this may be cis, this may be trans, this may be cis, this may be trans, anything. But if they are of same geometrical stereo configuration, then this carbon will fail. It cannot show geometrical isomerism, because in order to show geometrical isomerism, even my two bonds will be different and this center's two bonds will also be different. This center's two bonds are now same. So when you both will have same, whatever you may have, you may even have cis. So this will be one form. You may even have trans. But if you both are same, then this cannot show geometrical isomerism, as in you will not say H on this side, H on this side, because these structures have lost the battle. So once you apply the formula, it will be counting all the permutations and combinations. But actually, when their geometrical isomerism are coming out to be same, it is not, this one is not showing geometry. This is only this structure. So this is one structure. This is another possibility. So this is the second isomer, although this is not geometrically active, this stereocenter, but this form and this form have same molecular formula, same structural formula, but different 3D orientation. So they are satisfying definition of geometrical isomerism, although this is not geometrical isomer. So in order to do such questions, you have to apply some common sense. Now this is difficult to do. I mean, a tricky part which if you practice, then only you should attempt in the examination. So because it is just previous year question, so I'm discussing this also. Now these are the two options. Now if they are different, let's say if this is cis and this is trans, or any other permutation combination, if they are different, then this geometrical stereocenter will become geometrically active. Like for example, using another pen for this, if these two are different, any can be any, because numbering can be done from this side also, this side also. So I'll not be specific that this, I'm just saying if it is cis and it is trans, I mean anyone can be anything because numbering is same. So you do not have to worry about them, but worry about them. As in, if you are cis, so maybe cis and hydrogen are on same side, or maybe cis and methyl are on same side. So this will give rise to structure number 3 and structure number 4. So we are focusing all our attention to the middle C double bonded C geometrical stereocenter, and just by looking at this center, we can definitely find what our answer is. So answer to this question will beautifully be 4. Moving forward. Yes. So now discussing about the distinction between cis and trans isomers. So first of all, we need to learn one term, that is what are diastereomers. So diastereomers are stereoisomers, but all those stereoisomers which are not mirror images of each other are called diastereomers. So obviously cis and trans are stereoisomers because they have same molecular formula, same structural formula, but different orientation in three-dimensional space, so satisfying the definition of a stereoisomers. But if you put a mirror, they are not mirror images of each other, so therefore they are also theoretically termed as diastereomers. And the distinction point is all structural and these diastereomers, although they have same functional group, so their chemical properties will be same, but they will definitely have different physical properties. Now let us list those physical properties, that how they are different. Like for example, first of all, let us talk about the physical property of the dipole moment, the polarity, the mu, remember, from positive to negative. So coming to this polarity, let's say everything is same. This carbon and chlorine, we know this is positive, so this is negative, so the polarity due to this polar bond will be from plus to minus, and for this the polarity will be again from plus to minus. So we can very well see this transform, the dipole moment will be cancelled, so it will definitely have a mu net, although it has got polar bonds, but its net dipole moment will be 0, and therefore this mu is less. Sir, why that is more? Because you will get a vector over here, you will get a vector over here, the x component will get cancelled, but definitely you will be getting a y component. So this cis isomer, we can mathematically definitely observe is it has got higher polarity, higher dipole moment, and whoever molecule has got higher polarity, the attraction between this cis isomer and its other molecule will be higher because polarity is higher, so intermolecular forces of attraction, that dipole attraction will be higher. So if two molecules are highly attracted towards each other, they will be having high boiling point. If they are polar, then like dissolves like, solubility, water is the universal solvent, so they will be getting more soluble in water. So cis isomer has more boiling point also and more solubility in water also. But talking about the melting point, to what state of matter we melt? Solid. And solid is governed by the solid lattice. Not only intermolecular forces, but the crystal structure also plays a very and huge role. So therefore, when talking about the melting point, we are not considering only the dipole moment because we melt a solid. And therefore, we have to check the symmetry and the packing of the solid. So have you seen, if I simply draw a trans isomer, I can draw a trans isomer like a chair. So have you seen many functions around you where there are lot of stacking of chair? That means chair can be more easily packed, while cis isomer is just like a boat, a tub. So have you seen a stack of tub to a larger or a higher extent, or a stack of chair? Definitely all of us have seen a very huge and large stack of chairs, but stack of tubs, few number of tubs can come over each other, but after a point of time they get disturbed. So which is a better symmetrically packed solid? Trans isomer. It's all a concept of solid states. Therefore, I'm giving you an example of stacking of chair and tubs. So with that example only you can observe, because trans isomers are more symmetric when we are forming a solid. So because they are more symmetric, their melting point of trans isomer is higher than that of cis, while in these physical properties, the cis isomer was having a larger physical property than the trans one. Now, one more thing, talking about the stability. Now, physical property I'm not talking of. Physically we have already spoken of, because who is the person who is having low boiling point gets converted into gas to a higher low boiling point, so it is easily converted to a gaseous state, so it is more volatile. And obviously this cis form is less volatile, so trans is more volatile and cis is less volatile. But these all are physical properties. Talking about the chemical properties, sir, you said they have same chemical properties. What I'm saying is they have same two people can have same chemical property, but the extent to which they react is different. So talking about the stability, obviously with respect to their chemical existence, there is a point of difference between the reactivity. So who is more relatively stable? Now, as I've taken that example of fumaric acid and maleic acid over here because it is also a factual science behind it. Like, we definitely know that fumaric is a trans isomer of this COOH unit, and this bulky COOH unit is far apart in trans isomer. So because it is far apart, the steric, the strain, the repulsion due to crowding is also called steric strain or van der Waals strain. So this van der Waals strain is very less, so obviously this is more stable. So about stability, trans isomer is relatively more stable, therefore it will be reacting to a much lesser rate of reaction, while the cis isomer will react fast because of this crowding it is not stable. So stability of cis isomer is less, and therefore it will show some more reactions also. Like for example, if you heat this cis and trans form of this butane dioic acid, then the maleic acid as in cis isomer easily undergoes dehydration. Sir, where it is getting dehydration and why it is getting dehydration? Because these bulky groups are closer to each other. So one will release OH, the other person will release H. Ultimately, they will release a water molecule, and once water molecule is released, two acids form acid anhydride. So a cyclic acid anhydride is formed, while the trans isomer will not form any such anhydride. Moving forward, so let's try and decode this. Mu net equals to 0, that means it should have some dipole moment. JEE means 2014 question. Let's decode this. Now what I'm saying is, do not blindly go to the para side of any isomer, because definitely we will have a conclusion that sir, this is a carbon, that is chlorine, so this is delta positive, this is delta negative, so dipole moment will be like this and this, because such questions are very easy to trick you. I'm not at all saying that's definitely just like the trans form, because this para is also coming opposites to each other. So here also net dipole moment will be 0. Similarly, for this carbon, because as per VSEPR theory, this carbon is linear because forming two sigma bonds. So for this carbon also, dipole moment is on this side and on this side, and because it is exactly linear, so here also mu net is 0. I do not have any problem with this. But even JEE wanted to check your VSEPR chemical bonding logic, that because this oxygen, if you, although I have made this question like this, in your examination paper it was given OH. If you not think about the geometry of OH, what is the shape of OH? Sir, it's a bent shape molecule. So definitely this vector will be like this vector will be like this. That will be cancelled. But due to this is positive and this is negative. There will be one more vector which you are not sure, this is minus, this is plus. Although this direction is also almost opposite to each other, but in benzene, when oxygen is bent, so it can be, I mean, I'm oxygen, I'm bent with respect to ring and with respect to my hydrogen, but I can align myself in all of the 3D geometry. So we cannot be sure about this oxygen, that whether this is exactly cancelled or not. Although it will, because this is in this direction, this O bond H dipole is this direction, so they will be cancelling out each other, some components, but all components will be cancelled, we are not sure. So this will definitely have some mu, and similarly this will also definitely have some mu. You can only be sure that mu net is 0 once you are sure about the symmetrical structure, because this, although this is also a group, but C triple bonded N is a linear shaped molecule, so this will definitely get cancelled because this carbon will be in plane with this benzene ring and with the nitrogen also. So a very beautiful question to check your logic of dipole moment and jumping directly to optical isomers. Now, what are optical isomers, sir? They are also stereoisomers, so they have the same molecular formula, same structural formula. But what do they differ in? They differ in their ability to rotate the plane of a polarized light. Now, sir, what is this polarized light? So, any source you have, any light source will give, obviously that light source will specifically give you a radiation, an electromagnetic radiation that is of some particular wavelength and frequency. So that monochromatic light that you will be getting from your light source, it will be if you light a bulb in a room, it will be giving light in all possible directions. So it is a non-polarized light. That's why all direction is shown with this picture. Now, there is a apparatus, there is a instrument called Nicol prism having very small pores. So when light pass through n number of small pores that is present in Nicol prism, only one directional light can pass through it. So after passing through Nicol prism, that non-polarized light attains a specific direction and is termed as a polarized light. So what will be the plane of that polarized light? Sir, this perpendicular portion. So this will become the plane of that polarized light, because that light is now on a single direction. Now, when this polarized light is passed through a solution, obviously we are learning organic chemistry, so we will be putting only organic compounds in that particular solution. Now, if it is passing through that particular solution, and if that particular solution has a capability of optically changing the direction of light, then obviously the plane of light will also get rotated. And if this organic compound has the capacity to rotate the plane of this polarized light, then this optically active compound will be termed as optically active. And whether a compound is optically active or not, it can only be checked using this experiment. It is done in an apparatus, and the apparatus is called a polarimeter. So this is the working principle of a polarimeter. And if an organic compound is having the ability to rotate the plane of a polarized light, then only that particular compound is called an optically active compound. And what are the two possibilities? Sir, if it is optically active, it will rotate the light in clockwise direction. Then it is called if this optically active compound is rotating the plane of polarized light in clockwise direction, so it is termed as a dextro-rotatory optically active compound, D form, or some people represent it as with a plus sign, or you can rotate it in anti-clockwise direction. Then it is called as a levorotatory compound, or L form, or represented with a negative sign. Now, sir, if any organic compound is not at all rotating the plane of polarized light, then it is optically inactive. Now, if my optical activity is high, then the angle with which I will be rotating the plane of polarized light will be larger. But all these data can only be determined through experiment. So we have done all those experiments, and after doing all those experiments, we have segregated all those organic compounds in nature. And all those organic compounds, when we have observed those organic compounds, we have found a specific center in all the molecules which were having the ability to rotate the light of the plane of polarized light. So in a nutshell, all optically active compound was observed that they had a center because of which they were having an asymmetry. Asymmetry as in, when you are a light and you are falling on me, because of that asymmetric center, a center which is not having any sort of symmetry. So if I'm inclined, let's say this way, so I'll be entertaining the light and directing that light to that particular direction. And my isomer, as in my brother, having same molecular formula, same structural formula, but the only difference of orientation in three-dimensional space, he will be receiving that same light and directing that light in the opposite direction. So one will be dextro-rotatory, or on one side, and the other one will be levorotatory, that is on the other side. And those particular stereo centers are observed statistically and named as optical stereo center. So the famous example of optical stereocenter which we have and we find in the question that we encounter in our competitive examination, there are n number of optical stereocenter. But the most famous optical stereocenter for organic chemistry for JEE mains is a chiral carbon. Now, sir, what is a chiral carbon? A chiral carbon which is forming 4 sigma bonds with different substituted atoms. Now, if I am optically active, how you will determine to what extent I am optically active? By calculating, experimentally calculating the value of alpha. This value of alpha depends on the on the frequency and wavelength of light, and at a particular temperature, what particular temperature this concentration is taken. So although these for mains you do not have to know such things, but this common sense you should know that if in this solution only one type of that optical isomer is present, then 100% whatever the rotation will be happening to the plane of polarized light will be termed as the specific rotation. But in life everything is not pure, so if you have used that organic compound but it is not 100%, so the angle with which you will be observing it may be different as well. So this alpha is statistically equal to the theta, which is the observed rotation in any actual particular case, the actual rotation, upon what is the concentration, because if you take more of the organic compound, the concentration will also decide to what extent the plane of polarized light is getting, to what angle it is getting deflected. Now, it also depends upon the length of polarimeter. So this formula is specific rotation is equal to observed rotation upon concentration into length. Although, sir, we are asked a question although this is an advanced topic where there are some questions which have played this with logic as well. But for us, we should know what is optical purity, because this is a common sense. There are two brothers. One has the ability to rotate light in clockwise direction. Other has the ability to rotate light in anti-clockwise direction. If at all they are optically active. And those isomers are termed as optical isomers. Now, in a specific case, like for example, this is a JEE mains question 2022. What conclusion we have to draw from the previous slide is, let's say the question says, optical activity of an enantiomeric mixture. If you have mixture of the plus and the minus, as in if you have mixture of both the isomers, the optical isomers are also termed as enantiomers. The plus and minus, if both are present, then plus and minus, the optical isomers are also termed as enantiomers. So if you have an enantiomeric mixture, you do not know one is dextrorotatory, another is levorotatory. We know this. Let's say one rotates the light in plus 30 degree, because this is saying the specific rotation is plus 30 degree. That means if you take just the dextrorotatory isomer, it will be rotating the light with 30 degree plus 30 degree angle. If only levorotatory would have been present, it will be rotating the light in exactly minus 30 degree. But as of now, what is the observed rotation? It is 12.6 degree. So can you tell me the optical purity? Yes. With logic, with common sense only, you can predict that this optical purity will be what theta you are observing upon that alpha, which was the specific rotation, if one isomer would have been present in 200. So you tell me, if only the dextro, the positive one, would have been there, what degree it would have rotated the plane of polarized at 30 degree. But because of presence of minus also, some plus, if there are 100 brothers, out of which 50 are pushing forward and 50 are pushing backward, where the car will go? Nowhere. But here the car actually, it is getting rotated by what? By 12.6 degree. So if you take the percent, the ratio, and multiply it by 100, you will get what purity of the dextro isomer, that is dextro-rotatory optically active compound, is present. So if you will solve that, I guess you will get 42% as your answer. So moving forward, let us just list what are the conditions for any compound to be optically active. So the primary condition is the compound must contain an optical stereocenter, a center that is asymmetric, which do not have any element of symmetry. There are, again I'm telling you, there are many examples. Advanced ask so many stereocenters, optical stereocenters, but for mains per se, we just need to know this one most important stereocenter, which is a chiral carbon. Now what's a chiral carbon? It's an sp3 hybridized carbon with all sigma bonds that are differently substituted. Now when you have this asymmetric center, then obviously, sir, now because these two, for example, this is a famous example of an optically active compound, which is lactic acid, the general name. The IUPAC name is 2-hydroxypropanoic acid. Obviously we can draw the structure. Now if we closely look at this middle carbon, this has 4 sigma bonds and all the 4 sigma bonds are differently substituted. But now if you'll ask, sir, this will have two compounds, that will be constituting of two compounds in nature, actually existing different two compounds in nature, both having same molecular formula, same structural formula, but the only difference they have is their ability to rotate plane of polarized light. Then how come we can draw them? Because a tetrahedral carbon, obviously that geometry will be different, but tetrahedral only we cannot draw 3D in 2D. We can draw the wedge dash projection showing the tetrahedral carbon, but still this was solved, this problem was solved by the scientist, and he gave a projection formula to show a tetrahedral carbon who is optically active, and this projection formula is called a Fisher projection formula. How it is drawn? It is simply said that you draw the chiral carbon like a plus. Let's say this is that chiral carbon of that lactic acid. So, and try to draw the main chain on the vertical line. What is the main chain? So COOH, C and CH3, because that will be the main chain. So this will be COOH. This is that chiral carbon, the middle one, and the last main chain carbon is CH3. Now, what are the groups, sir? OH and H. So let us draw OH on one side, H on the other side. This becomes one of the optical isomer. And what about its other isomeric pair? Let's say this form is dextrorotatory. Whether an optically compound is dextrorotatory and levorotatory can only be determined through experiment. There is no way for us in order to determine the type of optical activity. It can only be determined through polarimeter. So these all are observational facts which we are learning now. So, sir, then how can we draw? So Newman said, so Fisher said, you take a mirror, okay, to take in a mirror and draw its mirror image. So let us draw. COOH CH3 will be as it is. So COOH CH3 will be as it is, but mirror image of this OH will be coming on this side, and mirror image of this farther H will be going to the farther end, that is this H. Now, if we just put this molecule over this molecule, then this H is not superimposing this OH. So this becomes a non-superimposable mirror image, which is in the short I've written NSMI. So the condition number 2 is when you draw its Fisher projection formula, it should be a non-superimposable mirror image of each other. And the non-superimposable mirror image isomers are obviously optical isomers, but they are also termed as enantiomers or simply enantiomeric pair. Now, obviously, when I'm saying that chiral carbon is an asymmetric carbon, so it should not have any element of symmetry. Sir, what are the element of symmetry? For those elements of symmetry, for knowing them in depth and detail is definitely important, but for advanced questions, for mains, your basic common sense will work. Now, because solid state also has been removed from JEE mains syllabus, so actually this logic helps in solid state also, and obviously in good questions of optical isomerism also. So I'm just giving you a brief. Further we'll be doing for advanced, but I've just given you this brief that the element of symmetry, actually there are 23 element of symmetry in total. They are basically of 3 types: the center of symmetry, the plane of symmetry, as in a plane by which along a plane, if you cut a molecule, it should be broken into two equal halves. It should be exactly symmetric. Plane of symmetry are further of two types, rectangular plane of symmetry or body diagonal plane of symmetry. Now, there is an excess of symmetry as in there is alternating excess of symmetry. It is there is existence of twofold excess of symmetry, threefold excess of symmetry, fourfold excess of symmetry. So all these this is all actually very important, but for advanced questions, and this is actually a detail of solid state. Solid state is even not there in JEE Main, so I'm just giving you a brief about it. But moving ahead now, moving to the actual side of optical isomerism, which is the questions. What type of questions we get now? For example, over here we have to select that which of the following do not show stereoisomerism. This is a JEE Mains 2021 question, so these type of questions you should practice. So practicing and learning theory just relating to them. Now let us draw them. 3 ethyl hexene. Hex is a 6 carbon chain, 3 4 5 6. Now in the third position, as in carbon 1 2 3 4 5 6, in the third, between third and fourth carbon, I have drawn the double bond. Now 3 is having an ethyl group. Okay sir, so stereoisomerism, that means you have to check geometrical also and optical also. So let us check geometrical isomerism. So no sir, this carbon, this is an ethyl group, this is an ethyl group, so one end is same, so it cannot show geometrical isomerism. Because you are having no carbon which is having all the 4 bonds different. How to check that? Just draw. If I'm having more than 1 hydrogens, then obviously I cannot have 4 different substituted bonds. Obviously you can see it as CH3, CH2, alkene. I need an sp3 hybridized carbon, so they both are already gone. So this is also CH2, CH3. So it cannot show OI also. No geometrical isomerism, no optical isomerism. So obviously we got our answer, but because we are practicing, so let us check what are the stereo centers present in these options. Now again, for hex 1-ene, okay, let us try hex 1-ene as in 6 carbons, 2 3 4 5 6, double bond here, okay, because it is 1-ene. Now 3 methyl, so 3 methyl. So obviously it can also not show geometrical isomerism because ends are same, but this carbon becomes a stereo center. Why? Because one is methyl, one is a 3 carbon chain, one is a double bonded chain, and one will be hydrogen. So it contains an optical stereo center, so not an answer. Now obviously not an answer. Now hex 3-ene, okay sir, hex 3-ene as in 1 2 3 4 5 6, here 3 4 dimethyl, so 3 methyl 4 methyl. Obviously yes, definitely it can show geometrical isomerism. I cannot see any optical isomerism because there is no chiral carbon, but geometrical isomerism it can show. Moving ahead, then again hex 1-ene, so 1 2 and 4th carbon, as in this one is having methyl, so definitely you can see that this is chiral because one will be hydrogen. So these all are basic questions that means normally ask many number of times. Now moving ahead, observe the structure of the molecule. Okay, observing the total number of structures which possess, okay, you have to again tell asymmetric center as in chiral carbon centers. Now so what about this sir? Obviously this is CH2, CH3, CH3, so not bothering, just bothering about this one. So let us bother about this one. Yes sir, this is 1 carbon, this is 2 carbon, this is hydrogen, that is OH. So yes, it is a chiral carbon, so option 1. Now over here, no sir, this is CH2 and no sp3, so no chiral carbon. Yes, let us observe this carbon NH2C. Yes, this will become, because there will be an hydrogen, so this will become a chiral carbon. A very easy question, just by observation you can do. Now what about this sir? No sp3 hybridized carbon only, so not possible. What about this one sir? This carbon, no, with this carbon it has 2 methyl group, so no, cancel. What about this one? Yes sir, this carbon is having this 3 carbon chain, a carbon attached with OH, a carbon, normal carbon, no OH, and one will be hydrogen, so it will be a chiral carbon. Definitely yes. Obviously I guess this is one more chiral carbon, but obviously because of presence of 1 chiral carbon it has become a chiral molecule, so obviously it is having one more. Even I guess this will also be a chiral carbon. So obviously the molecule is chiral, so you just have to tell the following structure how many are chiral, how many the total number of structures compound. Okay, you are not the total number of chiral carbons, just the structures. So how many having chiral structures? 1, 2 and 3. So your answer will be 3. Moving ahead. Now again the same type of questions every year this come. Now total number of chiral carbons in the given compound. Now okay, talking about the first structure. Now sir, element of symmetry we do not even have to know even a bit. No, through basic plane, if you can find a plane by which you can cut a molecule and it is divided into equal halves which are mirror images, then it is symmetric. So that is definitely a definition of plane of symmetry. Now but whenever a cycle is there, so can you cut this cycle in two halves? Sir, if it is broken like this, obviously above and below are not same. So this definitely has no element of symmetry. And because there is no element of symmetry, therefore, yes, it is chiral. Sir, you are just looking at the molecule. Yes, because whenever cyclic structure comes, the whole structure can also tell you that whether a molecule is chiral or not. Why? Because okay, one more optical stereo center, because of that you should know. Now what is it? Cumulated dienes. This one, because some questions determining the chiral carbon are present, so I'm discussing this one more chiral carbon with you. One more optical stereo center with you. One of the example of optical stereo center is definitely a chiral carbon. One more example of optical stereo center is a cumulated diene. But what type of cumulated diene? Even number of alkenes. Sir, what is cumulated diene? Whenever two alkenes are side by side, it is a cumulated diene. And if it is even number of pi bonds cumulated, then it is an optical stereo center. If you get an odd number of alkenes cumulated together, then that is not an optical stereo center. So we have to learn it. If you want, you can, but I'm explaining it because this is actually very important for advance, and mains also ask them a few times, because it actually gives you the picture that over in a molecule also you should see some symmetry, elements of symmetry. That's why. Now sir, obviously we can draw this sigma bonds, already drawn. I've done this for you to save some time. Now what about this pi bond? I just use a laser so that I may not disturb your picture. Now sir, what about this pi bond? Let's say the sigma bond is forming along x-axis, right? So this will be py and this is also py. So this is a sideways overlapping of the py orbital. Done. Now because for the middle carbon you have, this is x-axis, this is y-axis, so what orbital is available to form the other pi bonds are obviously the pz orbital. If this is x-axis, this is y-axis, then this is xy plane, the board is our xy plane, so z-axis will be up and down, coming out of the plane and going inside the plane. So that's why I've drawn this yellow color lobe that is having a sideways overlap. Now, can you tell me what is the plane at which these two hydrogens are resting? Yes, sir, definitely. Because through VSEPR theory, we know this carbon is sp2 hybridized, so it should be trigonal planar. So this is the one sigma bond, this single bond. What about the other two bonds, the triangle of the hydrogen? Sir, 1 and 1. Sir, but how you have drawn them? Because this was, remember, this is x-axis, this is y-axis. So the electron crowd is there in the y-axis. If this carbon needs to form a triangle, let's say this is that carbon, it has to form a triangle with what? With two hydrogens. So one hydrogen will be going to upside, one hydrogen will be going to downside. If this is x-axis, this is y-axis. Now, if there are electron lobe, then won't you feel that sigma bond will feel lot of repulsion from the py orbitals? Yes. So if you want to form a triangle, why you are making that triangle in xy plane? Make them in the xz plane. As in, this is carbon, this is one hydrogen coming out of the plane of paper, and one hydrogen going inside the plane of paper. So this triangle will be on this xz plane. So therefore, the hydrogens I have drawn, because this is xy plane, so I cannot put one hydrogen over here because it will be getting so much of repulsion from the pi electron cloud. So instead, it should go to the outside the plane and inside the plane. Similarly, what about this green, this the last carbon? Sir, because pi cloud is there in the XZ plane, coming out and inside the plane of paper. So now this board plane is available. So this one hydrogen and this other hydrogen is in the same plane. So this triangle is in the same plane. So I'm just giving you a picture to understand this. Let's say these two hydrogens are there in this plane only. This plane as in the plane of the board. So this is carbon, this is one hydrogen, this is another hydrogen on the plane of the board. But this is XZ. So what about this hydrogen? One hydrogen is over here, one hydrogen is over, one coming outside the plane of paper, one getting inside. So this is the plane of first structure and this becomes the plane of the second structure. Now you tell me, are these hydrogens coming in the same plane? No, sir. One hydrogen is where? Let me rest this. One hydrogen is this and this. Other hydrogen is this one and that one. So these four hydrogens are not symmetric. They are not coming in same plane. So can you find any plane if you cut this molecule, it will be symmetric? No. So there is no one center that is creating that asymmetry. The whole system is creating such an environment that even if these all are hydrogens, four hydrogens, but these four hydrogens are also not coming in a single plane. They are non-planar and therefore you cannot find any element of symmetry. So if no element of symmetry is there, then this whole system becomes a chiral center. So this whole system becomes a asymmetric center. I'm sorry, chiral word is used for an sp3 hybridized carbon, which is one of the example of optical stereocenter. So one more of example of optical stereocenter becomes an cumulated diene with even number of pi bonds, and obviously it will show optical isomerism. Now, sir, because we know this is pi and pi, and through general organic chemistry, through geometrical isomerism, you know that if this is a pi bond and let's say this is a ring, so ring can also form a restricted rotation, pi can also form a restricted rotation. So a cyclic ring directly connected with a double bonded carbon can also be a optical stereocenter, because that is also an even condition, cycle and a pi bond. But when it goes to odd number, what happens is, let's say this is x-axis, so this is py is used, so here pz is used, then the third one again py is used. So sir, if py is used, then hydrogen will be lying on outside the plane and inside the plane, outside the plane and inside the plane. So over here also outside the plane and inside the plane. Now all these hydrogen are coming in this plane only, in the xz plane. So because they are, so I can definitely cut this molecule into two halves, yes, and then it will become symmetric. So this is a symmetric center. So this is not a chiral center for us. But if these groups are different, for example, these groups are same. So I mean, for geometrical stereocenter it is, because it is a restricted rotation. Odd number of restricted rotation is a geometrical stereocenter. But when you will see geometric isomer, when these groups are also different, because here these groups have hydrogen only. Let's say if you have A over here and B over here, A over here and B over here, so it will again become cis isomer. I'm intentionally using laser because I'll be giving you these notes, but this is a geometrical stereocenter. It will only show geometrical isomerism when groups attached are also different. Now, why I'm telling you this is, for the whole molecule also, you have to sometimes see that whether it is having any element of symmetry or not. The most famous example of element of symmetry which JEE mains asks is a plane of symmetry. Now, after investing so much of time in this question, let us again go to this question. Now, because we know that when a cycle or something like cumulated system comes, we see element of symmetry in the whole molecule, not just the chiral carbon. So that's why I'm not searching a chiral carbon, I'm looking into the whole molecule, because carbon when forms a cycle is generally when all the carbon can come in a single plane. So let's say this is a plane. Can you find any plane of symmetry? No, sir. It cannot be distributed by a plane which divides it into equal halves? No. So because it is having no element of symmetry, so the whole molecule can become asymmetric, and therefore the whole molecule can become a chiral or an optically active molecule. So yes, this is an example. So this is one example which you will count as this is a chiral compound. Now, what about this one? Okay, in this one you can also see chiral carbon. How, sir? We'll just have a look. Can you watch this carbon? Yes, sir. What about this carbon, sir? Sir, one OH, one bond carbon containing O. This is a different environment, although this is also containing carbon with an O, but the environment over here of 2 benzene and over there of 2 are different. So this becomes, and one would definitely be H. So this becomes a chiral carbon. So this is optically active because of presence of chiral carbon. This is optically active because of presence of no element of symmetry. Now, what about this? Now, this is again a Fischer projection. And if nothing is written, so this carbon will be having one hydrogen this side and one hydrogen this side. Now, if you think of a plane, can you think of a plane? Yes, sir. What is the plane? You cut this molecule along this plane. Upside, downside, it is just symmetric. So again, it is because it is containing a plane of symmetry. So it is not chiral. Similarly, let us cut this molecule along this plane. When you find a cyclic structure, start looking for a plane. Do not only see a chiral carbon. The same logic which I'm telling you. Now, what does dash represent? That it is coming out of the plane. Inside the plane. What does dash represent? Coming out of the plane. So dash is inside, wedge is outside. So if you cut this molecule along this plane, OH, OH, mirror. OH upside, mirror. OH upside, mirror. So again, I got a plane of symmetry. So because I got a plane of symmetry, so this is also optically inactive. Obviously, clearly over here, I can see this is a plane of symmetry. So cutting the molecule into, sir, but this carbon is trigonal planar. So over here, hydrogen will be like this and this. So at the pi cloud, you cut along that pi cloud. That pi cloud will be coming like this. So cut along that. Obviously, these questions are good. That's why I've told you, you have to check whenever cyclic structures or some structures are given, you have to see to the whole molecule whether it is having some element of symmetry or not. Moving ahead. So, answer for this question is 1, 2, just 2. So, answer is 2. Good question. Moving ahead. Now, this I have already told you. Now, again, the same type of question, but those knowledge are important. Now, what about this, sir? This is a chiral carbon I see. COO, C, CH3 and 1 will be H. So because it is having a chiral carbon, so definitely it will be a chiral compound. Definitely over here, I can see an element of symmetry. So whenever cyclic structure you find, just check for the element of symmetry also, then go for. So because there is element of symmetry, so it is not chiral. What about this one? I'm using another pen. So CH3, no. Yes, this one is ethyl group, one is COOH, one is NH2. So this is a chiral molecule. So yes, this is an answer. No, okay, this H, CH3, but both are ethyl. So no, this is also not chiral. And hydrogen, you just see if two anything same are present, then it cannot be chiral. So no. What about this one? Yes, sir. HI, this methyl, and this C and N group. So this is chiral. So an answer for us. No, yes. HOH, ethyl and carbon and OH. So this is chiral. So an answer for us. Now, this is H. So this can also be chiral. This can also be chiral. But for some questions, I'm also telling you, even if there is, this is a chiral molecule, no doubt. So this is a chiral molecule. So this is an answer for you. So answer is 1, 2, 3, 4 and 5. So answer is 5 for you. But what extra because mains has this also. With this question also, you can see, although this is CH3 and C2H5, the ends are not same. But what I'm saying is, even a molecule contain chiral carbon, then is it compulsory it will be optically active? As a compound it will be optically active? No, because optical inactivity can be imposed also. Sir, how it is imposed? Through external compensation, or internal compensation. For example, there are active species, active centers, but if there's a car, if 10 people are pushing the car from left side and 10 people are pushing the car from the right side, there are people who are investing, who are pushing, who are rotating, trying to rotate the plane of polarized light. But if equal number of optically active centers are doing the same thing, then overall the car will not go anywhere. Overall the plane of polarized light will not change. Overall the light will not get rotated, is what I'm telling you. That even if optically active centers are present, then still the overall mixture can become optically inactive. How? By external compensation. As I've already told you, there are optical isomers, so there will be some dextro form also, there will be some levo form also. You add 50% of both dextro and levo form, what you will get? Sir, it will try to rotate clockwise, it will try to rotate anti-clockwise. Overall light will not rotate because both are present in equal amount, 50%. So if molar ratio of both are same, then optical inactivity can be forced. And such an optical inactive mixture is also called racemic mixture. Now, one more point. Over here also you can see I have drawn the Fischer projection of this alpha amino acid, a polymer. I mean, when the protein present in our body, when it get hydrolyzed, this is the monomer that we get. So one more biomolecule logic I'm telling you over here only. It is dextro or levo, cannot be determined. But yes, if it is dextro, it will be levo. If it is levo, it will be dextro. This I'm sure of. If I know the optical activity of that one, this will be exact opposite. But it is dextro or levo can only be determined through experiment. But one configurational knowledge you should have. What is that? The configurational knowledge is when you generally in the Fischer projection, you draw the main chain in the vertical line. In the horizontal line, you draw the other groups. When the horizontally present functional group is on the right side, this configuration is called D configuration. This is the dextro is represented by small d or plus sign. Levo is represented by small l or minus sign. The rotation is represented by capital small d and capital L, preferably plus and minus. This capital D is nothing to do with the dextro and levo. Whether it is dextro rotatory, levo rotatory, we do not know that. That can only be known through experiment. But this capital D configuration represents that even if there is a chiral carbon, then the last, because there is only one chiral carbon in biomolecules, you will get so many number of carbons. So the last carbon should have the horizontally present functional group on the right side, then that configuration is called D form. And if that functional group is on the left side, then that configuration is called the capital L form. They are structural configuration in a Newman project, in a Fischer projection, not their optical activity. Students get confused. That's why I'm separately telling you this. Now, optical inactivity can also be forced internally. How? If a molecule contains more than one chiral carbon, like over here, I'm having two chiral carbons, this one and this one. But if the molecule only is containing an element of symmetry, like you can divide this molecule along this. So because of presence of this, what is it? Plane of symmetry. The overall molecule becomes optically inactive, and such an optically inactive form which has killed its own optical activity, because if let's say this was trying to rotate light clockwise, so this will try to rotate light anti-clockwise. Just an example. So overall light will not rotate, and such a form is known as Meso form. Moving ahead to more questions now. Again the similar type of question. You have to tell the number of optically active. Again the same type of question. Sir, element of symmetry. So because of element of symmetry, it is optically inactive. The next one. Sir, definitely if you can cut this along this, sir, but this is tetrahedral. Tetrahedral also is every bond is at 109 degree 28 minute. So although this carbon is chiral, this carbon is chiral, this carbon is chiral, but if you cut molecule along this plane, but then one of the configuration, you will definitely get a Meso form, and that Meso form will make this an optically inactive mixture. Inactive form as in you can, I mean, without even drawing the Fischer projection, because of this presence of element of symmetry, which is plane of symmetry, you can predict that this is also an optically inactive compound. Now, what about this? Sir, there is no chiral carbon, so this is also optically inactive. There is a chiral carbon over here, so it is the first option. No, 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 no. This is CH3, so 2 CH3 on this carbon, so this also becomes optically inactive. Rest are just CH2. So what is your answer? Only one, sir. Moving ahead. Piece of cake. Now, you have to tell the number of chiral carbon present in this molecule. I am giving you all the questions so that you may have some confidence, or because students fear from optical isomerism. Advanced optical isomerism is, yes, a piece of cake. You have to invest a lot of time and practice to master that. But mains, never leave those questions, because they may appear very, dramatic, but let us attempt it. Number of chiral carbon present. Okay, sir. Is this chiral? Yes, sir, definitely chiral, because all 4 bonds are different. No, 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 because there is no sp3. Now, here I've again got an sp3 system. Let us check. One is attached with carbon of a ring, one is O, one is carbon of some bigger ring, and one definitely will be H. So this is also chiral. All sp2, this is sp3 but hydrogen, so reject. Coming over here, this is attached with nitrogen with a carbon with another carbon. This carbon is CH2 and this carbon is a chiral carbon. So these two carbons are different. One will be H. So yes, this is also an optical stereocenter. Moving ahead. Just look at the environment. Coming to this carbon, this is connected to CH2, which is attached to a nitrogen. So one bond is that. What about the other bond? Other bond is connected with a C, which is not H2, it is H. So this is different, this is different. This is CH2 connected with some C of different genre. So obviously this bond is different, this bond is different, this bond is different, although all are C, but I'm looking into their surrounding also. And one will definitely be H. So this is also chiral. Devote some time, you will also get it. Now, this is the, what about this carbon? One is H, one is this chiral carbon, which is obviously different. One is CH2, one is CH2, but this CH2 connected with an N, and this CH2 is connected with a CH3. So environment is different. So even just do not go to next carbon. If it is a carbon, look at the environment of that carbon, as in the other bonds that it is making. So how many chiral carbons you see? Sir, 1, 2, 3, 4, 5. So I have 5 carbon. Very beautiful question. Now, number of chiral carbon atoms. Moving ahead. Number of optical. Okay, now you have to do maths. That was asking number of chiral carbon. Now this JEE mains question is asking number of optical isomers. Sir, if I find one chiral, so in geometrical isomers, although I have not given you formula, we do not even use the formula. So, but yes, common sense we can use. If there is one stereocenter, isomers will be dextro and levo. So 2 raised to the power n will be your total number of optical isomers. And we just have to calculate the chiral carbons. So calculating those chiral carbon, this is CH2, CH2, CH2. This is a carbon which is chiral. Look at its environment. This is also chiral. So this is also chiral. This is also chiral. And this is also chiral. So again, how many chiral carbons we have? 5. So 2 raised to the power 5 is, I guess it is 32. Now, moving ahead. Number of stereoisomers possible for 1, 2 dimethyl cyclopropane. Now, this is a good question. A basic common sense. Because it is asking stereoisomers, not only optical isomers. So, sir, stereoisomers. Okay, let us check. Cyclopropane is this. Let's say this is 1, this is 2. Sir, we know that a cyclic ring is also a geometrical stereocenter, but it has to have different groups also. That's why I'm drawing like this to remember the upside downside thing. Now, let's say this is 1, this is 2. So methyl, methyl can come same side. So this is cis form. And obviously the methyl can also go in a trans phase. So this is trans form. But here we have just taken into consideration the optical isomerism. So there are 2 stereoisomers which are geometrical isomers, definitely. But now we have known the knowledge of optical isomerism. So let us check element of symmetry also. Sir, because it's a cycle, so why check chiral carbon? Let us check element of symmetry. Now, do you have any element of symmetry? Yes. If it is broken along this plane, it is symmetric about this plane. So because of presence of plane of symmetry, it is optically inactive. So it will just give you 1. That is this geometrical isomeric form. But this geometrical isomer do not have any element of symmetry. If you cut it along this, it is not getting cutted. So because it is having no element of symmetry, therefore I'm writing it, because this is a very good knowledge, people miss it. No element of symmetry. So therefore overall molecule is chiral. So chiral compound it is. When I'm saying compound, I'm not talking of chiral carbon. Overall molecule is asymmetric. Chiral has an asymmetric. Okay. So if molecule is asymmetric, then this molecule will be a chiral center producing two types of isomers, dextroisomer and levoisomer, rotating in clockwise and rotating in anti-clockwise, and they will be two different compounds. So first is this one, only this one, not any optical isomer of this, but this trans form will have two isomers in nature. So this will be compound number 2 and this will be compound number 3. A very beautiful question. So your answer will be 3. Moving forward. Now, let us, because this we have already discussed during geometrical isomerism, so let's try and I'll sip some water. Now, if this third bromine would not had been here, then if remove this bromine, if you already remember, then this was a symmetrical molecule. But because of the presence of this third bromine, it is not a symmetrical molecule, because now you are forced to just number this from one side. So this will be carbon number 1, 2, 3, 4, 5, 6, 7 and 8, and you cannot now number it from this side. So because now this compound has become unsymmetrical, so this 2, 3 will be always 2, 3. Like when this was not there, we were having such a case when the molecule was becoming symmetrical. So we were have to, out of those 4 isomers, one was getting repeated. So we were having 3 geometrical isomers. But now this will be cis trans, this will be cis trans. But on the contrary, icing on the cake will be this carbon is also a stereocenter, not a geometrical stereocenter but optical stereocenter. So this 4th carbon can even be dextrorotatory, it can even be levorotatory. So once when it is dextrorotatory, then what are the geometrical possibilities you have? This can be cis trans, this can be cis trans. So how many options you will get? 4. But once it is levorotatory, those 4 possible options will be coming again. For example, let's say if this is cis, then this can become cis also, trans also. Let's say if this is trans, then also this can become cis also, this can become trans also. So what are the possible number of geometrical isomers you have? 4. So those 4 possibilities will be existing when you have dextro form, and similarly it will also be existing when you have your levo form. So total stereoisomers will be 8. Moving forward. Now next question is still asking you that you have a molecular formula this, and now you have to select that out of which, out of these 4 options, which option has 4, which option has 2 chiral carbons. So you have to draw the structures. It is asking you butane, okay. Then in second position you have to take bromine. In second position you have to take deuterium. Deuterium is an isotope of hydrogen. So let us check what all are the chiral centers we have. Okay, we have only one chiral center, but the question is asking you, you should have 2 chiral center in which of the following. So obviously this is having 1 chiral center, so not an answer for us. Again, propane, I guess 3 carbon will not at all have 2 chiral carbons, but still let us attempt it. This is 2 is bromo, 1 is deuteriated, 2 is having a methyl. So here also you have just 1 chiral carbon, so not an answer. This one butane as in 4 carbons, second should have bromine, and third should have deuterium. Yes, now this is your chiral carbon and this is your chiral carbon, because you're having 2 chiral carbons, so this will be your answer. Now you can do such questions once you get confidence. So for confidence you have to revise this in n number of times. Moving ahead. Now, although this wedge dash and Fisher projection essentially per se is an advanced topic, but after 2016 I'll be giving you one question also of JEE mains only. Mains has also started asking very basic. I mean, these topics can go to a very good extent, but that is an advanced criteria. But for mains, you should actually not, you should know all the things. Do not know them in a very depth. Do not do very difficult questions. Those difficult questions you can definitely do, because that will give you confidence for your JEE advance. But for January JEE mains, you should just know all the concepts. So I'm giving you everything. So because we know a tetrahedral carbon is a three-dimensional structure, so that 3D structure cannot be drawn in a 2D pen and paper. So there are some projection formula which are given by various scientists. The very famous projection formula to represent a tetrahedral carbon is a wedge dash projection. We very well know what is wedge dash. If you do not know, I'm giving you all the basic. Out of those 4 carbons of a tetrahedral system, 2 comes in a plane and 1 group is out of the plane and 1 is inside the plane. This is the actual geometry of a tetrahedral system, as you know, through chemical bonding with bond angle 109 degree 28 minute. But in order to show that tetrahedral system, how we draw a wedge dash projection, 2 bonds on the plane. Wedge, solid wedge represents the group which is out of the plane, and dash represents that group which is present, which is going inside the plane. Now, there is one more projection formula, the Fisher projection. We have already seen in the previous slide. In Fisher projection, the vertical line represents those groups which are away from the viewer. So these vertical line are those groups which are away from you. If you are viewing it from the top, the vertical groups are going away from you and the horizontal groups are coming towards you. So you can even learn them with a dance: vertical away, horizontal towards you. So 1 and 3, 2, 1 and 2. So you can dance also that vertical is away from you and horizontal is towards you. And this logic is just that basic dance only. What I'm trying to tell you is, this is a wedge dash projection. How to convert this wedge dash into this this Fisher projection? Very easy. Sir, it is, students find it very difficult. You just have to set a right view angle. So just put your eye, let's say this is your eye, just put your eye from here. Sir, how to do it? Just go to that side. If you go to that side, what you will find is a wedge that is coming out of you, a dash that is coming this side. So this becomes your horizontal position. I mean, if you have to incline your view, your eye along this side in a 3D geometry, because you know this is out of the, this is coming out, this is going in, but this is for this plane. So you make an angle and watch this molecule through this side. So how you will be viewing it? This is going out, this is going in. Go from the side, this is going out of the plane, because you are now viewing it from that plane only. So one is out of the plane, one is inside the plane. So this is your horizontal position which is coming towards you. What was the horizontal line that was coming toward you? This one. And that is those 2 lines. Now if you're viewing it from this side, they will be going away from you. I hope you get that point. For example, I'm giving you an example also. For example, let's say I have some group A over here and B over here. So if you're viewing it from this side, this will be coming towards you. So if you project this wedge dash projection on a Fisher projection, this is coming towards you. So this will definitely be A and this will definitely be B, just like that. You just have to get the actual feeling of what this wedge dash projection is. So if this A and B, so that will become A and B. Now they are going away from you. So if you're viewing it from this side, this will be your top and this will be your bottom. So coming to the Fisher projection, this will be your top, this will be your bottom. It is just simple as that. Although we have Newman and Sawhorse projection also, but for them, those are advanced topic, but we will be covering them also, but for our conformational isomer, our last topic. Now, sir, what sort of question are asked over here? Now, because we know that tetrahedral carbon with all different groups is a asymmetric center. So whether a chiral carbon is dextrorotatory and levorotatory can only be determined through experiment. We already know this. But If at all, because it is asymmetric, let us assume, I'm giving you a common sense of why this theory is generated by our organic community, that let's say that molecule is receiving light, and who receives light? Those asymmetric groups. If you are receiving light, light is an electromagnetic radiation. Electron are dealt with the nucleus of the groups. Nucleus is represented by atomic number. That's why I told you while applying the CIP rule. While applying the CIP rule for deciding the priority when we were supposed to have EZ configuration in geometrical isomer, apply that same CIP rule in order to assign the priority of the 4 different groups of a tetrahedral carbon. Because if first is receiving the light, sending it to 2 and then 3 and then making the light rotate, then I do not know where the light will get rotated, dextro or levo. That can only be determined through experiment. But that priority will actually tell you if one is dextro, then the other will be levo. Or if one is having some configuration and other molecule is also having same configuration, then you can at least say that they are identical. I know this is not getting much digested inside your brain, so let me give you an example first. Now, to deal with the example, first we have to know the rule. There is a absolute configuration given by the scientist community, because again I'm telling you, whether a molecule is dextro-rotatory or levo-rotatory can only be determined through experiment. But what you can easily determine is if this molecule, this chiral center and this chiral center, whether they are same, you can at least identify this, that whether they are same or not. How? Theoretically. Theoretically how? Using this RS configuration rule. Or they are enantiomers, as in they are optical isomers. Or what with respect to one, how is the optical activity of the second? Same or different? That you can identify theoretically using RS configuration. What is it? Let's say you have a wedge dash projection formula. So first apply CIP rule on all the 4 different groups. So you will be having priority 1, 2, 3, 4, right? After that, bring the lowest priority group. That 4th group has to be on a wedge dash projection. It has to be on dash. Sir, how if it is not there in dash, then bring it to dash by even exchange. Sir, why even exchange? Because even exchange will make the activity, the optical tendency of the molecule same. Because this is a statistical observation which the rule, the community which has set the rule has given to all of us, because we need some theoretical knowledge also in order to at least identify that whether 2 compounds are same or they are different optically. So we have to learn this rule, which is saying the step 1 is you have to decide the priority by applying CIP rule. Then bring the lowest priority group to dash by even exchanges, because that will make the activity of the molecule same, not disturb it. And once it is done, now you will go from 1 to 2 to 3. Why I'm saying 1 to 2 to 3? Because sometimes if for going from 1 to 2, you have 2 possibilities. So you have to go from 1 to 2. How? So that after 2, 3 should come. And now if you are going clockwise, then the configuration is R, and if it is anti-clockwise, it is S. I'm not saying dextro or levo. Dextro or levo can only be determined through experiment. R does not mean it is dextro-rotatory. R means, let's say it has an optical activity X. So S will have opposite optical activity. This much we can be confident of. Now, if the projection formula is a Fisher projection formula, do the same. Apply CIP rule, assign 1, 2, 3, 4. Now bring the lowest priority group to bottom, because dash is bottom. So this you have to learn. How? By even exchanges. And then again from 1 to 2 to 3, if clockwise, so R, if anti-clockwise, so S. Sir, but give us some example. Obviously giving an example and a live example. This was a JEE main. When JEE mains used to be offline, this question came, and you expect a lot of question on this NTA. Generally, I mean, in the previous years it has not been as, but a high probable logic that you should know. Now, This 2016 question, sir, this is a Fisher projection. How to identify RS? I do not know it is dextro or levo. But first you tell me whether it has chiral carbon. Yes, sir. What are the chiral carbon? This is a chiral carbon. This is a chiral carbon. Okay. What else? First, what will be the numbering? So this is carbon number 1, 2, 3, 4. Okay. Because numbering, and you can obviously give the IUPAC name. Now, sir, because second carbon is also chiral, so let us assign RS configuration for second carbon first. So this is my second carbon. This is my second carbon. Now, this second carbon is attached with O, C, H and C. Just go to the atom to which directly it is attached and check its atomic number, the CIP rule. This is oxygen, so oxygen is most highest atomic number, most heavy nucleus, so this is priority 1. So this is carbon, this is also carbon tie. This carbon is attached with double bonded O and O, that means it is attached with 3O. So what arrow will come from here for the competition? O. What arrow this carbon will throw? It has further 3 bonds, Cl, C and H. It will throw an arrow of Cl. So here Cl is coming, here O is coming. Who won? Cl won, because Cl has higher heavy nucleus. So this becomes 2, so this becomes 3 and this becomes 4, because hydrogen is least prior. Now, sir, this is least prior. We have to bring the least priority group to bottom. How you will bring it to bottom? By even exchange. So these two are exchanged, because 4 you need at the bottom, but this will be odd exchange, will change the optical activity. So in order to make it just the same, I'm having one more exchange, that is called even exchange. That means first exchange you will do to bring this at bottom, and in order to make the activity same only, you will have one more exchange, so it will become an even exchange. So where I have reached for this second carbon, 1 is here, 3 is here, 4 is here and 2 is here. Now the rule says move from 1 to 2. Now I have said 1 to 2 to 3. Sometimes let's say if although it is not here, but let's say if 1 would be here and 2 would be here. So 1 here, 2 here. So you will move from 1 to 2 and next you will find 3. Else if 1 and 2 are just adjacent to each other, it is easy. But why I have said? Because you have to go from 1 to 2, so that if 2 is not coming directly, if it is opposite, we will find that case. So I'm going from 1 to 2. So how you're going? Sir, anti-clockwise. So this is S. So 2 is S. Sir, what about the other one? Let us go to the other one. Sir, it has one more chiral carbon, the third carbon. Now, let us draw that third chiral carbon. Sir, it is also having 4 groups, carbon, Cl, carbon H. So Cl is obviously of highest atomic number 1. Carbon, carbon tie. This carbon is having H, 3H. So it will have a first, obviously all H. So it will have next, it will bring into fight that from my side H is coming. From your side, who is coming? This carbon will say C, O, H. It will send O. So this 1. So this is 2. This is 3. This is 4. One exchange, because 4 I need here. Another exchange makes it even exchange. So 4 is here. 3 is here. 1 is here. 2 is here. Rule says 1 to 2. How I'm moving? Sir, clockwise. So it is R. So 3 is R. There were options given, so you will definitely take the option and you know that this is that configuration. Now, for Newman, for Fisher projection, we know how to assign RS now. For wedge dash, I am giving you all those examples which are JEE mains question. That was also JEE mains question. This is also JEE mains question, and this is the latest JEE mains question, 2022. Now, it is having 2 statements. Statement 1 is saying that this compound is optically active. It is optically active, then it should have some chiral carbon. So let us check. Obviously, you can see that this carbon is chiral. Obviously, it is quite clear that this carbon is chiral. Sir, how? 1 NO2, 1 H, 1 cis group, cis alkene. This is an alkene, a 3-carbon alkene. But what isomer? Sir, cis form. This is also an alkene, but trans form. Are cis and trans both same? No, sir. So this is also a very beautiful question in which they have written almost the the formula, the structure is same, but 3D orientation is different, and we know geometrical isomers have different physical properties. That means they are not same group, they are different groups. So this is cis and this is trans. So because they are different, so this carbon is definitely chiral. So option 1 is saying it is optically active. Yes, statement 1 is definitely correct. Now statement 2 is saying that this compound is mirror image. Sir, if it is mirror image, then if this is dextro-rotatory, then this should be levo-rotatory. Dextro or levo can only be determined through experiment. Now you have to assign RS only, because I do not know you are dextro or levo. But if you are dextro, then you will be levos. How can I know that? After assigning RS configuration, because RS will definitely tell us the optical activity. We will still not be knowing it is dextro or levo, but if it is R and that is coming S, then they are mirror images. That means they are enantiomers, optical isomers. But if both the optical activity are same, then they are identical structures. So here RS. So now again, because wedge dash, we needed some example for assigning RS. So giving in a live example. Now what are we doing? Sir, assign priority by SCIP rule. So nitrogen becomes prior. This is also carbon. This is also carbon, and all group is same. So for cis trans, there is no as such rule, but just for the case of simplicity, let us take, because trans is more stable. So I'm assuming trans is prior. So trans becomes 2, cis becomes 3, and hydrogen is definitely 4. So I have assigned CIP rule for this chiral carbon, and because lowest priority 4 is in dash only, so no even exchange required. So just move from 1 to 2 to 3. So from 1 to 2, now see, 1 and 2 are opposite to each other. So how you will move, from this side or from this side? So from 1 to 2, after 2 you should find 3. So you definitely have to move this way, as in clockwise. So because we are moving clockwise, so this chiral carbon is represented by R configuration. Now coming to this one, so this is chiral, priority 1, and remember trans we have given more priority. So if 1 is this, then 2 should be trans. Where is trans? This is trans, because this is cis. So this is trans obviously. So because if it is trans, so this we are giving 2 and cis we are giving 3, and this is 4. Again sir, 4th is in dash, so no exchange required, just go from 1 to 2. Here 1 and 2 are just adjacent, so this is 1, say 2. So how we are going, sir? R only. Because just by looking you cannot say that they have same configuration, because tetrahedral is a symmetrical system. So here the application of R and S are very important also, and these are just JEE mains question also. So because it is R, then these two are identical. If it was a mirror image, then if it was R, it should have came out to be S. But this is not S. If it would have been S, then they were optical isomers, as in enantiomers, and it will be mirror image. But because this is R, so this statement is correct, but this statement is wrong. When this statement will become correct, that this is just the identical structure as structure A. So let us go to the option. Statement 1 is correct, yes. Statement 2 is incorrect. So option C is your right answer. Moving ahead. So quickly coming to the last type of isomerism, that is conformational isomerism, because C single bond C is not restricted. So different orientations are possible which will have same molecular formula, same structural formula, but different three-dimensional orientation. So these all orientations also satisfy of being called as stereoisomers, but because they are orientation of one same molecule only, therefore these isomers are termed as non-true or pseudo-isomers. Conformational isomers are simply termed as conformations also. They are even termed as rotational isomers or rotamers or constellations. But remember one thing, they are actually also termed as conformers. But whatever type of orientations you will have, they are definitely called conformations or conformational isomers. But in nature, in mother nature, through our thermodynamic help, through our thermodynamic study, we are able to profile them, to energy profile them. And whenever we were profiling all these orientations, all those conformational isomers whose value whose energy profile attained a minima. That means their energy were relatively less. Only those conformational isomers are actually termed as conformers, and obviously they are interconvertible into one another because they can freely rotate and form one another, and obviously because they are same molecule only, so they have similar physical and chemical properties. Now, sir, if they are same molecule, then how will we draw them? We have new projections also. We have, in order to project those tetrahedral alkanes, there are some projection formula given to us. The first famous formula that came into picture was Sawhorse projection. So we are simply drawing the Sawhorse projection of the most common alkane, that is ethane, because methane is a symmetrical molecule, just one carbon and 4 hydrogens. So what question you also encounter in your examination, so we are starting our common sense with ethane. Ethane is C2H6. So let's say this is one carbon and 3 hydrogens, this is another carbon and 3 hydrogens, and these carbon are bonded to each other. But sir, over here you have not drawn the actual structure. Sir, this is, you can very well see, this is, if this is C, then this is H and this is H, sir. But why you have drawn like this? It is a tetrahedral system. Now remember, let us suppose this is a carbon, the first carbon. It is tetrahedral. Definitely, I'm agreeing to that. What is tetrahedral system? One bond, let's say, with another carbon, and 3 hydrogens, 1, 2, 3. Let's say these 3 fingers are 3 hydrogen. Now, if you just go as a viewer very far away from this tetrahedral system, these 3 bonds will, if you go very far away, it will appear a triangle to you. That's what we are doing. We are going so much far and seeing from this side. So if you just see from this side, then obviously I guess you can very well see, let me tilt it so that you are viewing it from far away. So similarly, it will also get tilted. So let me tilt this guy also. And now let us make that C single bond C bond as well. So this is our C single bond C bond. Okay, sir, this is one carbon, this is one hydrogen, this is another hydrogen, this is the another hydrogen. This becomes CH3. This CH3 is bonded with another CH3. So if you go very far, sir, if this CH3 is just, I mean, if you're very far away, this CH3 and the CH3 behind it, you will not be able to, this H will be completely superimposing this H. So such a form is called Sawhorse projection, and this Sawhorse projection, one bond, one C bond H is completely superimposing the another C bond H, and hence this form is known as a eclipsed form. Sir, but it may have another orientation also. Yes, one another form which is thermodynamically observed is, let's say you have, let us tilt this, let us tilt this guy also, let us make a single bond between carbon. But if this another guy, if this guy is tilted, okay, I'm sorry, if this guy is tilted, let's say like this, as in this scenario, this hydrogen which is downside and this hydrogen which is upside, both the hydrogens will be visible to you. This C bond H inclined on downside and this C bond H relatively inclined on upside, both are visible. Similarly, this C bond H on downside and this C bond H on upside, both are visible. Over here, one C bond H is not superimposing the other, and if you're viewing it from this side, you can find a upside triangle of the front one and a downside triangle for the below CH3 unit. So obviously this conformation where they are not eclipsing each other is called the staggered conformation, sir. But sir, we can have loads of conformations. Now this is the one of the projection formula which is known to us, and obviously while drawing also you must have observed this is not very famous because you have to be some level of artistic ability is required. Now, the another projection formula which became famous in order to show conformational isomer is the Newman projection, which is highly asked by JEE. Now What Newman projection said that, okay, you are viewing this tetrahedral system from this side, okay, what carbon you are encountering? This one. So this will be your first carbon, but in order to draw to represent that first carbon, you just need a dot. What about the back carbon? This will be the back carbon, which is not appearing to you because it has been superimposed by the front carbon. So to that back carbon, we will represent it by a circle. Now, this becomes the front carbon and this becomes the back carbon. What the remaining bonds you have as a triangle. So Newman said that why don't you take the front carbon at front as a dot and back carbon as a circle at the bottom, at behind it. I mean, there's no there is no behind or in front of you, because both we are drawing at the same plane. So this becomes our front carbon, and front carbon had 1 bond, 2 bond, 3 bonds. Now this triangle is very easy to be drawn. Now, what about the other one? Sir, the back carbon also has 3 bonds, but if those 3 bonds are all visible to you, so it must have rotated by an angle of 60 degree. So this becomes your 3 hydrogen, to which I was referring as a downside triangle. So backside carbon is making a downside triangle and the front carbon is making an upside triangle, and these triangles can easily be observed also, although they are tetrahedral, but if you view them far apart, it will appear a triangle to you. And this staggered form, when no C bond H is superimposing the other C bond H, it can be easily drawn and understood, and no as such artistic drawing is required out of you. So this Newman projection becomes more famous, and this is how you represent a staggered form. To staggered form, I am referring as capital S. Now, sir, if let's say this front carbon is fixed, okay, you fix the front carbon. Let's say the front carbon is fixed, because if you have to observe their conformational, you have to pick an origin. So the origin, the reference that we are picking, let's say we'll fix this first carbon, and with respect to this first, with respect to this front carbon, we are moving the back carbon by what? So let's say by an angle of 60 degree. Okay, so let us try. Why 60 degree, I'll tell you, but let us try that rotation by 60 degree of what? Of the back carbon, the white carbon. So the white carbon and white hydrogens will move. So this is 60 degree. If they move, this this hydrogen will be reaching here. Similarly, this white hydrogen will be reaching here. Similarly, this white hydrogen will be reaching here. So you can definitely see this is quite easy and convenient to draw, and this shows the eclipsed form when one C bond H is exactly superimposing the back C bond H, and hence this becomes your eclipsed form, or the to which I'm referring as E. Now, why I said I'm directly moving by an angle of 60 degree, because when we did energy profiling of these conformers of conformational isomers of ethane, what we find is this staggered form, as we can see, this staggered form was more stable because its potential energy was less, and this eclipsed form was having higher energy. You do not have to learn the value, but just for the case of starting this topic, it was having a higher energy by a value of 12.55 kilojoule per mole. So the energy difference showed us that this eclipsed form was having higher energy, and because it was having higher energy, so it was less stable. And this staggered form was having less energy, and because it was having less energy, so it was more stable. Sir, we get from that 0 degree was an eclipsed? If it is moved by 60 degree, you got a staggered form. Sir, between 0 and 60 also we'll get lots of conformational isomers. All those conformational isomers with intermediate energy between eclipsed form and staggered form are termed as skew forms. Of conformational isomers. And because they cannot be extracted in nature, so we just call them as a unit as skew form. So this becomes your staggered form with minimum energy. This becomes your eclipsed form with highest potential energy, and in between you will get infinite number of skew forms, and the potential energy graph will keep on fluctuating between eclipsed form and staggered form. Now, who has the highest energy? Who has the highest energy? Eclipsed form. So because eclipsed form has high energy, so its stability will be minimum. And staggered form with lowest minimum possible potential energy becomes the more stable, and in between you will get those infinite number of skew conformational isomers. Now, some important terms which these slides are all your JEE mains question. So pay attention to it. Now, some important definitions. Why after going and analyzing this energy profile, what we observed is there needs to be defined some terms in order to justify this theoretically. So what we defined is the two types of strain, one being the torsional strain and another one being the van der Waal or the steric strain. Now we very well observe this, that van der Waal and steric strain means the repulsive forces that acts between these groups, because ultimately these groups are also atoms, nucleus and revolving electron. So this atoms or groups, this carbon can also be connected with another number of atoms. So it can be a group also, it can be an atom also. So the repulsive forces that will be acting among these groups will be termed as van der Waal or steric strain. While, sir, this pink bond angle, this pink bond is a bond between the shared pair of electrons. So it's a bond pair. This carbon which is having C bond H bond is also having that bond pair. Through VSEPR theory, you also know that bond pair electrons also repel each other. But to that repulsion force of the electron, of the bonded pair of electrons, that repulsion force we term as torsional strain. So torsional strain becomes the strain due to bond pair electron repulsions, and van der Waal strain becomes the repulsive force generated by the repulsion between the groups that are attached with C. It may be C bond H, it may be some other group. Now these type of strains are acting in what? So if you consider eclipsed form has bond pair repulsion also, so that repulsion is also high. And in eclipsed form these groups are also closer to each other. So because eclipsed form has both the types of strain in it, which is bond pair strain, which is torsional strain, and the repulsion between group, which is the van der Waal strain. So because of the presence of these strain, it will have higher energy. And to the angle, the 60 degree, this angle, this theta is termed as the torsional angle because it is creating that torsional strain. So these terms you should remember for all type of theoretical question. Now, what becomes most important is the another isomers for butane. For propane you can easily draw, so I'm directly rushing into butane. So what is butane, sir? Sir, it is 4-carbon alkane. Now why I have drawn like this? Because I am focusing on second and third carbon. Why? Because it will give me variety of conformational isomers. So let us draw that. Let's say the second carbon will be your front carbon. So how many groups it has in the triangle? Sir, 1 methyl and 2 hydrogen. So this methyl and 2 hydrogen I am representing with a green color. So let us do this. Let us do this exercise. Very important it is. So this is the front carbon, the green one. It has 1 methyl group and 2 hydrogens. And because we need to see different conformations, so let us fix this front carbon. And with respect to this front carbon, let us see how many conformations we can make. I've just drawn the structure so that we can save time, because we already have consumed a lot of time, but I want to give you everything, and in order to give everything we require time. So bear for few slides more with me. Now, after fixing this 1 methyl and 2 hydrogen, what else we have, sir? The back carbon, which I have represented with the white color. What 3 bonds it has? 2 hydrogen and 1 more methyl. Okay, so let us draw that profiling with white color. Okay, now let's start with the most difficult case. Why I am saying most difficult? Because I'm starting with eclipsed form. When that C bond methyl is just below this methyl only. So that hydrogen will be here. The back carbon hydrogen will be here. So it will be, this methyl will be perfectly superimposing the back C bond methyl. So this becomes our fully eclipsed form. And because we know after 60 degree only we attain a extreme of potential energy, therefore all the skew forms we are not drawing and we are just rotating by 60 degree. Let us fix the first carbon and rotate the back carbon by 60 degree. I guess it is very easy. This methyl will come here, followed by this H and H. So this becomes staggered form, definitely. But to this staggered, I am referring as Gaussian staggered. Why? You'll see, because there will be more type of Gaussian staggered forms. Now, sir, how? Just bear with me for a few seconds. Turn this back carbon again by 60 degree. So this methyl will be directly hiding behind this the front C bond H. This hydrogen will be hiding behind this hydrogen, and this hydrogen will be hiding behind this methyl group. So this becomes your eclipsed form. But here, this methyl and hydrogen are not completely eclipsing themselves. Similarly, this methyl and this hydrogen is not completely superimposing themselves. So therefore, to this eclipsed form, I am referring as, this is a partial eclipsed form. This is not potential energy. This is partially eclipsed. Make sure you note that. Now, fixing the first carbon, let us move. So this methyl comes to the bottom and these hydrogens come here. Now, look at this staggered form. This staggered form and this staggered form is different, because over here, the bulky groups are at 60 degree torsional angle between them. And here, bulky groups are at maximum distance. So to this staggered form, I am referring as anti-staggered. Now, again rotate by 60 degree. So this methyl comes here, this hydrogen comes here, this hydrogen comes here. Now this structure is just similar to that of this third structure. So this is also partially eclipsed, this is also partially eclipsed, no difference. Now again rotate by 60 degree. So this methyl come over here, hydrogen over here, this hydrogen over here. This is also exactly the same as this. So this becomes Gaussian staggered, and if you again move by 60 degree, you will reach fully eclipsed, which we have started with. So now doing this energy profiling, which we have done experimentally also, but you do not need to learn the value, but you need to learn one thing. Any eclipsed form is having more energy than any of the staggered form, because here we have extracted four type of conformational isomers in between those infinite number of skew forms. What are those four types? Two eclipsed and two staggered. Among them, eclipsed is definitely of much higher energy. Why, sir? Because eclipsed has torsional strain and the staggered do not have torsional strain. So because staggered have torsional strain at maximum distance, they are at maximum possible distance, because some distance will be there, some bond pair repulsion will be there. So because staggered form is at minimum possible torsional strain, therefore their energy is low, and eclipsed form, any eclipsed form is of higher energy. Now, because of the van der Waal, the crowding of the constituents, the van der Waal strain, which has higher van der Waal strain, sir, fully eclipsed has these bulky groups, so it is having highest van der Waal strain, so highest energy, then partial eclipsed also. And what about the Gaussian and anti-staggered? Because in anti-staggered, the bulky groups are at maximum distance, so the van der Waal strain, the crowding, the repulsion due to crowding will be minimum. So this will be, anti-staggered will be having minimum energy, and Gaussian staggered will be having slightly higher energy than anti-staggered. Now let us do the energy profiling. We started with fully eclipsed. So let's say at 0 degree, I am at fully eclipsed. After moving by an angle of 60 degree, where I reached to Gaussian staggered, as in I reached here. After that, where I reached, sir, I again reached partially eclipsed. After that, I reached anti-staggered. After that, I reached partially eclipsed again. After that, I reached Gaussian staggered here. Okay, in the fourth one, I reached anti-staggered. Sorry, So this is 1, 2, 3. So this is anti-staggered. This is anti-staggered. So here I reach here. Okay. So what is the energy profiling that I'll be getting? Sir, energy is decreasing like this, then increasing, then again decreasing, then again increasing, then again decreasing, and then again I'll be reaching to full eclipsed. So this is the energy profiling that we observed, and therefore we have named 4 types of different conformational isomers for butane. With energy, obviously we can see highest energy is of fully eclipsed and minimum energy is of anti-staggered. So directly rushing to the conclusion. So what will be the order of stability? Fully eclipsed will be least stable and anti-staggered will be most stable. With having this conclusion in our mind that torsional strain in all the eclipsed form will be equal, in all the staggered form will be equal, because the bond pair repulsion is same. But obviously torsional strain in eclipsed form is much higher than any of the staggered form. And what about the steric strain? Steric strain I'm not comparing among them, but yes, among eclipsed form fully has more crowding, so more steric or van der Waals repulsion, and similarly Gauche has more van der Waals or steric repulsion or strain. But why I have given this symbol that maybe or maybe not, this is not always true. Only when there is case of intramolecular hydrogen bonding, then Gauche becomes even more stable than anti-staggered. Like for example, in case of ethylene glycol or in case of 2-chloroethanol, you can definitely have that common sense through chemical bonding. That Gauche staggered, yes, definitely generally has repulsion of bulky groups. But if those bulky groups are attracted towards each other, let's say if they can form hydrogen bond, like this O bond H can, so over here Gauche becomes more stable than anti-staggered. And similarly, although chlorine said, that's why this is a famous example, because generally we find hydrogen bond with oxygen, nitrogen and fluorine. So in such cases it has been observed in mother nature. So this you have to keep in your mind, that 2-chloroethanol also have more stable Gauche form. That means its energy will be less, because it is also intramolecular hydrogen bonding impact is also seen in this. Moving forward. So finally, coming to the last slide, that the cycloalkanes whose carbon are also sp3 hybridized, now these bonds try to remain at an angle of 109 degree 28 minutes. But when they cyclizes, like over here, you can very well see they are forced to come close to each other. And because they are forced, so repulsion will increase, and the strain created in such cases of cyclic compounds are termed as Baer strain or simply ring strain. Now, this was beautifully experimentally observed by their enthalpy of combustion that they were giving out, that although we say alkanes are not reactive, but because of this strain, these cyclic alkanes are very reactive, just like reactivity of an alkene. Like alkene undergoes hydrogenation, so they also undergoes hydrogenation. But to the mother's nature's surprise to us, 6-membered ring is free from any type of Baer strain or ring strain, which can be definitely observed by its value of enthalpy of combustion. And 5 and 7-membered ring structure are also stable. They also do not have that much of strain. So because cycloalkane is also very stable, therefore its conformers like of normal alkanes are also known in nature, but those cyclic conformers are actually asked by JEE Advanced only. And because I already have exceeded a lot of time, because I want to give you everything as I already said, so this is me, Gaurav Singh Arora, signing off with just one statement, that is, every bit of this hard work that I have put on with 121 slides, I just want you to revise it very, very well. Maybe go to the application or PW application where you can make the speed 2x and revise. And once you finish this, once you revise this, I definitely want it will be a reward from your side that you will be commenting that yes sir, I have worked for myself, and thank you. We'll meet in the next class.